চালিয়ে আসলাম, অঙ্ক হচ্ছে, ওটা একটু পরে গিয়ে করে নিচ্ছে এটা। হ্যাঁ,
Okay, Viplav, we are live.
okay, we are live, right?
Yeah, we are live. Yeah.
Also, one more thing, do we need to, when we are live streaming, we need to do the recording?
No, not necessary because it gets live streamed on YouTube, no?
Okay. It will remain on YouTube after that.
For example, you can test by going to the TCG CREST channel
Yeah.
from your Biplab's YouTube account or something, and see whether the conference from a couple of days back is there already or not. The one that was in honor of Professor Butker.
Nice.
So that would be a quick check of whether the live stream automatically just sits in the channel.
Yeah. Okay. Yeah, we have to check that. Yes.
Right. So we are live now, and yeah.
Yeah. Okay then.
All right. I've also informed Professor Das.
Yes.
So he should be joining any moment now, I guess.
Okay.
Yeah.
Okay,
So I'll
then
make
see you.
you the host. Okay, thank you,
Yes.
Biplab. So I'm making you the host now.
Okay.
Yeah, if there's anything, always feel free to call me. And yeah.
Okay.
Okay, thank you.
Thanks.
Yeah.
Sir, can you hear me?
Yeah, I can hear you.
Okay.
So who else have joined? আর কেউ জয়েন করেনি এখনো?
একবারে একটাই হবে না? এইটা কি? হ্যাঁ করো কানেক্ট করো।
Bhanu, did you join?
ওখানে দুটোই হয়ে যাবে। আর কেউ জয়েন করে?
Who joined? Hi, Bhanu.
Yes, Bhupen, can you hear me?
Yeah, I can hear you.
Okay, so
Dr. Chatterjee will be in soon?
yeah, I have sent him a reminder this morning as well.
Mm-hmm.
So we spoke day before yesterday night, that is Sunday night.
Mm-hmm.
And yeah, he's he said he may take about a little over 5 minutes. I said he can go up to 10. So let's see. So there is Biplab and is TCG CREST is who? Snehal or?
TCG CREST on Snehal's desk is also there. It may be also.
Oh, I think Dr. Chatterjee is trying to join now.
Yeah, right. You can see that.
Yeah.
Yes, yes.
Oh, hello, Punenduda.
Bolo.
So you're in? Yes, 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 yes. Okay.
Well, yeah.
Yes, yes. Okay. Thank you for
Yeah.
joining us. I mean, it must be quite late for you at night.
No.
We are
It's just
also live on YouTube.
Yeah. Oh, we're live on YouTube as well.
early
Oh,
morning for you.
yes.
That's okay. Good morning, Supuranduda.
Good morning, Manu. Bhupen, how are you?
I'm fine. And
Where are you? Office
I'm
or home?
in my office. No.
Oh, okay. Good.
So
It's
this is
early. Very
so
early to get there.
It's early, but it's okay.
yeah. So that is Snehal. So Punendu,
My screen is Snehal.
oh Punendu, I think Snehal. You can see him, and he.
No, I
Yeah,
don't
he's
see
really
Snehal.
he's really the chair of our organizing committee. He's done a wonderful
Oh.
job. Okay.
Hello, sir.
How are you, Snehal? I didn't think Snehal is on.
Yeah, he just raised his hand only. But you can
Oh,
talk.
okay.
Yeah. So Dr. Chatterjee just asked you how you are, Snehal. Okay. Yeah.
Yeah, I'm fine. How are you?
Good. Snehal, how are you?
Yeah, hello. Can you hear me?
Yeah, I can hear you. Good. I think
Yes.
people will.
So can you hear me? Can you all hear me?
Yes,
I can hear you.
Yeah.
I think
Yeah.
there is a little bit of delay because YouTube live is going delay by almost more than 30 seconds.
So are you on YouTube, Snehal?
Snehal, did you hear what Bhanu asked?
He might be on YouTube, actually.
Yeah, it's showing.
No, I am on this Zoom link also.
Oh.
But YouTube is running parallel.
Okay.
Yes, yes.
Hmm.
No. I am on both.
You are on both.
Since
Fine.
YouTube is running parallel, so this,
Okay. How many people on YouTube?
four,
Okay.
5 now.
But still too early for many people, I think.
Yeah.
But should you start or wait for 1 or 2 minutes?
Yeah, 1 or 2 minutes.
There's only 7, 8 people, right?
Yeah, that's right. 9 plus 4 probably.
So we should wait till.
Maybe you can wait for 1 or 2 minutes.
Just wait a couple of minutes and I'll probably take 3 minutes or so.
Yeah, I'm also 5 minutes, so can close it.
So you can wait 2 or 3 minutes and then probably some more participants come in. The number of registered participants are more than 300. It's more than 330 rather.
Yeah, I think they're probably going to come as. Right now, we only have people that are homegrown.
Yes, yes. Now yeah. Hmm.
We had one speaker from MIT, and he's now in Switzerland. So we had to reschedule his talk.
Yes. Yes. Well, I think our first speaker, Dr. Spring, has joined. So, yeah.
Hello, yes, can you hear me?
Yes, we can hear you. Good morning, Dr. Spring. I mean,
Good morning.
from India, I think probably, yeah, it's still morning in Japan, I think. Okay, so.
Time difference is quite good.
Yeah, the time difference is 3.5. Japan is ahead by 3.5. So that's, so this is Dr. Spring, Dr. Peter Spring. He is a member of Professor Nakamura's group. So
Very nice, Dr. Spring, for you to join us.
Yeah, thank you so much for the invitation. I'm looking forward to the conference. Yeah.
You're welcome. I mean, so we have Dr. Chatterjee, who is the chair of our board of directors. And so he will make some opening remarks. And yeah, I think we can, should we start now? I mean, there are not too many people, but we can still start, I think.
Yeah, otherwise we won't be able to keep the timing. All right.
Yeah.
Good morning, good afternoon, or good evening, depending on which part of the globe you are in right now. And I am Bhupen Dev, professor at the Center for Quantum Engineering, Research and Education, in short, CQuERE, and which is part of TCG CREST, TCG Centers for Research and Education in Science and Technology. I welcome you all to this symposium on quantum computing with superconducting qubits. Our center is about 3 years old, and we are still small, with about 5 theoreticians in the faculty, including our director, Professor Bhanu Pratap Das, and 3 experimentalists. And our experimental program currently involves photonic integrated circuits, nitrogen vacancy centers, quantum sensing with cold atoms, and superconducting quantum computing. And of course, we are eager to interact with the world leaders in these areas. So while we are setting up our superconducting quantum computing facility, our theoreticians are already using quantum computers available at different places like IBM, D-Wave, RIKEN, etc. And currently their main work on quantum computation is regarding different properties of atoms and molecules. However, soon their work will gradually evolve into more translational research towards realization of the vision of our founder, that is knowledge creation, knowledge application, and knowledge dissemination. As you notice from the symposium program, we have many reputed speakers today and tomorrow. And I'd like to thank all the speakers for accepting our invitation. And we have registered participants from many countries, over 10 countries. And I thank you all. And I am sure that you will immensely benefit from the talks by these experts. Now I'd like to invite Dr. Purnendu Chatterjee, the founder of our institution and chairman of the board of directors, for delivering his opening remarks. Dr. Chatterjee.
Thank you, Bhupen. Thanks everybody that's joining us on this wonderful 5th and 6th December and engaging with us on superconducting quantum computing. So the vision of CREST is to integrate into the global innovation ecosystem to contribute on resolution of large-scale science and technology challenges to solve crucial societal issues. CQuERE, as Bhupen mentioned, Center for Quantum Engineering Research and Education, which is emphasis on quantum computing, stands as a pivotal vertical within this vision and to contribute to this field. And we hope it will gain significant advantages from our other verticals in AI, ML, neuroscience, and the material sciences capability that we have built up so far in CREST. The field of quantum computing is rapidly advancing and holds the potential to revolutionize conventional computing paradigm. The progress in conventional computing following Moore's law is impeded because of this heat dissipation challenges. To overcome those, some novel ideas have been going around, as you have seen from movement from GPU-based computing from CPU-based computing. But notwithstanding all of that, many hard problems needs a new hardware substrate. And we hope quantum will be that substrate to help in drug discovery, to help in coming up with new materials for batteries, and many other areas where quantum chemistry is critical. Now, for quantum computers to become a reality, several challenges must be tackled, spanning hardware, extensive error correction requirements in quantum systems, software management, and intricate interface between classical and quantum computing. Within quantum hardware alone, there will be 5-6 critical areas of focus, including development of qubit networks, stable qubits, and many more, which you all are familiar with. But success in this hardware domain will hinge on numerous breakthroughs in these areas, with individuals worldwide contributing to these victories. Intriguingly, I think some of these breakthroughs may come also from unconventional approaches. So you'll have both conventional approach, which will be like taking a problem, developing a hypothesis, testing the hypothesis, coming up with things. There will also be non-traditional approach, similar to what a bumblebee does, which is not supposed to fly according to aerodynamic principles, but it does. So I hope both conventional and non-conventional approaches will help in coming up with these breakthroughs. Numerous breakthroughs have come together to make CMOS an ubiquity today over the last 50 to 60 years. I see the same journey for quantum computing, and many of you that are assembled here today are part to those breakthroughs. It'll be an exciting period for you. You will see how this field that you are engaging in developing in front of you. And I'm confident you all will play a very, very exciting and exhilarating role. I hope CREST and CQuERE makes a significant impact with you in this journey. And thank you for being part of this endeavor. Thank you, Bhupen and Bhanu. Over to you.
Yeah,
and have wonderful 2 days.
Yeah. Thank you, Dr. Chatterjee, for your enlightening forewords towards the conference, towards the symposium. So we are almost close.
I have given you 2 minutes.
Yeah, sure. You can take 2 minutes.
I've given you 2 minutes.
Oh, you have given me 2 minutes. No, I have already spoken. So we are about to start our session.
Yeah.
Okay. So let me invite Professor Bhanu Pratap Das, the director of our center, to chair the first session. And Professor Das, his research work involves involving quantum many-body theory of atoms and molecules and its applications to fundamental physics and quantum computing. And of course, eventually, as I mentioned, this is going to expand into more translational research. And before joining our center, Professor Das was in Tokyo Institute of Technology. And after coming back there, he has taken this responsibility to lead our center. Professor Das.
So thank you very much, Professor Deb, and thank you very much, Dr. Chatterjee, for your inspirational words. So we'll now start the first session, and the speaker is Dr. Peter Spring from RIKEN. He is currently a member of Professor Nakamura's group on superconducting circuits for quantum computation. During his PhD, he worked on developing a tilable superconducting circuit for quantum computation. The title of his talk is Developing Intermediate Scale Superconducting Circuits with 3D Wiring. Dr. Spring, please.
Yeah, thank you very much. It seems that I'm not able to share my screen. It says host is disabled, participant screen sharing.
Just a second. Can you share it now?
Yes, brilliant. Thank you.
So the talk is for 45 minutes, and then I think 5 minutes questions answer. So shall I remind you at some point?
That would be great. If you could give me maybe a 5-minute reminder before the end.
Yeah. Okay, sure, yeah. Okay.
So yeah, thank you so much for that introduction, and thank you very much for inviting me to give this talk. So yeah, I'm a visiting researcher at RIKEN now with Professor Nakamura. I've been here for about 2 years, and so sort of as was said in the introduction about there being many hardware challenges towards building quantum large sort of quantum computers. This talk is going to be about sort of some of those challenges, and in particular challenges related to superconducting circuits. So yeah, for a brief outline of the talk, I'll just introduce superconducting qubits and circuit architectures, that's going to be very well trodden ground, I think, for many of the people here. So I'll go over that quite fast. Then I'll talk about the architecture that we've been working on at RECON, and show some of our results. And then actually I'll discuss a little bit of theory that we've developed for how to model periodic quantum circuits. So we found this was quite useful for us as we wanted to know how our circuits behave as we scale them up to large scales of for instance 10 by 10 arrays or larger of qubits. How does the crosstalk and the coupling between qubits in the network behave? And then I can show some comparison with experiments from these models. And then finally, I'll talk about readouts. And so recently we've done some work to try and demonstrate fast readout in our circuit architecture. Okay, so first on to just superconducting qubits. So we're all familiar with this sort of ideal qubit, the just two energy levels, and you can represent it so on the block sphere, and this is what we really want, but nature doesn't really hand this to us, so we have to try and go out and find candidates in nature that can behave like an ideal two-level system. So one obvious candidate is atoms. So we can use the just energy transitions between the different levels of an atom, and there are many different candidates we can choose from, and you can find members that have sort of an energy structure that lends itself well to behaving like a qubit. So you can identify two levels that you can use and not have to worry so much about other levels. So one issue with using atoms is they tend to have very small dipole moments. So they couple quite weakly to light. So even though they can behave like an ideal qubit quite well, they can be quite difficult to drive, and they can be quite difficult to make interact with one another. This does have a positive as well, which is that they tend to have very high coherence times because they don't interact so strongly with environmental degrees of freedom. But so what we work on at RECON, and I think what this conference will mostly be talking about, is superconducting qubits. So yeah, this is kind of remarkable in that you can take sort of very large scale, up to millimeters or larger scale devices formed from sheets of superconducting metal that you then join with these special elements known as Josephson junctions. And you cool them down, and then they can actually display remarkably simple behavior, and they can behave like artificial atoms. So they have an energy structure that's kind of analogous to an atom. And crucially, because these Josephson junctions that we use, they're a non-linear but also non-dissipative circuit element. So it allows us to create energy level structures and ladders that are anharmonic, and so you can pick out two energy levels to use as your qubit. And because these things can be very large, they can have very large dipole moments, which means that you can drive them very easily and couple them to one another very strongly. So we tend to have very fast gates and fast readout times. But a obvious disadvantage is that they also will couple very strongly to environmental degrees of freedom. So one of the biggest challenges that we face is actually trying to reduce the noise in the environments of these qubits, and to sort of keep the information in the qubit state coherent for as long as possible. Okay, and then very briefly, so we use transmon qubits in our work at RECON. So the idea of the transmon qubit is that if you take the Hamiltonian of a simple Josephson junction shunted with a capacitor, it has this form here, which is very close to a well, it's very close to what we would like, but there's this unwanted sort of offset charge term, Ng, and so this relates to sort of uncontrolled charge fluctuations or voltage fluctuations in the device, and so for low ratios of EJ to EC, what you see if you plot the energy structure of this Hamiltonian is that the energy levels are very sensitive to this offset charge. So it creates a large amount of noise in your qubit and means that your decoherence times are very, very short. However, it was kind of realized that if you operate in a regime where this EJ over EC ratio is large, so sort of around over 20 or so, the energy levels flatten out, so they lose this sensitivity to the offset charge. And then if you expand the Hamiltonian, it can take a very simple form. So you can get sort of a simple harmonic oscillator, and then with a crucial nonlinearity, which makes these energy levels not equally spaced. And so there's some really nice features about the transmon that have made it so popular. So even though you exponentially destroy the charge offset sensitivity, the levels of the qubit only become more like less anharmonic, like the 1 over the square root of the EJ over EC. So they still remain suitably anharmonic to use. And then while you become less sensitive to fluctuations in the offset charge, it actually still couples very strongly to AC voltage sources. So you can still couple a transmon strongly to drives to manipulate the qubit state. And also you can couple it strongly to, for instance, other transmons and to resonators for performing readout. Okay, so then just a little bit about scaling up circuits. So for a kind of typical unit cell would be you have a qubit, then you couple it to a control line, and then you also couple it to a readout resonator for performing measurement of the qubit state. And then you also want to couple neighboring qubits together to be able to perform entangling gates so that you can actually build up an interesting qubit state in a larger scale system. And so then you can imagine that this is a kind of cartoon of how you might couple these or put these circuits together. So you can build up larger arrays just by tiling these kinds of unit cells. So another nice thing about superconducting circuits is that we can just lithographically define them onto silicon substrates or sapphire. So they in some ways are very straightforward to scale up. However, there are some issues. So one issue that crops up is as you make the circuit larger, you can run into problems of spurious modes. So if you have any disconnected ground planes, for instance, you can get voltages that build up across them at certain frequencies. And this can cause decoherence and crosstalk. However, so that challenge is relatively straightforward to combat, as long as you're careful using, for instance, like air bridges or through silicon vias and suitable packaging. You can control the spurious mode problem. Another problem is this wiring problem. So it's very simple to understand. It's just if you build up a 2D array of qubits, you can imagine that you can send wiring to the edge qubits very easily, but it gets harder to access the qubits inside the array. And so as the array gets larger, if you're trying to do all of your wiring from the edge, it gets harder and harder and harder to reach the circuits in the middle. So a solution to this issue is to use out of plane wiring. So here somehow you route your wiring off the chip, and then you're not limited by this problem of edge connection. So some examples of different types of out of plane wiring. So there's flip chip bonding. So you can see, for instance, this was used very successfully by Google in their Sycamore processor that they used to demonstrate their quantum supremacy experiment. Then you can use multi-layer wiring. So this is similar, but here instead of having all of the wiring fan out on one PCB, which also runs into problems as you scale the number of qubits larger, you just use more and more layers of PCBs. So here, as you increase the number of qubits, you can in principle just increase the number of layers to avoid this fan out problem. And then another approach is to use a kind of fully vertical wiring scheme. So for instance, so in my PhD, actually, I was involved in this approach at Oxford, where we just used coaxial cables directly that would come in vertically and couple to our circuits. Okay, so that vertical wiring is the approach that we're taking at RECON. So now I'll talk about the circuit architecture that we're using here. Okay, so here's a schematic of our architecture. So there are four main parts. There's this control wiring part. This contains these 3D wiring. So it's pogo pins actually that are coming in and contacting the backside of our circuit chip. So the circuit chip here, it's in our design, we have this unit cell that's about 4 millimeters by 4 millimeters. And each unit cell contains 4 transmon qubits. And we're using 4-to-1 multiplexing on the readout. And so, yeah, the coupling to the outside world is done via the backside of the circuit with this 3D wiring. So then on top of the circuit chip, we have a cover chip. And this is to reduce crosstalk between circuits and importantly, make sure that all of our ground planes are connected to try and remove spurious modes. Then on top of this cover chip, there's the package cover, and this is just providing a compression force down onto the cover chip to ensure that that the cover chip well connects to the circuit chip and that the circuit chip well connects to the control wiring part below. Right, so now I'll just go into a little bit more detail about each of these parts. So here are some images of our control wiring, and this is for a 64 qubit device, this example. So here there's 80 cables coming in. This is UT47 semi-rigid cable, and then these coax cables they come up into this part where they connect to these spring-loaded probes. So these are made from gold-plated beryllium copper. The reason we use beryllium copper is that so there's a spring inside inside this PTFE sleeve, and so the spring constant of beryllium copper doesn't change very much depending on the temperature. So it still gives a good well, it has a similar spring constant down to cryogenic temperatures. So we're operating at around 10 millikelvin here. So then, and yeah, these probes have a stroke of about 1.5 millimeters in this case. Then, if you look at the right figure, and you can see the zoom in on this control wiring, I tried to separate this out into the different unit cells. So you can see at the center of each unit cell, there's a pin that we're using for readout, and that's for reading out 4 qubits. And then on the edges of each unit cell, there's 4 pins, each controlling one of the qubits. And then between these control wiring pins, there's actually other pins on the circuit. These are just used to try and ensure that there's good grounding between the circuit and this enclosure. So they contact the different ground planes on the chip. Okay, and so in total on this part, there's 169 pins, and each pin is when it's compressed, it's pushing with a force of about 16 grams. So actually, when we load the chip on this, the chip is being pushed up by with a force of about 4 kilograms. Okay, so and I'll talk about that a little bit more later. So then, yeah, so for the control methods, in slightly more detail, this is a picture of the backside of the circuit, and this is the backside corresponding to one unit cell. So in the corners, you can see there are these these 4 regions. This is where the qubit probes contact, and then in the center, there's the region where the resonator, the readout probe, contacts. And the coupling principle for the circuits is slightly different. So for the qubits, the probe contacts the backside, and then the coupling to the qubit is actually done capacitively through the substrate. Whereas for the readout, the probe actually is contacting directly to a through silicon via, and then that via carries the signal to the front side of the circuit, where it then capacitively couples to the resonator. And yeah, so one of the reasons we're doing that is that we've been exploring quite fast readout capability, and if we use this structure where we send the signal through the substrate with a via, we can couple the resonators to the readout line really strongly. So then on the control for the qubits, so yeah, slightly more detail. Again, we found that actually in our original design, the qubits coupled very, very strongly to the control lines, much too strongly. So they just decayed their energy radiatively through the control lines almost immediately. So we adjusted the design so that we actually inductively shunt the central pad on the backside to the ground with these spokes. You can see an image of that in the middle, and so we can change the number of spokes and the width of these spokes, and in that way we can control the coupling of the qubits to its control line. And an advantage of this is that we can control that width very accurately because it's just defined by lithography. So we can have precise control of how strongly our qubits couple to the wiring, and then so you can see some measurements of this on a 64 qubit device. So this is just a histogram of Rabi frequencies of different qubits. So we've driven the qubits through their own control line, all at the same drive strength, and just looked at the variation in the frequency of the Rabi oscillations. And yeah, so for 80% of these results, they all fall within about a 1 megahertz variation. So this corresponds to about a 1.3 dB spread in the effective drive strength, and so that corresponds quite well to the variation just in our dilution fridge lines. So it's indicating that for 80% of qubits, the control pins are coupling with a very uniform coupling strength. In 20% of cases, the effective coupling is weaker. So that indicates that we might still have some problems with our 3D wiring. So maybe sometimes the pin isn't contacting perfectly well to the backside, or maybe there's an impedance mismatch where the coax cable sort of terminates and connects to the pogo pin structure. So there's still improvements to be made, but we think it's encouraging that we can see this uniform coupling. Then the the cover chip. So this is just a silicon chip that's been coated so first it's coated in titanium nitride, then we do 300 micrometer deep RIE etch, and then coat the etched surfaces in aluminium. Then we place bump bonds, indium bump bonds, onto the titanium nitride, and then press this down onto the circuit chip. And so the design is to try and ensure that there's no disconnected ground planes anywhere. And so we're not using any air bridges in our design. We're just connecting ground planes using these cover chips. And then finally, this is a picture of the package cover. We're actually, as you can see, this has many pins in it. In this case, it's got over 700 pins. This is actually overkill. We're reducing the number of pins in future designs. So these pins don't provide any control capabilities. They are just there to provide a compression force to push the circuit chip down into the wiring. So we want to make sure that the force pushing the circuit down is larger than the force provided by the control wiring part, because we want the circuit to have a good galvanic connection to the control wiring and also to the ground that's surrounding the control wiring pins. So for that reason, here we have many of these pins. So actually, these pins are providing about 15 kilograms of force down onto our 64 qubit devices. So in total, those devices are under a compression force of nearly 20 kilograms. But we haven't seen any issues with chips breaking after mounting. So we don't seem to have any issues from this large compression force. And then this is how it all fits together. So you can see just the control wiring part. Then after we've mounted a 64 qubit chip, then with the cover chip on top, and then with the package cover. Okay, so now I'll talk just briefly about the circuit fabrication. So we're using a double-sided process because we have circuits on both sides of our devices. Aluminium through silicon vias. So this through silicon vias are for routing the signals for readout, and also importantly for suppressing modes inside the substrate as we scale up. Then the circuits are made from titanium nitride. The junctions are made from aluminium using the Manhattan process. And then we're doing laser annealing of our junctions to tune the frequencies. Okay, so just general steps. Very briefly, first of all, we define our through holes for the vias using deep RIE. Then we deposit titanium nitride on both sides of the circuit. Then we deposit aluminium on top. And during this step, we also coat the sidewalls through the through the silicon, which defines the through silicon vias. Then we define the aluminium patterns using a wet etch process. So the main features defined at this stage are we have these edges around the vias. This is related to the via fabrication process. So we want to ensure that we have a good galvanic connection from the top side to the bottom side. And then we also define probe pads that we use for testing resistances of qubits. So we don't like to do resistance measurements directly against the titanium nitride because we don't get a good contact between the probe and the titanium nitride surface, but we do with the aluminium. Next, we define the titanium nitride circuits by a dry etching process. And then after that, we do the junction fabrication with the Manhattan technique. And then this is a picture of a completed 3-inch wafer. So this has got 5 64-qubit circuits on it. Okay, and then just some images of the via fabrication. So the way we do this actually is we evaporate aluminium at an angle onto the substrate and rotate the substrate while we do the evaporation. And in that way, we coat the sidewall, which creates this via, and then we do it on both sides. And you can see some images, for instance, on the right, you can see the kind of the galvanic connection between the sidewall aluminium and then the aluminium on the surface of the substrate. So it's really important to have a good galvanic connection between the sidewall and the surface layer. Okay, so now I'll talk about the circuit design briefly. So yeah, it's fixed frequency transmon qubits. We're operating quite high frequencies between 8 to 9 gigahertz. Nearest neighbor capacitive couplings, cross resonance entanglement gate. Sorry. Then 4-to-1 multiplexing on readout, and our readout resonators are around 10 to 11 gigahertz. So on frequency assignment, we're using a maybe slightly unusual frequency assignment pattern. So we have 2 unit cells. So within each unit cell, make sure that neighbors have a large detuning actually. So we're not operating in the so-called straddling regime of the cross resonance gate. We detune our neighboring qubits by on the order of 1 gigahertz. So an advantage of that is that crosstalk along the circuit decays a little bit faster, and also we are a little bit less sensitive to small frequency errors. So we can tolerate small frequency errors better without having frequency collisions. And then so we have these unit cells with 4 qubits, and we slightly offset the frequencies in neighboring unit cells so that we can try and avoid next nearest neighbor frequency collisions. So in this kind of pattern, in total, we have 8 target qubit frequencies, 4 for each neighboring unit cell. And so to try and achieve this pattern, we're using laser annealing of junctions. So the idea here is that you can selectively anneal junctions to change their resistance, which then corresponds to their critical current and the frequency of the qubit. So this is some of our results of this work, and this work has been done in collaboration with Fujitsu, the laser annealing. So here you can see an example 64-qubit device where initially we had about a 3% standard deviation in the junction resistances. And then after laser annealing, so after 1 day, that standard deviation had been reduced all the way down to 0.5%. But one problem that we have is that we see that after we laser anneal, we sort of seem to reset the aging process. So the junctions age significantly after the laser annealing. So after day 2, the standard deviation has remained small, but the mean has moved up by about 150 ohms in this case. And then as we wait longer, so after a week, the standard deviation has increased actually back to about 1.5%, and the mean has moved again. So this is a bit of a problem that we have. So there's a few strategies you can take. One is that after laser annealing, you try and just cool down your device as quickly as possible and get it under vacuum to prevent this aging. Or you can sort of try and calibrate the aging and take it into account when you target the frequencies for your laser annealing. But yeah, one of the disadvantages of that approach is that this spread seems to return a bit. But okay, so then this is an example of some results for our annealing process on a 64 qubit chip. So 8 of the qubits were dead in this case, but we had these 8 target frequencies that I spoke about earlier. And here I've just grouped the measured frequencies of qubits by group. Into these 8 different bands. And so if you look at the variation of frequencies within groups, it tends to be around 1%. So that's at the moment what we can achieve with our laser annealing process, but we would like to try and improve that further. And then just some general results on these devices. So we have coherence times of about 40 microseconds T1, 60 microseconds T2 echo. Our single shot readout is about 99% in the 64 qubit devices. So I'll speak a little bit about fast readout later in our 16 qubit devices. So then single qubit gates best are around 99.96, and these are fasts in less than 20 nanoseconds. And then our best 2 qubit gates at the moment are around 99.1%. And this is largely coherence limited. It's because our 2 qubit gates are quite slow. We're using cross resonance with these large detunings between neighbors. Okay, so now I'll just change gear a bit. So now I'm going to talk about these models for periodic quantum circuits, and I'll have to move a little bit fast through this section. So here you can see this is a toy model circuit for an array of qubits. So the idea here is that we have qubits that are nearest neighbor coupled, and we sort of want to know what's the, for instance, the J coupling between any 2 pairs of qubits in this array. So our approach to solving this problem is you can first imagine having a current source placed across all of your junctions in each qubit. And you just vary the current in neighboring qubits only by a constant phase factor. And so if you have that system, because of the periodicity, you can actually use just Kirchhoff's voltage laws, and you can map this whole array. So this is an infinite array into a single unit cell. And so you have just a single qubit now, and it's shunted by this impedance, and this impedance depends on the phase that's the phase difference between unit cells. So this circuit is then quite easy to actually just solve, often analytically. So you can solve for the impedance across the junction in this single unit cell as a function of the frequency, and then also as a function of this phase term between unit cells. And so what's nice is that then you can apply a Fourier transform, and you can actually map this onto a system that we're interested in. So in this case, you can map it onto a system where now you have a single current source just on any particular qubit, and you can calculate the voltage that induces onto the qubit, onto any other qubit. And this is sort of a transfer impedance, and there are methods that are known for how to map transfer impedances between qubits onto an effective transverse coupling between qubits. Okay, so a kind of concrete example here is the case of a concentric qubit. So yeah, if you see this equation for the J coupling, it has this this form, and so what we found is that for floating qubits, if the outer pad has got a strong capacitance to ground, much stronger than the inner pad. What it means is that the J coupling, so the crosstalk, it decays much slower than, for instance, the case of a grounded qubit. So your next nearest neighbor J coupling might be only 10% of your nearest neighbor J coupling for a concentric design, which is quite large. That's quite a large crosstalk term compared to if you use a grounded qubit, where it might be 1,000 times smaller or more. So this sort of prompted us to maybe try and move away from using floating qubits, which I'll show you later. And then very briefly, so this this approach is quite general. So we can also model finite length effects. So we could look, for instance, at a coupler of this form. So like a 2 qubits coupled by a section of transmission line. And what we actually find is that the J coupling, the equation has quite a simple form, and it depends on whether or not the coupling circuitry can propagate traveling waves. So actually, you can plot the band structure of such an array of coupling circuitry, and you can see that as long as you're operating in a band gap, the J coupling will decay, in a well-controlled sort of just exponential way. And maybe an interesting result we found was that for grounded qubits, actually the decay of the crosstalk is just fully determined by the nearest neighbor coupling strength. So it actually is independent of the type of coupling circuitry that you use. So then we could do a similar analysis now for a 4 qubit unit cell. So you can either solve a circuit model or do a finite element simulation. And again, so we found that in our circuit, as long as we are operating below 16 gigahertz, we're in a band gap. So the crosstalk should decay exponentially in a well-behaved manner. So then here we can also look at the control line crosstalk. So this is saying like from a particular control line, how strongly can I drive different qubits? And you can also model this using this same sort of periodic circuit model theory. So then this is an example for the simulation of the control line crosstalk in our device. So we see that, we can simulate this, and if you take a cross section, we can predict that the control line crosstalk decays, in a simple exponential manner. And then we can compare that to experiments. So here we monitor a qubit, we input a signal from a different port, and then we just measure the relative frequency of Rabi oscillations in the target qubit and the control qubit. And then we can map that out and get an array of control line crosstalk. And we see that if we look at cross sections, the decay is agreeing quite well with the simulation. And the nearest neighbor crosstalk is small, so it's less than 40 dB, and next nearest neighbor is less than 50 dB. Okay, so I'll move very, very fast through this section. So this is just talking about some work we've done on trying to demonstrate fast readout. So, okay, as a result of maybe these periodic circuit models, we've adjusted the circuit. So we've gone from these quite large floating qubits to these grounded qubits, you can see. And then we've also adjusted our readout circuitry. So we've moved from using a single Purcell filter that's a lambda/2 resonator for our 4 readout resonators, to using dedicated Purcell filters. So 1 lambda/4 resonator filtering each readout resonator.
Excuse me, Dr. Spring. Sorry to interrupt you. You have 5 minutes left.
Okay, brilliant. Yeah, sorry, I'm running a little bit late, so I'll go through this section very fast. Thank you.
Fine.
So dedicated per cell filtering has become a very popular way of providing per cell filtering to qubits. So the reason is that you get kind of a double benefit. So it gives you better per cell filtering. So qubits don't decay through the readout line at all, but it also suppresses measurement crosstalk. So yeah, very briefly, you want to have your readout resonator and your filter resonator on resonance. And when you do this, they hybridize into kind of two sets of modes, a low mode and a high mode. And you actually do your readout by interrogating these hybridized modes instead of the kind of bare readout and filter mode. And so these are some examples of where this has been used. So it's recently was used successfully in a surface code demonstration experiment. So yeah, typically you couple your readout resonator and your filter resonator capacitively. And so it has this kind of equivalent circuit of just two resonators capacitively coupled. So this is a picture of our approach. So it's slightly different. We're coupling the resonator and the filter via a section of sort of multi-conductor transmission line. And so the equivalent circuit here, it has a capacitive coupling, but also an inductive coupling. And the point of this is that we can take advantage of this effect to actually create an extra layer of filtering. So it results in an additional notch filter. So you can actually find an analytical formula for where this notch should be. And so the benefit is that if you target this notch frequency to be around your qubit frequency, we can explore having filters that are very strongly coupled to the readout line, but still we don't suppress the T1 time of qubits at all. Okay, so then this is just some measurements in one of our 16 qubit chips. So we use this method we call Stark shift spectroscopy to measure the filtering of our resonators. And so we can see that we indeed get these notches, and we can quite accurately the notches accurately agree to our COMSOL simulations. So we can target the notch frequencies well. And so around these notches, the T1 limits of our qubits exceed like 100 milliseconds. So they're really strongly protected. Okay, so then this is then showing spectroscopy on one unit cell in this device. And so here we're plotting the group delay, and you can see the fit to a reflection model. So yeah, we can use this spectroscopy to accurately extract the different circuit parameters. So the J coupling between the readout resonator and the filter, and the G between qubits and resonators, and also the decay rate. And then we can look in the time domain. So here I've just sent in a long 224 nanosecond pulse onto a resonator and looked at the ramp up time, and then the ramp down. Maybe just very briefly, an interesting point is that the transient dynamics of using these dedicated filters, they depend on all of these parameters. So the external coupling, but then also the detuning between the qubit and between the filter and the resonator, and the J coupling between the filter and the resonator. Okay, and so then, so this is just our best result on one of these qubits. So we did a 96 nanosecond readout, and we got an assignment fidelity of 99.7% and a QND fidelity of 99.2%, with a quantum efficiency of about 30%. And so this sits around here, this work. So it's not the best assignment error, but it's very close. And this is in a 3D integrated architecture. Okay, then so the readout crosstalk we measured to be less than 40 dB. Okay, and then so very briefly then, we think we can try and improve this readout further. So we're now making a device where we're targeting quite an aggressive readout parameter. So an external coupling of greater of around 100 megahertz actually. So the filter should have a coupling to the line of 100 megahertz, and it should be robust. This kind of design to detunings between the filter and the readout resonator. Okay, so yeah, to summarize, we've been developing this 3D integrated packaging and wiring architecture with vertical wiring and spring-loaded probes. And we've measured, nearest neighbor crosstalk less than 40 dB. And this has been demonstrated at a 64 qubit scale. And then, using this 3D wiring architecture, we've now demonstrated a fast, high fidelity readout of qubits. And we think that we can make this readout even faster. So with that, I would like to thank you all very much for your time. So there are many people working in our group, but in particular, I'd like to thank Shuhei Tamate, Yusuke Abe, Yutaka Tabuchi, and Yasunobu Nakamura. And thank you all very much for your time.
Okay, so thank you very much, Dr. Spring. So now we have time for some questions. So, I mean, please ask your questions directly. I think that, so just unmute yourself and ask your questions.
Okay, let me ask a couple of short questions. One is that the qubit frequency distribution that we showed, most of them, about 49 of 63, are around 6 gigahertz or 6 megahertz. That was the omega Rabi frequency. But there are lots of qubits in the very low frequency regime. Was that intended or just unintended?
Sorry, I'll just find the slide. Because I just want to make sure I understand.
The next earlier one.
Earlier one, okay.
The histogram distribution that showed.
Oh, this slide here.
This one, right? Okay,
yeah. So this isn't the frequency of the qubits. This is the frequency of Rabi oscillations that we can drive in the qubits.
Was this intended or unintended? Like the 13 out of 6, which is the very low Rabi frequency.
Yeah, this was unintended. So we are still investigating why this is. So we would like this histogram to just have one bar. So all of the qubits are driven with the same Rabi frequency for the same drive power. But what we think is happening, I mean, there are a few possible things that could be happening, but we think that somehow some of the probes, so about 20%, are more weakly coupled to qubits. And this could be because maybe some of the pins are the springs are not providing a good enough force to give contact properly to the backside of the circuit. It could also be that there's actually a kind of lateral misalignment of some of the pins, so that they're not properly contacting the right location on the backside. And then another possibility is that it's not actually to do with the contact between the probe and the circuit, but actually maybe the probe is not well connected to the coaxial cable that's feeding the signal in. So maybe if there's a large impedance mismatch there, we could be sending a weaker signal onto qubits. So it's not. This isn't intended, and it's something that we would like to fix.
And one of them, I say, that's a very high Rabi frequency.
Yeah, this one we are scratching our heads about. We don't have a good answer for that. I mean, maybe the most prosaic answer is that there was actually just a mistake calibrating the power when we drove that qubit. It seems very odd that one of the qubits would be much more strongly coupled. I Okay, one possibility actually is that I said that we're using these inductive spokes to control the coupling. So if some of those spokes were disconnected on one qubit, for instance, if the circuit got scratched a little bit, that could increase the coupling a lot. So that could explain what's happening on that measurement.
Okay, thank you. I had the second question is that your laser annealing of the junctions, and I see that you get a better, narrower standard deviation, which is good, but I also see that the resistance is increasing. Is that desirable?
Yes. So, as far as I'm aware, whenever people are laser annealing junctions, it's always to increase the resistance. So, I don't think the process is well understood, but when you heat up a Josephson junction, yeah, the something about the chemistry within inside the oxide layer, it changes and the resistance increases. And I'm pretty sure that you can't, or I don't know of ways to reduce the resistance using the laser annealing process. So yeah, the strategy is normally to deliberately target a lower resistance than what you want during your fabrication, and then you get this quite large spread, and then you anneal your junctions and increase the resistance to your target frequency, and then you should be able to achieve your target with a smaller standard deviation.
But won't it increase the dissipation if you get the higher resistance?
No, so this is the room temperature resistance of the junctions. It just corresponds to the critical current of the junction when it is cooled down in the superconducting state. So it's not related to the dissipation.
Okay, thank you.
Okay, so any other question?
Sir, if I may.
Yes, please.
So, Dr. Spring, I would like to know what is your challenge list when you would try to scale your quantum circuit design from, say, 4 qubit to 16 qubit to 100 qubit. What would your list be that these are the challenges from science perspective or from technology perspective?
That's a good question. So there's many answers. From a hardware perspective, yeah, I think just having a very robust fabrication process so that you can have a low failure rate in your devices. So have all of your junctions working and not shorted and open. That's one challenge, and to achieve very high accuracy of your qubit frequencies. So as circuits get larger, frequency collisions become a real problem across the chip. So you need to have really accurate control over qubit frequencies. And yeah, I'd say that you just need all parts of your hardware to have a low failure rate. So if something works well at a 4 qubit scale, it might not work well at, as you go to 16 or 100 or 500 qubits. Because, for instance, with these control pins, as an example, even if it works 80% of the time, if you have a device with hundreds of qubits, then that's not really good enough. So making sure that all parts of your hardware stack are very robust is really challenging. And then there's also the obvious problems of just high quality qubits. So as well, you want to make sure that all of your qubits have high coherence times. We often have problems where you'll have sort of dropout qubits. So even if the average coherence time is sort of 50 or 100 microseconds, we might find that we have 1 or 2 qubits that have only got 1 microsecond coherence, and that can affect the performance of the overall chip. So yeah, on the hardware side, I think that just having a very robust processes and robust packaging and wiring is one of the biggest challenges for scaling up.
Thank you.
Okay, so I think we've time for
Hello.
at least one more question.
Hello,
Yeah, this is Vijay from TIFR. Hi, thanks for the nice talk. I also had a technical question about your laser annealing process. So one thing you showed us that while you're able to push the qubit frequencies all closer, I guess the requisite resistances, you observed increased aging after the laser annealing process, which shifted all the frequencies. This seems slightly counterintuitive to some other works related to this I have seen, where in some sense a naive way of thinking about the laser annealing is that it's some kind of controlled or accelerated aging, and usually once the devices reach their final aging, they tend to stabilize more. Is this something you have seen consistently across many devices, or this is just still very small statistics at this stage?
No, I think this is something we've seen consistently. Yeah, I completely agree with what you said. It's very strange. So this has been done largely by collaborators at Fujitsu, but they have done this on enough chips to I think have good statistics. And unless I've misunderstood, yeah, as far as I'm aware, they've also done tests where they'll deliberately let the device just age for a week or two after fabrication, and they'll observe the aging saturating, and then they'll do the laser annealing, and it sort of seems to reboot the aging process. So then after the laser annealing, they see aging starting again. I don't know why we're seeing this. It might be about the particular temperatures we're using for the annealing, but I mean that seems very that's too vague. So I agree with you that it's very strange, but I think we have seen it enough to have good statistics that in our devices it is happening, that the aging seems to kind of reboot after the annealing.
Okay, thank you.
Thanks.
Okay, so
Hi, Peter Spring. Hello. Am I audible? Hello.
Yes, please. Yeah. Okay, please go on.
Yeah, I'm Praveen Kumar, scientist, BRC. I have a technical question regarding indium bomb bonding. So I wanted to know what is the thickness of the indium bomb bonding you are using. Whether fluorine gas cleaning is required during indium bomb bonding, and what are the steps you are taking to preserve the coherence time of the qubits during the or after the bonding process. And finally, actually, whether you are depositing indium on the aluminum directly or you are using any interfacial layer. That's all. Yeah.
Okay. Yeah. So about the cleaning steps, I actually don't know the details of the cleaning. But what I can answer is, okay, you can see this SEM image. The diameter is about 20 micrometers of the bonds, and yeah, the thickness is, I think, on the order of kind of 3 to 5 micrometers. Then we are not depositing any of our bump bonds onto aluminium. We are always depositing onto titanium nitride. I think the reason we're doing that is that I think there was some work quite some time ago where they were worried that they were seeing that indium contacting to aluminium can form a normal state alloy, which can then lead to losses. So for that reason, we're just being cautious, and we're always depositing the indium directly onto titanium nitride. In terms of seeing losses in the qubits, yeah, what I can say is that before using these bump bonding cover chips, we were just using sort of CNC machines enclosures as acting as kind of a lid that we were pushing down onto the devices without having bump bonds. And actually, when we moved to these indium bump bonded color chips, we saw that the coherence times didn't really change in devices. So I don't think it's causing. I don't think it's a significant loss channel for our qubits.
Thank you. Thank you.
Can I just make a quick comment, 30 seconds?
Yes, please. I think that will be the last comment or question.
Titanium nitride is actually a diffusion blocker. So it probably prevents alloying between aluminum and indium. I don't know whether that is in any way responsible for whatever effect we are talking about.
Oh, sorry.
Yeah, please continue. Yeah.
Yeah, I was going to say, I think that's kind of our thinking behind using this titanium nitride on the cover chip, is that we want to have some kind of layer that's separating the indium from the aluminium.
Okay, thank you.
Okay, so thank you very much, Dr. Spring, for a very nice and enlightening talk. And so we'll now move on to the next speaker, which is Professor Vijay Raghavan from TIFR. And so Professor Vijay Raghavan is at the Tata Institute for Fundamental Research in Mumbai. He leads the Quantum Measurement and Control Laboratory, and their aim is to tackle the fundamental challenges in building and controlling superconducting quantum systems. The title of his talk is Quantramon, a multimodal quantum circuit with an integrated qubit mode and a measurement cavity mode. Professor Vijay Raghavan, please.
Thank you. Thank you to the organizers for inviting me to this online conference. And thank you for the introduction. My name is Vijay. I'm an associate professor at the Tata Institute of Fundamental Research. And is my screen visible?
Yes, yes.
Okay, great. So I'll be telling you about some work which has been going on for some time now, and hopefully we are reaching close to concluding this part of work. This work is led by PhD student Kishore Salunke primarily, and of course these are the rest of the lab members and others who have been involved in the earlier stages of related work. And this is about a qubit circuit, which is really a two-mode circuit, and with both a qubit and a measurement cavity mode are present. Of course, this is very standard, as you have seen even in the previous talk. So I'll try to highlight what exactly is going on here and what are the interesting properties and what are we trying to look at. So the previous speaker had already given an introduction to superconducting qubits, but just for completeness, I will also briefly show a couple of slides. The most commonly used superconducting qubit is the trans-1 qubit, which can be just thought of as a nonlinear oscillator, which is created using Josephson junctions shunted in parallel with a capacitor to basically form LC oscillator circuits. These LC oscillators operate at microwave frequencies and at dilution-rich temperatures, so that thermal energy is sufficiently smaller than the minimum quanta, 1 quanta of energy in these oscillators. The Josephson junction provides the nonlinearity so that the levels in your weakly anharmonic oscillator are not equally spaced like they would be in a harmonic oscillator. And that allows you to isolate two of the lowest levels as your qubit, but it's truly a multi-level system, just like any generic quantum system would also be, but we choose the two lowest levels. The thing to keep in mind is that in the case of the transmon, the other levels are not too far off in frequency. Typically, the difference here between omega 01 and omega 12 would be of the order of 300 megahertz or so. So that is the anharmonicity. This is the price you pay for suppressing charge noise, which was mentioned by the previous speaker. But this compromise seems to work well. This anharmonicity is sufficient to do reasonably fast operations for both, interesting physics experiments, but also for quantum computing. And the presence of the higher levels can make their effect in various ways. Sometimes they just lead to renormalization of certain properties, but in other cases, they can also play both a positive or a negative effect depending on exactly what's going on. And here's a picture of a 3D transmon, which is, you can see it's quite big, almost millimeter scale. These circuits are visual, you can see them with your naked eye. And then what you're seeing here in the middle are these two Josephson junctions here in a loop forming a squid, which allows you to tune the inductance in situ if you would like to do that. And these two big squares here are the capacitor pads sort of in this planar geometry. We've also drawn a picture of the pendulum because the nature of the nonlinearity is the same as that of a pendulum. That is, the restoring force is proportional to the sign of the displacement. That's the same kind of physics you have for a Josephson junction, and that's what gives rise to this cosinusoidal potential. Okay, so the main topic here is connected to measurement and what goes on in a measurement. So in order to measure superconducting circuits, what you do is you take this nonlinear oscillator, which is the Josephson junction and a squid, and you couple it to a linear oscillator. And this is the famous circuit QED experiment where you're doing basically light matter interaction physics, but at the level of the circuits, which is why this name circuit QED was given. And this architecture also allows you to implement a very idealized measurement in these circuits. Typically, one analyzes this by comparing it to the cavity QED picture, where you have an atom interacting with an electromagnetic field confined inside a Fabry-Provok cavity. So here, of course, we're typically talking about optical frequencies and atoms. The same physics here is happening with nonlinear oscillators replacing your atom and linear oscillators replacing your Fabry-Provok cavity, but everything is happening at microwave frequencies. The simple version of the Hamiltonian here basically involves a two-level system approximation of your atom and a harmonic oscillator Hamiltonian for your cavity. And this simple capacitive coupling gives you this kind of exchange coupling or Rabi coupling, where essentially you kill one photon in one mode and create an excitation on the other, and vice versa. So this is the basic interaction. Of course, this Hamiltonian here sort of seems to suggest that these two modes are resonant so that they can exchange photons. But for measurement, the qubits and the cavity resonant frequency are actually kept off resonant. And that's because we actually don't want the qubits to exchange photons with the cavity, because we would like the qubit to retain its information. But when you do that, which is now what's called the dispersive approximation, where the qubit and the cavity frequencies are detuned by this quantity delta, and if that delta is much greater than the coupling strength, that is the rate at which the two oscillators can exchange photons, which is controlled by this coupling capacitor here, then you get a modified version of the Hamiltonian shown here, which is called the Jaynes-Cumming Hamiltonian in the dispersive approximation. So now if you see what has happened is you have your qubit two-level approximation term has been maintained, but now the cavity term and the interaction terms have been combined into one effective term, where the qubit, the cavity frequency omega r, which is the coefficient of this a dagger a plus 1/2 term, has a qubit state dependent term shown here. And this chi is proportional to this detuning and the coupling strength. It's not exactly equal to this when you have a transmon. And this now suggests a way of measuring the state of the qubit. That is, the cavity state frequency now depends on the state of the qubit. And this allows you to make a measurement. In fact, this is how you make a measurement. And here's a sort of a cartoon representing these resonance measurements, where you scatter microwaves of this cavity, which is now coupled to the environment with some rate kappa. And typically, you measure these systems in reflection, but it can also be done in transmission. But the point here is that, ideally speaking, there are no dissipative elements on the left side of this circuit. So any microwave you send in steady state, all the power comes back. So the information is encoded in the phase and not in the amplitude. So you get resonance curves, two different ones for the ground and the excited state of the qubit. And typically you will bias yourself at somewhere in the middle and detect a phase shift. And it's this phase shift which you infer as the quantum state. So for one quantum state 0, you will get a different phase shift from quantum state 1. And then everything else depends on how good the signal to noise ratio of your setup is. So on the right side here, sort of examples that if you're operating here, you're trying to detect these two phases. And of course, to detect a phase, you have to integrate for a certain amount of time with a certain amount of power. And that gives you some distribution of the phase values depending on how good the signal to noise ratio is. And the ability to separate these two different distributions sort of tells you how good a measurement you can actually implement using this method. So this is sort of the most basic things, and you saw some numbers for readout fidelity in the previous talk as well. And this has been going on for quite some time, but there are still some challenges on measuring these numbers. And as you want to go to a larger number of qubits in a processor and want to implement things like quantum error correction and accurate calculations, the readout fidelity, that is how accurately you can discriminate the quantum states on measurement, is also very, very critical. And one has to push these numbers to as high a value as possible. Particularly when you want to implement error correction, you have to do this fast, you have to do this accurately so that you can correct the state based on the results of your measurements. So one typical challenge is that when you look at these this technique, it seems like if you now start thinking about, well, what is going to determine how good an SNR I'm going to get? Well, this is just a simple problem of determining two different phases on a microwave signal. So it basically depends on how strong the microwave signal is, because the same phase shift on a larger signal is a larger signal. And then it depends on how noisy your measurement chain is. And this is one of the reasons why people use ultra-low noise amplifiers for these kind of measurement techniques. But you can also, naively speaking, think that, well, I don't seem to have any limitation on how much power I send to this system. And the higher the power, the more signal I get. So I should be able to get arbitrarily large signal to noise ratio. Now, it turns out that this doesn't happen because this Hamiltonian is really an approximation. So when you start putting a lot of power into the system, you actually start to affect the qubit state. And if it's a transmon, it can actually not only mix between your 0 and 1 states, it can even go to the higher states, and then you have a problem. So you're trying to improve signal to noise ratio, but your state itself is getting changed during the course of the measurement, and that can actually prevent you from accurately determining. So this has again been studied for quite some time. In various scenarios, people have looked at these effects. So we were looking at it in a slightly different version of this device, and that's what I'm going to tell you in the rest of the talk. So this circuit QED geometry can be implemented in different ways. Here is an example in 3D circuit QED, where you have a three-dimensional waveguide cavity, which serves the role of the readout resonator. And then you put your chip somewhere in the middle where it interacts with the electromagnetic field to give you this effective circuit. Or as you saw in the previous talk, you can do everything on chip. You can have these transmission line based resonators on chip, also integrated with these Purcell filters if you would like to implement this thing. So physics wise, they are identical, just different approaches of building. Of course, if you want to make a quantum computer, the 2D approach is the one which is scalable. The 3D approach is good for studying some basic physics, and it's also modular and easy to use. So a lot of our work has focused on 3D circuit QED geometry as well. Okay, so I'm now going to slightly change the circuit here to motivate where actually we arrived at this circuit, which is the main topic of this talk. So in the early days, when we started work in our group about 10 years ago, we were looking at these multimodal circuits. So these are more complicated combinations of Josephson junctions and capacitors in order to give rise to more modes of oscillation. So, right, a simple single LC circuit has one mode of oscillation, but a more complicated circuit like this, with 4 junctions and many other capacitors, and here you see the 3D implementation of that device, you have several normal modes. And in particular, we studied this circuit called the trimon, which has 3 normal modes of oscillation. And each of these 3 normal modes gives rise to a qubit mode. There are 3 anharmonic oscillators. And because they are always part of the same circuit, they're actually constantly coupled to each other. So really, you have to think about this as a coupled 3-qubit system. And that can also be interpreted as an 8-level Hilbert space. But the structure of this Hamiltonian allowed you to have universal control over this 8-level Hilbert space or a 3-qubit Hilbert space with some interesting properties which allowed us to do certain gates, especially higher dimensional gates, a lot more simply, which is basically these 3-qubit gates in the Toffoli class. And they were actually the most natural gates to do here. So it's kind of counterintuitive. Typically, single qubit gates are easier and natural. And as you go to higher dimensional gates, you have to do many more operations. Here, it's kind of the opposite. Then the most natural gate here is actually interpreted as a 3-qubit gate. And then there are other things you can do. And we studied this over course of several years and showed that there are some cases where such an architecture can have advantages. But one of the things this evolved into, so this particular circuit has 3 modes. So what are these 3 modes here? If you look at the 4-junction Josephson circuit, which actually was originally considered in this work back in 2010 for making amplifiers by using these different modes of oscillations and pumping them to couple these different modes to create amplification. Here we're using them just as nonlinear modes, which are already coupled to each other because of the circuit topology. But if you look at the modes, it's the same structure. You have these 4 junctions, and there's one dipolar mode where this terminal is going to oscillate with respect to this terminal. And, assuming a perfectly symmetric case, these other 2 terminals on the side sort of remain at 0 potential. So you have like an oscillating mode. So you just think of this as an effective inductor, which is between these 2 terminals here. That is one of the dipolar modes. The other dipolar mode is exactly the same kind of thing, but now 90 degrees rotated. So you now have an oscillation from this to this, and while these 2 sort of remain at 0 potential. And this is also a dipolar mode because there's a plus and a minus. And you can have a quadrupolar mode where now these 2 opposite terminals are at a single potential and oscillating with respect to the other 2 terminals here. And this is the 3rd normal mode. So this basically gives you a way to visualize what these normal modes are. And by choosing the right circuit parameters, you can make the normal modes have different frequencies. And so you can use them for 3 different qubits, right? So, this can be done by choosing the right normal mode coordinates and then writing down the Hamiltonian. And when you do that, when you write down the Hamiltonian in terms of these new mode variables, which are these normal modes, you get your standard transmon Hamiltonian written in this sort of with this 4th order nonlinear term. And that's for mode A. Similarly, you get the same thing for mode B and mode C. And then you have this coupling term, which is proportional to phi A square and phi B square. So you see that these are also 4th order nonlinear terms like your phi A4. But this phi A4 is often called a self-Kerr term in a nonlinear system. And these are cross-Kerr terms because they involve 2 different modes. So you see that there is this pairwise cross-Kerr mode coupling between all the 3 modes of the circuit. And this is what is important for the main circuit in this talk. Okay, so this is the circuit now we are interested in. Now, if you look at it, it kind of looks different, but I'll convince you that this is actually just like a variation of the circuit in the previous case. So now you see that there are these 2 junctions, and now we have a linear inductor and a capacitor. And this part in red is sort of the readout cavity, right? It's a linear oscillator, but it's coupled in a different way to the other junctions, which is now forming the qubit. So if you think about this mode structure earlier, I presented this dipolar mode has now become the linear cavity mode because we have shunted it with a linear inductor. And that linear inductance now actually dominates this mode, and these nonlinear inductors are only a perturbative effect on that. So this has now become the linear cavity mode. And this other orthogonal dipolar mode, which is this point with respect to some virtual point here in the middle, that has become the qubit mode. And because in that qubit mode, you can see that these 2 points are at the same potential, so you can consider these 2 points to be sort of shorted together. And then you just have 2 Josephson junctions coupled, shunted by these capacitance, so which is the qubit. So by choosing the Josephson energies of these junctions and the inductive energy of these capacitors and inductors and the capacitor, you can get the frequencies in the right place, which means that the qubit is sort of at the qubit frequency and the readout is at the readout frequency, right? So this, you see how the mode structure from the previous circuit translates to the mode structure here. It's basically the same circuit now with slightly different parameters. But what is different about this circuit? That the cross-Kerr coupling, which we saw earlier, is going to be the same. It's the same type of coupling between these 2 modes. And this cross-Kerr coupling actually comes out more naturally from this circuit as opposed to doing a dispersive approximation. So remember that it's this cross-Kerr coupling which gives rise to the term which gives you the dispersive shift. Here, the same term is originated. So finally, the Hamiltonian looks the same. It's just that how you arrived at that Hamiltonian is different, right? So if you now solve this again using these mode variables, you get your transmon-like qubit, you get your harmonic oscillator with a very weak nonlinear term. Now, this is now no longer plays a role in terms of providing any nonlinearity. And you get your coupling term, which is again of the type phi q square and phi r square. And now when you write it down in your sigma z notation for the qubit and photon number of ladder operators for your cavity, you come and you see that you get the same term, which is a dagger a into sigma z. And now the cross-Kerr term, which earlier we were calling chi as dispersive shift, emerges as a term here. Okay. And a similar circuit was studied, and some very nice results were published from this group at Grenoble, and where they had arrived at this from a different angle, but they also had a cavity mode which was coupling strongly to one of these qubit modes, as opposed to just only having the cavity mode here. Okay. And if you actually even go back more than 20 years ago, there is a version of this circuit where this orthogonality between these modes of the readout and the qubit was actually used in this device called the contronium. In fact, my PhD work was on that circuit. But there, the qubits were in the charging regime, whereas here, the qubit is in the transmon regime. And this was what motivated us to call this device the contromon, as an ode to the contronium, which was sort of one of the first coherent qubits, which evolved after Nakamura showed his charged qubit experiments in 1999, and the contronium showed good coherence at the sweet spot in the 2000 and 2001. So that's the origin of this name, contromon. It's the transmon version of the contronium, but it has some of this, shares some of the same properties here. So just to summarize this, here's your contromon circuit, and here is the standard circuit QED Jaynes-Cummins circuit I showed earlier, where the qubit is coupled to the cavity. And here, the starting point of the Hamiltonian is slightly different. Here you have your sort of E dot D dipolar term coupling to the electromagnetic field of the cavity. And then after doing the dispersive approximation, you get the final readout term. But for the case of the contromon, it's sort of a more direct. And this paper from Grenoble Group also noted that this more direct version, that you're not really working with an approximate Hamiltonian, may play a role in how this Hamiltonian handles photons in the cavity. And that's sort of what motivated us to also study the circuit, to see indeed if it works differently and if there are anything interesting going on there. Okay, so how does this device look like? As I mentioned, we work in the 3D circuit QED geometry. where we, in this case, it's sort of a hybrid between 3D and 2D, if you would like. So you see here sort of a cartoon image of what the device looks like, and here's the circuit. It's made slightly differently, where this inductor is actually split into multiple components. You can see this meander inductor here. This is the shunting capacitor to form the readout resonator part. And the qubit junctions are here, which you cannot see. And these big pads here are the 3D capacitor pads, which provide both the capacitance for the qubit, but also the coupling to now not the resonator, because the resonator is directly coupled right here, but actually to a waveguide cavity. So here's a zoom in of what this looks like. The reason this inductor is split into 3 different parts is to control the qubit and the cavity coupling, like how much effect of dispersive shift or that cross curve term you get, that is controlled by how much of the inductance is shunted by the qubit. So this is something you have control in your design, and you choose that. So this is sort of what it looks like in circuit form. Okay, so by controlling the ratios of L1 and L2, we can control the cross-curve coupling between the qubit mode and the cavity mode. And this entire device, so here is now some optical images, SEM images of these devices. And you can see all the different meander inductors. The Josephson junctions are right here. And this device is actually now placed inside a 3D waveguide. So this is where the 3D part of the thing comes in here. And the qubit, of course, is 3D because it has these big capacitors as opposed to small compact capacitors. And we have a low loss aluminum side on the top and a copper on the other side, so that we can apply a magnetic flux from the outside to tune the flux through this loop here. So remember, right in the middle, you have a superconducting loop formed out of the Josephson junctions and the linear inductor, a part of the linear inductor of the cavity. Okay, and here is the copper part, and you see what we do is that we place these chips here. Now you can see these silicon chips with these antennas, which is the qubit capacitor, and they are placed in the middle where the waveguide mode has the highest amplitude. And we can actually tune the coupling also between the cavity and the waveguide, that sort of controls the kappa, or the rate at which the environmental coupling is done, by changing the position of this as well. So this allows us some tunability, not in situ, but at least we can choose and change it if we would like from experiment to experiment. Okay, so typical numbers for these things are the cavity frequencies, usually around 7.4 to 7.5 gigahertz. We work in the early experiments mostly with somewhat low kappas of around 1 to 2 megahertz. Qubit frequencies are typically around 4 to 5 gigahertz, and harmonicities in the transmon regime around 200 to 250 megahertz. And in the early days, we were having T1s of the order of 30 microseconds or so. This is in all aluminum devices. Okay, so in one of the earliest devices, we noticed it, and in fact, this is sort of, this experiment is what motivated us to look at this more carefully. We were just looking at this device just from to study this intrinsic multimodal nature, and we noticed something which happened accidentally, because in that particular experimental run, our ultra-low noise parametric amplifier was not working properly. So anyway, we're looking at this measurements. So this is a standard protocol. You do heralding to initialize the state, which is basically you do a measurement and then you throw out all the results where the qubit state ends up in 1, so that you can prepare a pure 0 state. And then you wait for some time for the cavity to empty out, and then you either do no pi pulse or a pi pulse to look at the ground and the excited state difference, and you make these histograms. And we were very surprised that we got very high measurement fidelity. This is not anything typical record. We saw 99% and higher in the previous talk. But at that time, we were quite surprised that without any parametric amplifier, we're getting close to 98% fidelity. And in fact, if we only looked at the histogram separation and what we call as sort of the intrinsic SNR fidelity, it was quite high. So we were a little bit surprised by this, pleasantly, that we are able to get these high fidelity, which directly seems to indicate that even though the noise of the system is high, because we are not using these ultra noise parametric amplifiers, the only other reason this would work is that we are able to work at fairly large number of photons, and that doesn't seem to be affecting the qubits, not too detrimentally. So clearly here the limitation is still, as you can see, that the ground state data has some excited state bump and an excited state data has some ground state bump over here, which is what the qubit state mixing, which can happen due to T1, but it can also happen when you put in photons and additional process take over. So, we got very excited. We decided to remeasure it with including the parametric amplifier, and we thought, okay, we will now get very high fidelity. And, we did, but it only improved marginally to about 98.8%. But you can now see that the number of photons was about half where we got the best result, and the integration time was also less than half of the previous case. And this basically motivated us to look at this device in more detail. And, this results of using high photon numbers without the use of parametric amplifiers is now being studied in many groups. Here's a paper from Ian Pop's group, looking at it in fluxonium devices, which is very different from transmon, but they also tend to suffer from the same kind of issues at high photon numbers. And of course, the previous paper I mentioned from the Grenoble group. So if I now want to look at these two devices, what other differences do I have, right? So there is one very interesting thing which was actually highlighted back in the 2002 Contronium work as well, that this inherent orthogonality of these modes, the fact that these are two different normal modes of the system, actually protects the qubit from the environment. So in the case of the standard circuit QED, the readout is coupled to the environment, and it sort of acts like a filter to protect the qubit. But that filtering effect only goes as, the detuning between the qubit and the cavity and the coupling strength inversely. Here, if this circuit was ideal, in the sense that if these two junctions were identical and these two capacitors were identical, the two modes are actually not interacting with each other in this particular way. So any dissipation on the cavity mode cannot affect the qubit mode because of the symmetry of the circuit. So it has, in some sense, an inherent Purcell filter, but it's not a filter, it's a protection due to symmetry, which is protecting it, but yet there is coupling between the qubit and the cavity. So this is sort of the main point here, right? And consequently, the dispersive shift, which is basically how much the cavity shifts in its frequency, depending on the state of the qubit, because that is also directly proportional to the amount of signal you can get from the system, again depends on the detuning and the coupling strengths in the same, in this kind of way. So if you move the qubit frequency away from the cavity, the signal gets weaker. Here, the detuning dependence is actually extremely weak. There is really no connection between the frequency of the cavity and the frequency of the qubit when you start talking about how much signal you're going to get in terms of this cross-curve shift. That can be somewhat independently computed. So this also offers you the flexibility of choosing the qubit and the cavity frequencies quite differently. They don't have to be close to each other, which is typically the case for the standard circuit QED circuit. And that is also the reason why one has to introduce these Purcell filters, which have been introduced in the previous talk, where you're introducing additional modes to kill the coupling of the qubit to the environment so that you don't suffer from the Purcell decay through the measurement line. Here, that protection is more intrinsic. You can also change the qubit cavity detuning according to your requirement. And maybe there are better optimal conditions to operate the circuit. So these were like two interesting properties. So we did some experiments to look at that. So for that, we made a tunable quantum design where instead of these two junctions, we changed them into squids. So we could actually tune the Josephson energy of these junctions inside the experiment so that we could change the qubit frequency while maintaining the cavity frequency more or less the same. And the way it works is that there are these two loops now. There is this main big loop, which is this loop here. And that, for the Quantrummon's operating condition, always has to be at integer flux quanta. But as we go from one integer flux quanta to the next, you can actually tune the EJs of the small junctions. So that changes the qubit properties. Okay. So here's some experimental data where we looked at the resonator frequency and the qubit frequency as a function of flux quantum. And you can see that the qubit frequency in red detunes from, tunes from about 7 gigahertz or so and comes down to about 4 gigahertz over 6 flux quanta, whereas the cavity frequency is more or less same on this thing. Of course, there's a small variation, but on this scale, it looks constant. So this basically allows us to change the qubit cavity detuning. And then for each of these operating points, we measured how much is the dispersive shift. That is, how strongly does the qubit affect the cavity in terms of its frequency. And that data is shown here in red. The blue data here is the same resonator qubit detuning, now plotted in terms of detuning. So you can see that the blue curve changes by almost 3.5 gigahertz over this range, whereas the dispersive shift only changes by about 1.5 megahertz or so. So between 3 and 1.5. Of course, it's a factor of 2, but it's a small number. So the dispersive shift is barely changing. Then this is what I had indicated in the previous slides, that the dependence of the signal on the detuning is quite small. And by actually, you can even, if you wanted to design something with a much larger dispersive, much larger detuning, you can change the coupling by changing those inductor ratios. So this sort of shows that this property is being manifested as predicted in this experiment. And as I said, for the transmon, this dispersive shift goes as G square over delta. Right. The other thing we're also looking at is to look at how this symmetry protects the qubit as well. So the role of asymmetry, right? So as I mentioned earlier, the dissipation from the radar port is decoupled from the qubit if there is no asymmetry in this junction. So this is important. Now, in reality, any device, I cannot make these two Josephson junctions identical. These capacitors can be reasonably identical, but the Josephson junctions will always have a few percent variation. As we saw also from the previous talk, that there are always fabrication-related variations, right? So we did some estimates of what would happen if we could tune one of the junctions and change the asymmetry in situ. So instead of now both junctions being tunable, we made one of the junctions tunable. So again, you go from one flux quantum to the next flux quantum in the big loop, and then you have some discrete changes on that. And what we estimated is that for a typical set of parameters, the cross-Kerr coupling, because that is the signal we are interested in, doesn't change that much. But the transverse coupling, which is now the same type of coupling that the standard circuit QED has, which is this exchange coupling, actually can increase and change. And at one optimal point where the symmetry is as close to, the asymmetry is as close to 0, that transverse coupling goes to 0. And this sort of starts to hint at the things we are trying to look at, is that in a real device, is it the remaining transverse coupling, which is the standard coupling which is present in the circuit QED circuit, does that have a role to play in deciding whether a large number of photons can be put into the cavity or not? So this was the motivation of making the device like this. And so we made one device and measured the asymmetry as the function of flux points. And then you can see that at some particular flux point close to, in this case, second flux quantum, the asymmetry comes very close to 0. And that would give rise to change in cross-Kerr and dipolar coupling of this type. So this would allow us to tune the asymmetry inside and actually try and study this effect, whether we can see whether the asymmetry which gives rise to the dipolar coupling has a role to play in deciding whether how much photons one can put that. And that also have the effect on both Purcell, because the Purcell effect will also be affected by this asymmetry, and whether it is going to have an effect on the radar quality. So at this point, we had looked at a few devices, but we were not really getting very, I would say, very precise results. Qualitatively, things were happening, but quantitatively, we were not able to get much going. And this, we basically realized that this effect we are trying to study, this improvement in readout fidelity by suppressing these bad terms, is actually a very small effect. People already get 97, 98, 99% fidelity. And we are trying to see if that can go up. So it's a very small effect. And what we realized is that our aluminum devices had quite a variable coherence, and they were not that great, around 20 to 30 microseconds. Particularly during the time when we first started these experiments, we were having a period of poor coherence in the lab, and these numbers were poor. And what we noticed that it made it very difficult to isolate the effect we are trying to study from other effects which also affect the readout, which is the coherence itself, and also if there are two-level systems in your environment. And that made it very difficult to get a systematic result here. So more recently, we started looking at making qubits with tantalum capacitors, as I'm sure many of you know that a few years back, this was first demonstrated in the Princeton group, that by using tantalum for the capacitor pads instead of aluminum, significant improvement in coherence was achieved. And so we started to look at this just as something to have an additional toolkit in the lab's capabilities. And this work was led by PhD student Srijita Das. And then when we were able to make transmon devices using the tantalum process, we did see an improvement in coherence and also a lot more stability. We decided to try the same process for making this quantromon as well. And that now allowed us to improve our coherence by about a factor of 2, though we have measured devices with even better coherence. But more importantly, we also saw a significant improvement in our echo times, which typically used to be similar to T1, but in this case, they started approaching 2T1, and we started getting devices routinely in the 50 to 60 microsecond regime, and echo times nearly double that. So we were we're excited about this development. We started looking at some devices. So I'll show you some very preliminary results on this tantalum quantromon, but we have measured many more devices, but we're still analyzing the data. So here's a sort of a summary of some data we have. So this is now measuring the fidelity, the maximum readout fidelity we're getting as a function of drive amplitude. So this means more and more stronger drive. And by operating this device, this is now made out of tantalum capacitors, but it has this tunable asymmetry, and seeing how the fidelity changes with the drive amplitude. And we see that there are some flux quanta where the drive amplitude continuously causes the fidelity to increase, and then it comes down at a much higher amplitude, whereas in other cases, it can come down at a lower amplitude. So this is now starting to indicate that the asymmetry is playing a role somehow. So we have to now, of course, quantitatively make it match, but we are already seeing this effect. And these are all now, again, 96, 97% readout fidelity. I think the best we got was around 98, all without any paramps being parametric amplifiers being used. And we're also looking at how these different phase shift states evolve as a function of time for different readout amplitudes. So these two blobs represent the ground state and the excited state. And as the integration time is increased for a particular readout amplitude, and then you see that as time progresses, the excited state sort of falls back to the ground state. And that is one of the processes which prevents or minimizes the readout fidelity. So this is for a slightly low power in the cavity. And then if I go to higher powers, then you start seeing more of these blobs. So each of these colors are when the qubit is initially prepared in the ground state, or initially prepared in the first excited state, or even initially prepared in the second excited state, because we start seeing multiple blobs, which tells you that the qubit state is also changing to the higher states of 2 and beyond. And this again is something seen by many groups, starting with the group of John Martinez many years ago, where they saw that at high powers, the qubit states can actually leave the computational subspace and go to higher states as well. And that affects the readout fidelity as well. So this is all fairly new data, and we're still crunching the numbers, but there's some indication that we have some effect which we are trying to look at.
Okay. Excuse me, Vijay.
Yeah.
Sorry to interrupt you. You have 5 more minutes.
Perfect. So I just wanted to quickly show one last thing, which we are also trying, and we have taken some initial data on. So here is the same quantromon circuit, but now we have made a small modification where we have replaced this linear inductor partially with a Josephson junction. So this now actually makes the readout mode cavity also nonlinear. And in fact, going back to my PhD days, this was actually what I did, was to use a nonlinear resonator as a way to do the measurement in the contronium circuit. So we decided to look at this now in this quantromon circuit, which is a transmon version of that, in the same thing. And the advantage or motivation here is that if you look at the nonlinear resonator response, which is shown here, this is a sort of a nonlinear cavity. So here is at low powers, you have a linear resonance, and then as you go to higher powers, this resonance starts to bend, gets sharper, and then you see this very sharp region. So this is the linear regime, which is where typically the standard circuit QED does. Now, if you go to slightly higher power, you can actually get parametric amplification in the nonlinear cavity itself. And then you can also go to the bistable regime, where the nonlinear resonator itself becomes bistable and has two modes you can use here. So we just started to explore this. And again, the goal is that if we are able to integrate the amplification in the device itself, it would make the overall circuit topology a lot simpler. You don't need separate amplifiers, and you can get good fidelity here. So we have just started looking at, we basically started to look at the histograms at low powers in the linear regime, at slightly higher powers in the param regime. We see some improvement, but it's very, very modest. And I think this device currently doesn't have the best coherence, or the device parameters are not optimized. But we are also able to go into the bistable regime, where now these histograms are very well separated, because these states latch, and you can actually integrate for a very long time. And the state will not change even as the qubit state changes, because the nonlinear oscillator state becomes locked. And this was one of the features also pointed out 20 years ago in the Josephson bifurcation amplifier. And but the fidelity is not good at all. It's 78%, which is very, very modest or poor, I would say. And I think the primary reason here is that the device parameters for the coupling and everything has to be optimized, so that we have to make sure that we're not going to too high a power in the nonlinear regime, so that the other effects start to kick in. But at the same time, it should not be too low that we are not able to see the nonlinear regime properly. Okay. So with that, I'll come to my conclusion and basically say that, we discussed this Contromon, which is a two-mode circuit with an inherent cross-curve coupling, and it has this potential of achieving high measurement fidelity even without the use of following low noise amplification stages. Key property is that it has a highly suppressed Purcell effect and also a dispersive shift independent of detuning. This can give an advantage in terms of making even large-scale circuits, because you can now design your cavities without worrying about the dispersive shift. Choose the cavity frequency. We use this tunable transmon to demonstrate this weak detuning dependence, and also the devices with tunable asymmetry, and we have seen some initial effect on the Purcell effect, but this is ongoing work, and we hope to finish it very soon. And then finally, I mentioned some initial work with the nonlinear cavity readout. So with that, I would like to thank all the group members, the students and the postdocs who have been doing this work. And I would also thank you for your attention. I'll take some questions.
Okay, thank you, Vijay, very much for a very clear and nice talk. So now we have time for some questions or comments.
I have questions, Vijay.
Yes, please.
Two-mode circuit JJ that you showed, are those squid structures or the single junctions?
Sorry, which circuit?
Two-mode circuits.
So this one?
Yeah, something like this. These are.
So it depends on what you call a squid. Let me actually go to this version here, which is probably more closer to the real circuit. Yeah, this one here. So see, the small junctions are individual junctions in the basic experiment. So they are not squids, but there is a superconducting loop, because this inductor is also a superconductor. And the value of flux inside this loop plays a role in the Hamiltonian of the circuit. And the normal operating point is that this loop has to be at integer flux quantum, otherwise you have some other effects. But later on, we changed this circuit for a different experiment, where we made these single junctions now into squids. So these single junctions were replaced by two junctions in a loop. And that gave, so here you can see that there is two junctions and there is a loop here. So now you have two different squids. So this is a squid, this is a squid. And then there's an overall loop as well. So what you do is you adjust the flux so that you're always at integer flux quantum in this big loop. And that will have a smaller flux in the smaller loops because the field is the same, the area is smaller, and that is what allows you to do the tuning. So there are squids in this circuit, but in the previous version, there are no squids.
Okay.
Yeah.
This second question is without JPA experiment that you mentioned.
Yeah.
Do you first check with high intensity, that means high photon number, and then look for this 2-photon transition and then gradually reduce the intensity?
No, so we basically do a sweep of the readout amplitude and the integration time, and then we sort of find the point where the fidelity is the best. And then we look at what is happening at that particular operating time in terms of where the states are, whether it looks like this or whether it looks like this. And then we try to find the best point. What we are really trying to do is to adjust the device parameters in such a way that this curve will keep going up and approach very high fidelity without coming back down. So this coming back down is the problem, and we are trying to understand what is affecting this and how we can push this, because the larger the signal we can put, we know the better the signal to noise ratio would be, provided we don't affect the qubit states. So we do a thorough study as a function of amplitude and integration time, and then find the best optimal point. And the same thing, if I can do this experiment with the parametric amplifier as well, and there the optimal might be at a different point, and that will tell us about the relative contribution of signal to noise ratio affecting the fidelity and qubit state mixing affecting the fidelity.
So here this 3-5 case is quite different. Is that what the third state is involved here?
Possibly out here at very large amplitudes when the fidelity start to come back out. This weird feature here, I think, is something related to a resonance in the circuit, which I think we had. So this behavior at lower powers at the beginning, this weird feature here is slightly atypical. But for us, the main point here is that the fidelity continues to remain high till a significantly higher amplitude for the red case, which is closer to the zero asymmetry point. Whereas as you are at these other flux quantums where the asymmetry is higher, you see that the fidelity starts to come down at a lower amplitude. So this is the signature what we were looking for. Now, of course, the best fidelity is actually better. I mean, the highest fidelity is better for these other points. It goes to a higher value and then comes back down, whereas this red one sort of remains slightly on the lower side but stays high. So this is all related to a combination of the different effects we are talking about. It could be related to TLSs or other things. So this is what we are trying to now understand and see if we can optimize the device so that we can keep making the fidelity go higher to much larger amplitudes and achieve very high fidelity without the parametric amplifiers.
Okay, thank you.
Any other question?
Hi, Vijay. Interesting talk. Just a short question before here.
Yeah, hi.
Yeah. So, question about your aluminum device with the single squid.
Yes.
So when you did the experiment at different 5 nodes, integers.
Yes.
You could tune the frequency nearly by 3 gigahertz or so.
Yes.
I was wondering if you have looked at some frequency-dependent dielectric losses, because this is pure aluminum device, so most likely they're there.
Yes. So this is something we have seen in other experiments as well, is that in general, our qubits become worse as you go to higher frequencies. So we typically see that after 5 gigahertz, the qubit coherence is usually quite low. Now, in this kind of an experiment, even in other circuit QD experiments, because our cavity is usually also at higher frequencies, so unless you do a very careful separation of the Purcell T1, it's difficult to pinpoint the dielectric losses, and we have not looked at it very systematically. But generally, we see that above 6 gigahertz frequency, we have not had much success in making very good quality qubits. The tantalum qubits have shown somewhat better performance in that regime, but they also tend to get worse at higher frequencies.
Okay.
Yeah.
Related question here about the architecture.
Yeah.
So in comparison to junction inductance, the
Yeah.
linear inductor that you put, are you operating in a like a hysteresis loop of the hysteretic limit of the, or like what is the larger number here, LJ or the linear inductor?
Oh, no. So the linear inductor here is, of course, much smaller in size compared to the inductance for the qubit junctions, because you see qubit junctions have much lower critical current and much higher inductance. So the loop inductance here is actually very small. So you're far from the hysteretic regime.
Yeah. Okay, thanks.
Yeah, and that is intentional, and also by design, that is the natural values of L you need, because you have flexibility in choosing L and C for the readout cavity up to you. So we chose small L, which is large EL, and then the capacitance is chosen accordingly to give the readout cavity frequency.
Yeah.
I have a question.
Yeah.
So regarding this tantalum, that is the alpha tantalum, right? The superconducting phase of tantalum. So does this coherence time and input time somewhat related directly to the transition, superconducting transition time of the material?
So let me see if I understand the question. You're asking that is the improved coherence of tantalum related to the fact that tantalum has a higher TC compared to aluminum? To the best of my understanding, that is not the reason. So if you look at the papers from the Princeton group and other groups who have done, they point out that there are two potential reasons. There is some evidence to support that as well. Is that it's related to actually the oxide on the surface of tantalum. So if you look at the general understanding of what is limiting qubit coherence in typical transmon devices, it turns out to be dielectric loss at the metal substrate interface and then metal air interface. These are the two dominant ones. And it seems like the aluminum oxide on aluminum is somehow a poorer dielectric than the tantalum oxide on tantalum. It also seems to grow thinner than aluminum oxide. And again, there are some subtle differences on whether your device is made using a lift-off process in the aluminum case, or whether it is etched aluminum with the Wilson junctions made later on. That can affect the metal substrate interface quality as well. So tantalum films, deposited on a pristine sapphire wafer may have a better metal substrate interface as well. It's these things. So the TC really doesn't play such a big role. It might have some indirect effects later on, but I think that is not really the reason, because there are other materials which have higher TC, but they don't give better coherence. So it's really got to do with the quality of the metal substrate and the metal air interfaces.
Okay.
Yeah, maybe Vibhor can add something to that.
Actually, I have the same understanding. I would have said.
Yeah.
Well, we have time for just one more question or comment. Okay, so if not, let me thank you once again, Vijay. So the first session ends now, and the second, we are right on time actually. So the second session will start after half an hour at 10:30 India time. Okay. So Snehal, do you want to say something? Or?
Yeah. So it's a half an hour break. So.
Okay. All right. So we'll come back after half an hour then.
Just come back at 10:30.
Yes, exactly.
Yeah, 10:30 India time. Yes.
Yeah.
Okay. Fine. Thank you. Thank you both. I'd like to thank both the speakers, and so we'll be back in half an hour. Right.
Vijay, you're going to be the chair for the next session.
So Vijay, are you there? Okay. Anyway, so I think he, maybe Snehal, you can call him and remind him something about that.
Yeah, sure.
Yeah, okay.
Because we are really to this focus people. Yeah, we did. It's we are. But the problem is we are very kind of similar in other conversations. Like in Bangalore, we call it B and B. There is clear differentiation microphones. But it's not that different.
ইউটিউবে কত পার্টিসিপেন্টস কিরকম ছিল? 20 জন। রেজিস্টার করেছে অনেকেই, কিন্তু
প্রচুর। আমার ধারণা ইউটিউবে যেহেতু লাইভ হচ্ছে ওটা স্টোর হয়ে থাকবে, লোকজন এখন দেখবে না,
পরে দেখবে। পরে দেখবে নাকি?
কিন্তু ওটা তো সেভ হয়ে থাকবে।
ওটা আমাদের ওয়েবসাইটে সেভ হয়ে থাকবে নাকি?
হ্যাঁ, মানে টিসিজি ক্রেস্টের ইউটিউব চ্যানেলে ওটা সময় থাকবে।
আচ্ছা,
বিজয়কে জানিয়ে দিচ্ছে, ও বলেছে যে তাই বিজয়।
আচ্ছা, ঠিক আছে। স্নেহাল একজন সায়ন চক্রবর্তী, তো ও একটা মেল পাঠিয়েছে, তোমাকে ফরওয়ার্ড করলাম, রেজিস্টার করেছে, বলছে জুম লিংক পাইনি। Hi, Vijay.
Hi.
You're already there. So you asked for this orders, copy of order. So I'll send you maybe tomorrow or day after.
Okay. Yeah.
We still have 1 minute or 1 or 2 minutes.
Yes.
Right. So you're
Oh, hello, Miyazaki-san. This is Bhanu Das.
Hi.
Hello, hello. So,
Hello.
okay, so you're the next speaker.
Yeah.
Okay, sorry, I should.
All right, so let's invite the chairperson of the next session is Professor Vijay Raghavan, and he has been already introduced, but he was the previous speaker. But people who just joined, for them, is Professor Vijay Raghavan leads the Quantum Measurement and Control Laboratory at Tata Institute of Fundamental Research, Mumbai, India. Professor Vijay Raghavan.
Thank you, Professor Bhupin. Good morning, everyone, and welcome to the second session. You can hear me, right?
Yes.
Okay. Yeah. Good morning, and welcome to the second session on Symposium on Quantum Computing with Superconducting Qubits at the Center for Quantum Engineering Research at the TCG CREST. The first speaker today is, in the second session, is Dr. Miyazaki, who's a researcher at System Platform Research Laboratories, NEC, Japan. He works on quantum annealing from a theoretical perspective, and the title of his talk is Quantum Annealing with Josephson Parametric. So over to you, Dr. Miyazaki.
Okay, I share my screen.
Sorry, on my end, the screen looks frozen. Okay.
Can you see that? Okay.
Okay, we see that now.
Okay. Okay. Thank you for kind introduction, and thank you very much for inviting me to this symposium. I'm Ryoji Miyazaki, working for NEC company. NEC Japan, and also I belong to the National Institute of Advanced Industrial Science and Technology, called IST. We NEC and IST are working or developing a quantum annealing machine. Later I will explain what quantum annealing is. Anyway, we are developing a computer based on the superconducting qubits. And this is a national project. We developed superconducting device in collaboration with IST, Tokyo Institute of Technology, and Yokohama National University and Waseda University, and so on. This project is supported by NATO. Anyway, this is the national project in Japan. This is the picture of just a mock-up of our quantum annealing machine. But anyway, we are developing the actual hardware in our lab. And the right-hand side, this picture shows this is the actual device that has an 8 qubits in this area, based on the superconducting parameter device. I will explain that. We are developing such a hardware, but I'm not an experimentalist. So I'm talking about only the theories related to this development of hardware. This is the outline of my talk. First, I will explain what quantum annealing is. I will give a brief introduction of quantum annealing. And after that, I explain our company and its approach to quantum annealing. That means that I will explain our theoretical scenario, which we rely on to build actual hardware for quantum annealing. And after that, I will address the theoretical study of this scenario, this approach that is done by me and some problem. Anyway, first, I'm talking about, kind of a quantum algorithm. But this is not, this is different from the gate-based quantum computation. That is the digital computation, but quantum annealing is an analog computation. And for quantum annealing, we prepare a trivial state of a quantum system as an initial state. And for example, we prepare a system as a state in a state where in an eigenstate, one of the eigenstate. For example, here, this figure shows the energy spectrum as a function of quantum effect, but the quantum effect is decreasing with going to the right-hand side. And for quantum annealing, we decrease the quantum effect gradually, and simultaneously we increase internal interaction, the interaction in the system, and the interaction encode the problem which we try to solve with this algorithm. And the resulting state of the system, that means that after decreasing the quantum effect and increasing interactions, the obtained state of the system corresponds to the solution of the problem we try to solve. In this protocol, the system system goes on this car and arrives at this state without quantum effect, where the system has no quantum fluctuations. So we can obtain trivial state. So we can obtain such a non-trivial solution, non-trivial state that corresponds to the solution of our encoded problem from a trivial initial state. And this is just a scenario. And I explained about the typical setup, where in a typical setup, we search for the ground state of async model. Why we focus on the async model can be in the both in academic and industrial community. So it is the it is our motivation to focus on the async model. And also async model is a very simple one, so it is a good stage to investigate the quantum. And for this setting, we prepare initial state. We prepare the system governed by this Hamiltonian HQ. That is a simple one. Has only the field, magnetic field in the async representation. The sigma x means that we set a computational basis as an z direction. I mean, the final classical spin system is described by the spin z component. So sigma x means that is a transverse field. The field transversing the product of the superposition of the spin up and down states for each spin. And this is an initial state. The transverse field is a quantum interaction in the system. The interaction is described by Jij. That is the coupling appeared in the classical Hamiltonian like this. This is the Hamiltonian for the Ising model. And J our problem to be solved. We can map the combinatorial by this decreasing the transfer field and increasing the interaction. And the ground state for this system is non-trivial. For example, this would be Okay. It will be something like the up. Once spin 1 takes up, spin 2 is down, spin 3 is down, so on. So we obtain the ground state, such a non-trivial ground state for this Hamiltonian, where we encode the problem. This is a scenario of the quantum annealing in a typical system. I think you may be interested in the theoretical basis of this algorithm, stop protocol, this procedure. That is the adiabatic theorem. The runtime of the quantum runtime much longer than this value guarantees the giving the correct solution. Correct solution means that, for example, we try to find the ground state of the thing model. We obtain the correct ground state if this condition is satisfied. Delta minimum is the minimum energy gap. For example, for the ground state search, the delta min is the minimum energy gap between the ground state and the first excited state in the whole passage of the quantum. So, for example, in this case, this difference is the delta min. So, if the runtime is much longer than delta min to -2, this quantum annealing gives the correct solution of the problem. And this algorithm, quantum annealing, has a correspondence to gate-based quantum computation. That means the adiabatic simulation of quantum circuit. This means the simulation of the gate-based quantum computation, quantum circuit with quantum annealing can be efficient. Can be efficient when the can simulate the gate-based quantum. In this meaning, the quantity, but such a and such ideal quantum annealing has not been physically realized so far. But anyway, the ideal quantum annealing is equivalent to gate-based quantum computation. Yeah, I say the ideal quantum annealing has not been realized, but anyway, not imperfect one has been already implemented in physical system. The D-Waves quantum annealing machine is such a physical implementation that has 5,000 flux qubits for the transverse field Ising model to realize the transverse field Ising model. And this hardware realizes a coherent quantum annealing. Coherent quantum annealing means pure quantum annealing that is not disturbed by noise. But such a coherent quantum annealing is realized only in a short time regime, very extremely short time regime. That is 10 nanoseconds or so. And I did not mention this point, minor embedding, but we need a minor embedding to encode programs in the physical qubit network. The physical qubit network has a specific graph structure. So we try to solve some problems with such a hardware. We translate our problem to the problem which can be represented in such a physical qubit network. So such a method of translation is called minor embedding. Anyway, we need such a translation to solve some problem with the actual hardware. Yeah, so far I talked about the general point.
Right. I just wanted to say that there are some audio issues, I think, from your end. Periodically, we can't hear anything for about 5 to 10 seconds, and then it comes back. Can you just check your network?
A network?
Yeah.
Uh-huh.
Because the audio keeps drop out.
Yes,
I mean,
it is same here. And even on YouTube.
Okay, just a moment. I change the network. I hope it works well. Is that okay? Does it work?
Yeah, right now it's fine. Maybe you can disable your video in case there is some bandwidth. We can see if that.
I should stop video.
Yeah.
Okay.
Yeah. Okay. Let's see now. Thanks.
Okay. Where should I resume?
No, this is fine. You can resume wherever you
Okay.
left off. It's just that it was happening again and again, so I thought it better to interrupt and check. Yeah.
Okay. Next, I'm talking about the NEC's approach. What I'm talked about was the general scenario of quantum annealing. But next, I'm talking about our company's approach to build a quantum annealing machine. But I'm not, as I said, I'm not an experimentalist. So I'm talking about only from a theoretical point of view. And if you are interested in engineering point of view, please see a talk by Aiko Yamaguchi. She is a member of experimental team in our company, in our group, at the Inca conference. That is the conference on the quantum annealing. The movie of our talk in this conference is available on YouTube. So if you are interested in engineering, please check this video. Anyway, I'm talking about the NC's approach from theoretical point of view. There are three points. One is theoretical model. The second one is qubit platform. The third one is the last one is encoding method. It may be helpful to show those points for D-Wave machine. For theoretical model, D-Wave reproduces the transphosphidizing model, and the qubit platform for D-Wave is RF squared or flux qubit. And the encoding method is, as I said, minor embedding. The method is called minor embedding in CQuERE or its descendants. CQuERE is the name of the graph structure of the physical qubit network in the D-Wave quantum machine. Anyway, we adopt a distinctly different theoretical model, platform, and encoding method from the D-Wave one. So I'm explaining them. First, I focus on the theoretical model, co-parametric oscillators. That is called KPO also, and that is nonlinear quantum oscillator with a parametrically driven field. This is a Hamiltonian of the KPO. Such an oscillator in quantum mechanics is described by bosonic operators. So I described the Hamiltonian with bosonic correction and annihilation operators, A, and A. And the first term is a standard harmonic oscillator term. But this KPO is a nonlinear quantum oscillator. So this has a nonlinear term that is called Carr nonlinearity. And also the K is called the Carr coefficient. And also this system has a parametrically driven field. This corresponds to this term, the third term, parametric driving. We also call it pump. And this is an oscillating field. And the frequency is denoted by omega p, and that satisfies the condition. Omega p over 2 is close to omega. Is the frequency of the harmonic oscillator term. And also we can add the coherent driving term. This is also called oscillating term, but the frequency is close to the harmonic oscillator. And this is a little complicated Hamiltonian. So we move to a frame rotating at omega p over 2. This is the important frequency. And then we ignore the rapidly oscillating terms, and then we deduce the we can obtain the effective simple Hamiltonian like this. The delta is a new parameter that represents the difference, frequency difference, omega minus omega p over 2 plus k. K is a Carr coefficient for the cardinal linearity. And there, the other three terms turns to these terms. We ignore the oscillating terms, so we obtain the stationary simple Hamiltonian. That is what we focus on after. But anyway, we know that KPO is what KPO is. But what we want to do is we utilize this KPO for quantum annealing. So a natural question is, how do we use KPOs for quantum annealing? So quantum annealing with KPO, we set the initial Hamiltonian like this. We set P equals 0. So the Hamiltonian, and now epsilon set to be 0. So then the initial Hamiltonian is like this, having only delta and K. And the ground state of this initial Hamiltonian is a vacuum state, where no photon, where the system has no photons, and the eigenvalue of the A is 0. And this figure shows the Wigner function of the state as a function of P, and this figure shows the initial Wigner function. The vacuum state is represented like this. And for quantum annealing, in this method, we increase P. For the transverse speed Ising model, the standard case, we decrease the transverse speed, but in this case, we increase P. And then the state is squeezed like this. And we increased P much larger than the delta. Then the ground state of the system is superposition of coherent states like this. Alpha 0 plus minus alpha 0, where alpha 0 is square root P over K. This is the so-called cat state, more specifically, even cat state. So an Ising spin, or the two-level system, is encoded in the two coherent states of the cat state, this one. For example, we encode the up state in this coherent state, and the down state is encoded in this coherent state. And then we generate the qubit or Ising spin, or two-level system. And when we add epsilon, coherent driving epsilon, the ground state becomes close to, if epsilon is positive, the ground state is close to plus alpha 0 like this. So the system selects one of the two coherent states according to the sign of the epsilon. So if epsilon is negative, the minus alpha 0 is selected. So epsilon coherent driving works a longitudinal field in the Ising Hamiltonian representation. Next, we consider the QA with interacting KPOs. This is Hamiltonian interacting KPOs. The Hamiltonian is composed of the sum of the Hamiltonian of each KPO and the interaction, linear coupling of KPOs, shown like this. KPO I and J is connected with a linear coupling denoted by Jij. And also we apply coherent driving to the two KPOs epsilon I and epsilon J like this. And if at one instance of the problem, if Jij is negative and epsilon I is positive, epsilon J is negative, the ground state would be the plus alpha 0 and minus alpha 0 for KPO I and J respectively. And then this is translated to the up spin and down spin for the Ising representation. And so this corresponds to the solution of this. This corresponds to the ground state of the Hamiltonian, and also this corresponds to the solution of the problem which we try to solve for example, the combinatorial optimization problems. This is the basic scenario of the quantum annealing with KPOs. Okay, we now understand how we use the KPO for quantum annealing. But next, what we want to do is to build a quantum annealing machine with such a method. So next is, how do we physically implement this method? So we next move to the qubit platform, that is just as a parametric consistency class. What is a JPO? You may know that is superconducting circuit. Schematic circuit of JPO is shown here. That is C shunt is separated by a modulated magnetic flux phi EX. The magnetic flux is generated by the AC current in this line. The frequency is omega p, and such a modulated magnetic flux leads to a parametric oscillation in the system in circuit. Hamiltonian is sorry, and this is an effective circuit of a JPO. We can describe the circuit like this. The circuit has a CJ and squid with two branches. The one branch has an effective Josephson junction with an effective Josephson EJ sigma, and the other branch has an effective Josephson that is oscillating with frequency omega p. And then the Hamiltonian of this circuit is represented by this. This has a 2 degrees of freedom, Q and phi. Phi is a superconducting phase across squid. And this is a classical description of the Hamiltonian. So we next quantize this Hamiltonian with the Bosniak representation like this. And then, of course, we move to the rotating frame at omega p over 2. And then we obtain this quantum version of Hamiltonian after some calculations, where EC is a charging energy and omega is a frequency, described like this. And note that the ground state in the null frame corresponds to the highest energy state in the rotating frame. So I set minus here. So minus HJPO, so for minus HJPO, the ground state of this minus HJPO corresponds to the ground state in the null frame. And you may find that this is the same form of KPO. So we can generate the KPO by using JPO. And we NEC and collaborators physically implemented this KPO. This is the schematics of their circuit in experiment. And this is one of the main results. The horizontal axis shows the F. I did not mention the F. F is a flux bias. In the actual circuit, in the experiment, has a flux, has a linear inductance, and then there's some physical value depends on the flux bias. But anyway, in the region where the flux bias is large, the Kerr coefficient K is much larger than the kappa total, the total photon rate. So this result showed that larger K than the photon loss rate is obtained, and that indicates the quantum regime of the KPO. We generated the quantum version of a KPO, described like this. And next, we consider the coupling of two JPOs. We assume the coupling is done by capacitive one, and the two JPOs have the same pump frequency, omega p1 called omega p2. If this condition is not satisfied, rapid oscillations hinder the coupling. So we set this condition. But this is a condition for frequency, that there are constant part of the phase. So we set the relative path phase theta p to tune the coupling. And the Hamiltonian in the Bosniak representation in the rotating frame at this frequency is described like this. The start term is the coupling of two JPOs. And in this expression, theta p appears. The coupling depends on the relative pump phase theta p. And this expression corresponds to the two interacting KPOs. So we can generate the two interacting KPOs by two interacting JPOs. And this system has been implemented by NEC and collaborators like this. And this is one of the main results. This shows the correlation is consistent with theta p. This shows the probability of the state, measured state. And this point corresponds to the upswing and upswing, and this corresponds to the we have two JPOs, and in this case, the horizontal axis, if the horizontal axis takes the positive value, the left spin, left JPO lies in the state corresponding to the up state. And if horizontal axis takes the negative value, the left JPO lies in the state corresponding to the down state. And then the vertical direction. If the vertical direction, then it takes the positive value. The right JPO is in the state to the upspin, and the negative one to downspin. And then the higher probability is obtained for the upspin and downspin for when theta p over 2 is set to 0. This setting is corresponding to the coupling is positive, so it is consistent with this setting. And of course, the theta p over 2 is set to pi. The whole the coupling, the sign of coupling is changed to negative. So the spin up and down or down and up, the probability of such two states are higher. Sorry, no. The measure in high probability. Next, we consider the more larger systems than the 2 qubits. But for that, we need an encoding method. And we adopt the Lechner-Hawkins-Zola scheme for the encoding method. And this part is collaboration with RTQC, that company RTQC. That company is, the leader of this company is Lechner, this Lechner. That scheme or the LHC architecture is a candidate for qubits network for quantum annealing. In this method, in this network, parity of multiple logical qubits or the product of multiple logical qubits are encoded in each physical qubit. Advantage of this method is that this has no couplings of distant physical qubits. Only with there are only nearest neighbor coupling. But such nearest neighbor interactions, forward ones of physical qubits. This is disadvantage point. The Hamiltonian of the final Hamiltonian in quantum annealing, that is classical one, is represented by like this. This has JRJ is the parameter which we encode the problem, and we add the forward coupling term like this. This is this. We set the forward interaction for any placket shown as squares in this figure, and if this product is 1 for any placket, we can map Sij to this product of logical value sigma and sigma j like this, and then this Hamiltonian turns to this logical Hamiltonian like this. So the ground state of HLHC physical system for large C is mapped to that of H logical. That means that if C is large, the lowest energy eigenstate takes the in the lowest energy eigenstate, the ground state, this product would be 1 because it may be minus C times 1. So if the ground state of HLHC for large C is mapped to that of H logical. And another point of the advantage of this method is we can encode the multiple interaction logical qubits. I did not discuss that in detail. But anyway, to implement this method, the difficult point is forward interaction. So how do we implement the forward interaction of qubit? But theoretical idea to implement the LHC architecture has been already proposed, where JPOs are used as an and the proposed circuit There are 4 JPOs, and the central part is a coupler. That is a single Josephson junction or C-shunted one. And how is the forward interaction realized? Simply speaking, nonlinearity of the coupler generates the forward interaction. And the conditional pump frequency protects the forward interaction. That is similar to the two-body case. This is the extension to the forwarding. And the interaction is tunable with phase difference between pumps, like the two-body case. But the maximum strength is limited by circuit parameters. We can decrease the coupling, or we can change the sign, but the maximum strength is limited by circuit parameters. Physical implementation of the forward coupling is not published in the paper, but we have a press release like this, where we observe the harmonic coupling. And also, we already have the 8-qubit machine. This machine is investigated in the joint research with Tohoku University, that is a university in Japan. We have such an 8-qubit machine in our lab in Tsukuba. And the Tohoku University is in Sendai, that is far from Tsukuba. And the researcher in Tohoku University accesses the 8-qubit machine in Tsukuba via internet, and they send some problem and solving the problem in this 8-qubit machine, and the machine returns the solution to this researcher in Sendai. Okay, this is summary of NEC's approach. KPOs and the AC scheme are pieces of a new method of computing, and KPOs generate the cat state where an Ising spin is encoded. The LHC scheme treats the Ising model only with the nearest neighbor interaction, but forward interactions are required. This is the difficult point. And JPOs bridge the two pieces, KPOs and LHC. JPOs works as KPOs, and the forward interaction can be implemented with JPOs. And LHC already implemented interacting KPOs, forward couplings, and an 8-qubit system. And next, I briefly explain a theoretical study on NEC's approach. Forward interaction, in particular, forward interaction of JPU. Theoretical study of forward interaction. This is a slide I already shown in the previous page. Anyway, you know that we can, the theoretical idea to implement the NEC architecture has been already proposed. But as I said, the maximum strength is limited by circuit parameters. But to realize the LHC architecture or LHC method, we need a large coupling constant for the forward interaction to successfully map the physical variables to the logical variables. So we need to find such a good coupler to realize a large coupling constant. So the problem is, how do we realize a large coupling constant for the forward interaction? So our aim of this study is finding forward couplers with a large coupling constant for the LHC architecture. And we studied that theoretically examining forward couplers. One is previously proposed one, shown in this previous slide. And we also explore other couplers. And the result is the proposition of a generalized coupler in parameter settings, where the coupler has generalized coupler has an additional control nodes to increase the forward interaction. And we can give a guideline for setting parameter to increase the forwarding coupling constant. And this is the coupler shown in the previous slide. That is the single Josephson junction, or C-shunted one. And each JPO capacitively couples to the JJ, the coupler, here. And this is our proposed coupler. This has the two parallel branches of JJs here and here. One has an identical JJs in a series. And the other branch has a single JJ with smaller Josephson energy, where alpha is smaller than 1. And magnetic flux is sliding, but phi g is equal to half a flux quantum. This condition is important. And this setting, this structure is includes the previous coupler as an case where n equals 1 and alpha equals 0. And on the other hand, when alpha equals 1 over n, this structure is known to be the quantum. This is a special flux qubit, and this structure is used also for a nonlinear two-body coupler. So we apply this structure as to the four-body coupling. And we set alpha close to 1 over n to increase the four-body coupling constant. This is the potential of the coupler. This term, phi is the superconducting phase across the coupler at the edge of two edges of the coupler. And this term, the first term corresponds to this branch, and the second term shows the other branch. And phi g is set to exactly equal to phi 0 over 2. Then this term becomes pi, so the second term becomes this one. And we can expand this potential, and we expand this potential up to the fourth order, and we obtain the second coefficient and fourth order coefficient like this. And we can tune the coefficient by setting n and alpha. And when n equals 1, alpha equals 0, this is a single JJ. This is the case of previous one. EJG2 equals EJG4. So introducing n and alpha, we can tune the ratio of the second and fourth order. I did not discuss the details of the outline of the four-body coupling constant, but anyway, this is an outline of derivation. We transform the Hamiltonian to the Hamiltonian for four-body interaction. Interaction of each JPO and the coupler via this capacitor are transformed to the direct four-body interaction of JPOs, JPO 1, 2, 3, 4. We use some approximations like the rotating wave approximation, and we assume that the coupling constant of JPOs and the coupler is assumed is small. And then after such a treatment, total Hamiltonian turns to this one, composed of the sum of the Hamiltonian for JPO. And then the four-body coupling constant, four-body coupling appears here with the four-body coupling constant G4. And this term corresponds to this term in the LHC Hamiltonian in the Ising representation. And the four-body coupling constant G4 is described like this, where G minus prime is the effective coupling constant of JPO and the coupler. That depends on the parameter of JPO and the coupler, but I did not show the details. And ECG prime is a capacitive energy outcome, and EJG4 and 2 are a coefficient of the potential of the coupler. And that has enough. And there are three factors involved in the coupling constant G4. One is the G minus prime, coupling of each JPO and the coupler. That should be a small perturbation, not to strongly affect JPO. And the other two are non-linearity of the coupler. One is the capacitance of the coupler. That should be small to increase G4 related to ECG prime. And the last one is the ratio of EJG4 to EJG2 for the third term. That should be large to increase G4. So what should be done to increase G4? We have I propose that two strategies. One is that decreasing capacitance of the coupler. It can increase, this strategy can increase G4 without increasing G minus prime much. We want to increase G4, but we do not, G minus prime should be a small perturbation, small one. So we do not want to increase G minus prime. And this strategy realizes such a condition. This is the result for a specific setting of circuit. This curve indicates the four-body coupling constant as a function of the capacitance of the coupler. When we decrease the capacitance of the coupler, the four-body coupling constant rapidly increases. But the G prime, that should be small, does not increase much. And the second strategy is setting alpha close to 1 over n. It increases the ratio, the abstract value of the ratio of EJG4 and EJG2. This is described like this. And this is the resulting four-body coupling constant as a function of alpha for different n. For example, n equal 2 curve, when we increase alpha, the four-body coupling constant decreases for small alpha, but for larger alpha than some value, the four-body coupling constant rapidly increases, and then we can obtain the larger four-body coupling constant than the previous one. This straight line corresponds to the system with n equal 1, so that is for the coupler, four-body coupling constant for the previous coupler. So we can obtain the larger four-body coupling constant than the previous one. This is okay.
5-minute warning.
Okay.
Yeah.
This is a summary of this part. We need a four-body interaction of GPUs to implement the LHC architecture, and large coupling constants are needed for actually realize the LHC architecture and the quantum annealing. And theoretical idea for implementation has been already proposed, but we propose a new one that has a circuit structure like a flux qubit, and that has also additional control nodes. And just such an additional control nodes increase four-body coupling constant, can increase four-body coupling constant. And we propose two strategies. One is decreasing capacitance of the coupler, and the other is the increasing the ratio of the first and second order terms of the coupling. Okay, so this is a summary of this talk. I introduced what quantum annealing is, and in the next section, I explain the NEC's approach to quantum annealing. There are three parts: KPOs, JPOs, and LHC scheme, and an 8-qubit system has been implemented in our lab. And I also explain the theoretical study of this approach that is on the forward interaction of JPOs. Okay, that's it. Thank you. Thank you very much.
Thank you for that interesting talk. We have plenty of time for questions. Okay, maybe I will start with one question. So the previous annealing system we are familiar with, of course, is the D-wave annealer, which you had also mentioned. So I had two sort of questions related to that. Maybe I missed this aspect, like how does the approach of using KPOs and JPOs in terms of any specific advantage compared to how it is done in the D-wave system? And two, since, again, these are based on superconducting circuits, and we know there are lots of variations when you try to make many of them, will such variation have an effect on the quality of results one can obtain in this quantum annealer, or are there already methods to mitigate those variations from cell to cell, or even within a junction? You talked about identical junctions in an array, whether if they are not exactly identical, what kind of effects it can have.
For the first question, yeah, I explained what KPO is, but yeah, I did not explain how KPO is better than the transverse field dieting model. But it is the yeah, there are some studies on the KPO, and they revealed some characters of the KPOs. For example, the I did not prepare for that, but anyway, that is a little different. KPO is a little different. It has a little different noise tolerance. I mean, the KPO is robust against the photon loss. This is the one of the factor compared to the transverse field, I think. But it is a little weak for the dephasing. So there are trade-off, pros and cons. But anyway, such a difference is already known. But anyway, we are now studying such a difference in characters. So yeah, now I cannot answer such a clear answer for such a difference. And the second one, sorry, the second one, would you say that again?
Yeah, so the second one was about how your idea will be affected by, the fabrication related uncertainties about qubits, the junctions not being exactly the same, either within the same circuit or from cell to cell as you make more of them. Will that have a role, or can it be tuned since you do have some tuning available in your circuit?
That is a very good question. You mean yeah, I assume they are identical and JJs, and if there are some differences, how such a difference affect the result. Yeah, I theoretically calculated such a effect, and yeah, it affects the result, and such errors in the fabrication decreases the probability coupling constant.
So do you have like a tolerance limit that one can tolerate up to this much of variation, but beyond that it will not be very good for?
It depends. It depends. That means that I show that there is also trade-off for large alpha. If we set the alpha to be large one, the such noises, such errors, strongly affect the probability coupling constant. So, but if we set alpha to be not so large, errors in alpha does not so affect the probability coupling constant. So we need to find a good point to set the alpha. But sorry, I cannot say the exact value of such a threshold of alpha for now.
Okay, all right, thank you. Other questions?
Yeah, I had a question.
Yeah.
I have a couple of questions. The internet, the Tsukuba Sendai internet connection that you showed, I'm just curious whether it's a classical internet or quantum internet.
That is classical internet.
Classical internet. Okay. Then my next question is that your first Hamiltonian you showed, omega p is divided by 2 equal to omega. That means your driving frequency is exactly double the natural frequency of your JPO, right?
That is not exactly equal to double.
That was the previous one. Yeah, somewhere omega p over t equal to omega you have written there. So does it have to be always 2 times omega p, or approximately equal? Okay.
Yeah, approximately equal, and such a difference is represented by delta here.
Okay. All right. So I didn't notice that one before. Thank you.
Okay. We have some more time. So, a few more questions.
So let me ask a question. So Miyazaki-san, this is Das. Now, I'm somewhat familiar with the D-Wave embedding architecture. Now, I didn't fully, and that is not all-to-all connected. I think the latest, in the latest architecture, 1 qubit is probably connected to 15 other qubits. And now, so your architecture is obviously different. I mean, you, as I understood, you're trying to implement the LHZ scheme. So would that improve the connectivity between the qubits? Or did I miss something?
This one.
Yeah, yeah.
Yeah, in this network, the interaction is only for nearest neighbors. So, for example, the number of qubits interact to one qubit is maybe 8. So it is very small number, but but we translate the problem to represent. We translate the problem to embed the problem in this architecture. So yeah, something like the embedding procedure is needed.
Okay, all right.
And such a procedure is corresponding to this mapping S and 0.
Okay.
So this is like a chain in the D-wave case.
Okay, thank you.
Good morning.
Yeah, sorry. I guess I was muted. Now I was asking if there are any last question. We have a couple more minutes. Okay, maybe I can ask one last question. So this comparison with D-Wave architecture has come up again and again in this question answer session as well. But maybe one last thing I would like to know is that are there a particular type of problem which is very suited to this architecture you are proposing? Like what would be the
that is the this one, multiple interaction of logical qubits. For the, I did not mention such a Hamiltonian, but if our problem is represented by the Hamiltonian, like the Jij, sigma I, sigma j times sigma k, such a problem is this architecture is good to represent such problem.
Okay. All right. So if there are no more questions, let's thank the speaker. And thank you, Dr. Miyazaki, for the talk.
Okay, thank you.
You can unshare your screen. And let me now welcome the next speaker, Professor William Oliver. Will is a principal investigator in the Engineering Quantum Systems Group at MIT, USA. His research interests include the materials growth, fabrication, design, and measurement of superconducting qubits, as well as development of cryogenic packaging and control electronics involving cryogenic CMOS and single flux quantum digital logic. The title of his talk today is Quantum Engineering of Superconducting Qubits. So over to you, Will.
Hi, Will. This is Bhupen here.
Yes, hello. How are you doing?
I'm doing fine. How are you doing?
Pretty well. I just got a note that Zoom quit wondering if you can see the slides that I've put up.
Yeah, we see it.
Yes, we can see and hear as well.
We can hear you. We
so
can see the slides.
Hello, are you there?
Yeah, now the slides are no longer present.
Okay, yeah, so I had a crash on my side. Let me try again. It's very strange. We do this all the time in classes, so I'll give it another shot. Let's see.
Yes.
Okay, hopefully this one will go without any trouble. So I'm going to go into screen share mode.
It's already shared.
or sorry, slide share.
Yeah.
Okay. Oh no, I'm very sorry. It says it's crashing again. I wonder if we have an incompatibility in the.
Is it the PowerPoint which is crashing or the Zoom? Because you're still connected to
No,
Zoom.
it's the Zoom. Do you see the slides advancing?
No, it's frozen on the first page. But
Yeah.
we can still hear you. So you're connected to Zoom.
All right, let me try and share again. Yeah, it tells me that
Maybe
Zoom keeps.
maybe
Yep,
disconnect
please go
from
ahead.
Zoom and re-log in.
Okay, I can try that. Sure. I'll be right back.
Maybe disconnect from Zoom.
Okay, I'm back. Let me do this again. Screen. Okay. How's that?
Yeah, we can see the screen waiting to go into presentation mode.
Oh, I'm sorry, it crashed. It's unexpectedly. Never had this happen before. Have you had it happen during this conference yet?
No.
Hasn't
No.
happened yet.
Okay, that's interesting. Did Zoom prompt you for like an update to some latest version or anything like that?
Boy, this is annoying. I apologize. I'm not sure what happens. I use Zoom all the time, so I'm not sure what the issue is.
Bill, did you get any prompt for updating Zoom to the latest version or anything? I mean, if you're using daily, I'm sure it's all updated. Yeah.
No, let me.
Can you try sharing some other like a PDF file or something?
I don't have one. I could create one.
Like anything,
Try one.
just yeah.
Oh, just anything?
I mean, any PDF file just to see like the full screen
It
version.
works. Yeah, sure. So here's the conference schedule.
Yeah.
Can see that.
We can see that.
Yeah. You see me scrolling through it?
Yes.
Yeah, scrolling.
Fine.
Boy, that's really strange. So must be something between Zoom and my PowerPoint, which is, oh no, it just quit again. It must be Zoom. Look, I'm gonna log off. I'll try into Zoom and then I'll come right back. I apologize for this. I'll shorten the talk, no problem. I'll be right back.
Yeah, we have plenty of time. So
okay.
Yeah.
Okay. All right, third time's a charm. Let's see if this works. Okay, you can see that so far?
Yes.
Yeah, that one we can see.
See if I can just even do this without it crashing at one. Ah, shoot. It just quit again. I'm not sure what to do here. It's very strange. I've never had this problem before.
Let's see. Could it be specific to their Zoom link? Maybe we can. Will, are you there? Hi, Will, are you still there?
Yeah, it just popped me out. It crashes two or three times and then kills it. Yeah.
Maybe we just try one small experiment to see if it is a problem with the Zoom link they have sent. I'll just email you a different Zoom link, just like my Zoom account, and let's see if it crashes there as well. And
okay,
at least we will have some idea on how to proceed.
The
So
other
you can,
final alternative is if you send a PDF file to us, and we can show it from here while you talk from there.
Yeah,
that's true. Yeah.
If nothing works, that's the last option.
Yeah. I'll have to generate it. Give me a second. Yeah, it's unfortunate because there are a lot of videos and things that I had wanted to show. But,
so Will, I'm sending the link to your mit.edu address. Is that okay? The one without the Lincoln Lab one.
oh, yeah, Lincoln Lab one doesn't work.
Yeah.
I'm going to try one more time. I just VPN to MIT. Maybe there's something to do with it. So I'm actually doing it from MIT. Last shot. Okay. Chat, that's good. You can still hear me?
Yes.
All right, maybe that was it. I don't know. Very strange. Let me go into slideshow mode to see if that, hopefully that won't crash it. Step by step. Well, at least we know we can get this far. And you saw it advance?
Yes, it's gone to the next slide, but this is not in slideshow mode.
Right. Yeah. Sorry. I just wanted to do it one at a time because worst case, I could do it like this. So, okay, I'm going to go to slideshow mode. There we go.
Yes.
Ah, that's interesting. So VPNing into MIT seemed to work. Okay. Well, problem solved. Very sorry for all the
all right.
The controls. Good. Really a pleasure to be here. Thanks a lot for the invitation. It's okay to get now? Hello?
Yeah.
Okay, so it's okay. Sorry.
See the first page, yeah.
Yeah, okay. Yeah, good. So Will Oliver from MIT, I'd like to talk about at a very high level quantum engineering and in particular of superconducting circuits, and really a pleasure to be with you here today. So before I talk about quantum, I'd like to go back and remember the history of classical electronic computing. The vacuum tube was invented in 1906, and it was used as a radio transceiver amplifier, basically, for many years. And it was 40 years, 40, before a computer called ENIAC, you can see here, takes up a whole room. The following year, the transistor was invented in 47. And in about 10 years, we had a fully transistor-based computer called X0, developed at MIT. Still takes up a whole room. It used transistors that were soldered together. It wasn't a chip. To get to chips, we needed the integrated circuit in the late 50s. And even with that, it still took 20 years to get to the chips that we now recognize. The one I'm showing from 1971 is the Intel 4004, is a 4-bit processor. You'd have to go to the mid 90s to get Pentium Pro, which had millions of transistors, and then another 25, 28 years to get to where we are now with multi-core processors and billions of transistors. So, of course, the technology we have today is quite wonderful, but we should remember that it took over 100 years to develop it. Now, quantum computing is much more recent, proposed originally in the early 1980s, but it took about 15 years for people like Peter Shor and Eddie Farhi and Nishimori in Japan and others to figure out how to use a quantum computer. And they came up with algorithms like Shor's algorithm and adiabatic quantum computing, Grover's algorithm. But it really took another 25 years to get to the hardware today, which is that we have small quantum computers in the cloud available, maybe 100 qubits or so. I guess IBM just yesterday announced 1,000 qubits now. And so the takeaway message here is that quantum computing's real. It is now. Scientific reality. But advancing from fundamental discoveries to useful machines takes time, and it takes just science. And the other to remember is that it's to be in play, meaning that it may be no surprise that the companies that are making the chips in the business how to make
Sorry, Bill.
Sorry to interrupt. So there is an interruption in the voice.
I'm sorry, what's it?
Yeah, the audio is choppy.
All right.
Maybe you can disable your video to conserve bandwidth. Maybe sometimes going through VPN can slow down things a little bit.
Okay, let me stop the video. Is that better?
Let's see.
I'll keep going. Just interrupt me if it's a problem. Okay. All right. So good. So with that, here's my outline. I'll give a brief intro to quantum. We'll talk about superconducting qubits, engineering quantum systems, and then 3D integration technologies. So just very briefly, how's a quantum computer different? Well, it's good to compare a classical computer. Classical computers are bits, so 0 or a 1 that's represented, for example. And these are discrete states, and deterministic, basically. These transistors we have today are almost perfect. So if you set in 1, measure 1, set it in 0, measure 0, the error rate is very, very low. But quantum computers are different. They work based on coherent two-level systems, not the classical ones. All these quantum bits or qubits. And you think of it as the planet Earth.
Sorry to interrupt. The problem still persists.
I'm sorry, what's that?
So the problem of your voice interruption still persists.
Yeah, the audio is quite choppy. It comes and goes.
Can wait. Well, that's no problem.
Have we lost connection?
Oh, I'm still here. I'm trying to. Can you hear me? Okay.
Yes,
Or is
we
it
can
quite
hear you.
choppy even now, just talking?
No, this is okay, better than before, yeah. But it comes and
I
goes.
see. So it
That
might just. I see. Yeah, I'm in Zurich and it's like 7 in the morning and I'm not sure what I can really do. Yeah, it's very unfortunate that
yeah, the audio is
this is
much better
happening.
now.
It's much better. Yeah, so as long as I don't show my slides, you can hear me. So let me try
try
again.
Yeah, let's try again.
Yeah. Okay. All right, good. Is that audible or is it breaking up now?
So far, it's okay.
All right, let me keep going. I'm trying to raise my voice a little bit here in case the microphone is the problem. So we can think of this as the planet Earth. The state 0 is at the North Pole, state 1 is at the South Pole. And when you're at the North or South Pole, you're basically a classical bit. But if you're anywhere other than the North or South Pole, then the qubit is in a superposition state of 0 and 1. And this leads to consequences we know from quantum mechanics that measurement is probabilistic. And so what it means is that quantum computers rely on encoding information in a very different way than our classical computers do. And one more way to see that is if you think about representing n bits, classical bits of information, there are an exponentially large number of states we could represent, 2 to the n. So if n equals 3, there's 8 states from 0, 0, 0 to 0, 0, 1 to 1, 1, 1. But you can only represent one of them at a time. So if we wanted to process any one of these states, we would have to, or let's say we wanted to process all of these states, we would basically only have two choices. One is we could buy an exponentially large number of computers and in parallel input all the different states into the computers and calculate some function at the input, and that would be the output. Or you could take one computer and just serially feed in an exponentially large number of states and calculate the output. But either way, because the state space is exponentially large, you require either exponential hardware or exponential time to do the calculation. Quantum computing is different. We can still have n qubits. There are still 2 to the n classical states, but we can combine all of them into one superposition state where each one of these classical states is weighted by a coefficient, a probability amplitude, as we call it. And then we effectively will put this single quantum superposition state into our quantum computer and it calculates some output. And the way that it does that is through a combination of quantum parallelism and quantum interference. And we'll talk about measurement in just a moment. So the question is, how can we take advantage of this quantum information, a way of representing it? Well, just like with classical computers, we have gates. So classical gates are shown here, for example. I won't read through all of them in the interest of time, but there's a NOT gate, an AND gate, an OR gate. And these are Boolean logic gates, which take an input and create a classical output. What is important here is that we know that for Boolean logic, we don't need all of the gates that I've shown here on the screen. We only need a few of them, and they're not even unique. The NOT gate and the AND gate, for example, are a universal set. Now, it does require at least one 2-bit gate, but with a universal set, we can go from any state in the state space to any other state in the state space. And that means we can do universal Boolean logic computing. So that's the way conventional computers work. And quantum computers work in much the same way. We have many gates, and again, I won't read through all of them, but they're basically rotations of the qubit state around the Bloch sphere or the planet Earth. And so one is the identity, basically don't do anything. the X gate rotates around the X axis 180 degrees. And we'll see an example of this in just a moment. So there's many single qubit gates. There are also two qubit gates where the state of one qubit impacts the other qubit. And we'll see that as well in a moment. But what I want to say here is that quantum computers similarly have a universal set of gates for implementing arbitrary quantum logic. And again, it's not a unique set of gates. There's different combinations. But with a universal set, we can implement any arbitrary quantum logic. In fact, we can also implement any Boolean logic gate in principle, but a quantum computer does that often, usually, no better than a classical computer does, and often it is actually less efficient than a classical computer. And we'll note that it takes at least one 2-qubit entangling gate. So let me show an example of a single qubit operation. This is the classical gate, a NOT gate. Takes a 0 to 1, a 1 to 0. Quantum version of that is called the X gate. And what I'm showing here is a video, and I hope this more or less comes through, that shows the rotation of the blue vector, which is the block vector, the qubits. It's being rotated around the x-axis, which is why we call it X gate. Yeah, this just froze. Why did that happen? Are you still there?
Yes, but the presentation has disappeared.
Yeah, boy. This is almost a comedy of errors. All right, let's go back. Try this again. Okay, I think we're back. Is that true?
Yes.
Okay. All right. Maybe I won't do this just in case. All right. So here's the animation. Geez. VJ?
Yeah, the screen just came back. It was frozen for a bit, but now, yeah, we can see the slide, but it's frozen.
Static?
But maybe, yeah, it moved after like 5 seconds, it moved a little bit. Maybe you can just move to the next slide. Okay, presentation is gone again.
I'm really sorry. The Zoom just crashed again. I'm not sure what to do here. Do you guys want to? Do you want me to continue fiddling with this, or do you just want to call it a day and say this just isn't going to work?
Bhupen, do we want to try the other option? Will, if they can share the slides from their end?
If you send it a PDF to us, so we can display from here.
All right. Let me do that. Who should I send it to?
The organizers, you got a mail from organizers, right?
Yeah. All right, let me save it as a PDF file because it's a huge file. Very sorry for this. This doesn't happen. Zoom is usually pretty reliable.
Yeah.
Yeah. All right, so I'm generating the PDF file now. It'll take a second, I think. All right, I got the PDF file. I'll now email it to the organizers.
Will, you can also send your PPT presentation. Also, you can send. I mean, if it is not too
Way
big.
too large. I'm sorry. You want the?
Is it greater than 25 megabytes?
Much larger. It's got a whole bunch of videos in it.
Ah.
Yeah. Okay, so you want me to send it to the Qubit Symposium CQuERE at
Right.
Gmail?
Yeah, you have already sent it?
No, I'm just attaching it now. Yep. Let's see. Okay, I am sending it
Okay.
right now. Yeah. Okay, so you guys should get it in just a moment. Yeah, my apologies. Not sure what's happening. Okay, it's left the inbox, so it should be on its way.
Okay. এসে দেখো পাঠিয়েছে just. So we are still waiting to get it.
Okay, no problem.
এসছে? এখনো আসেনি? এসছে?
No, no, not yet.
Has it come? Has it come? Hello?
Not yet.
Not yet?
Not yet.
Will you try to send it
On
once
my
again?
side that it.
Come yet.
I'm sorry, what's that?
It hasn't come yet, so you can.
Oh, okay, I saw on my side
again?
that it's sent. Yeah, it left.
Will, what was the size of the file?
7 megabytes.
Oh, okay, then it should be fine.
এখনো আসেনি? I don't know what the problem is.
Yeah, very sorry for all this
Yeah,
trouble.
can you send it to my mail also? I don't know what is happening.
Okay, sure.
Maybe include this email as well. I'm sending you an email on chat here.
Okay.
Just a Gmail address so that.
All right, I got it. Thanks, BJ.
Yeah.
All right, so that should be on its way to you.
হ্যাঁ কি হলো আসছে আমার তো আসেনি এখনো
I just saw it left my inbox or my outbox, so it's in the ether.
Okay. Refreshing.
Will, did you send it to my email?
No,
Dev?
to VJ. Do you want me to
VJ.
send it to you too, Dev?
Yeah, Bhupen sir.
Yeah.
Yeah, sometimes it happens that any mail sent from any other domain to TCG CREST domain, I mean, does not come. It may happen. So it will be better if you collect the mail from in any Gmail account rather than tcgcrest.org. Most probably that's the reason.
All right, I can
I have
send it
not,
back to you.
I have not received it on my Gmail as
I
well.
communicated with him from my Gmail, so he must have sent it through Gmail.
Okay.
I sent it to Gmail, but I didn't send it from a Gmail.
So yeah, I haven't received it yet.
Yeah, this is.
It's some security issue which is blocking.
Vijay, did you get it?
No, it's not here yet.
All right, let me try a Gmail.
Yeah, you may
Sending it from
press
my
execute
Gmail. Yeah.
using your Gmail. That is okay. So we just received it right now. Yeah.
আসেনি না এখনো?
Yeah, just received it.
Just check. Okay. Yes, we got it in.
Hey, it arrived. All right, good.
Yes.
Yeah. ডিসপ্লে করছো তো এখন নাকি?
Yes. Here it is. So yeah.
Go to the same page, the last page where Kotuji was displaying.
And there won't be any video. That's fine. We'll just keep going. And I'll.
You are here.
Yeah. So I think we can skip this part because without the video, it doesn't make too much sense. So yeah, next slide. Yeah. Okay. So on this slide, what we're showing is basically a 2-qubit gate. The classical version on the left is the classical XOR gate. And it takes 2 bits as input, X and Y. X is the control bit, Y is the target bit. And you can see the truth table there for classical exclusive OR. And if you look on the right, the quantum CNOT gate, basically the same truth table for inputs, but now you have a control qubit and a target qubit. And here qubit X is the control and Y is the target. So the actually I can maybe do some stuff here. So if you have an input that is basically 0, 1 plus 1 superposition for the X qubit, the control, and Y is in its ground state, you can apply the CNOT gate and you'll get an entangled state at the output where the 0 corresponds with the 0 and the Y. That's a 0, 0, 0x, 0y. But when the control qubit is in state 1, we flip the y qubit. So when x is 1, y becomes 1. And now we see that this can no longer be entangled, or it can no longer be separated into an x and a y component. So it's entangled. And so the point here is that of these types of single and 2 qubit gates, we can do any arbitrary quantum logic. Next slide, please. Yeah, so the way that an algorithm works then is we take a massive superposition state, we put it into our computer. Generally it'll be an equal superposition state. Put it into our quantum computer, and then implement a series of gates based on the algorithm. So single qubit gates will apply one gate to one qubit, but you can see that it impacts all of the states in the superposition state, and they're an exponentially large number of them. Now that's followed by quantum interference, which serves to change the coefficients. Now we have alpha, beta, gamma, delta, etc. Sometimes we'll do 2 qubit gates where the control qubit determines what happens to the target. But again, it's one gate applied to 2 qubits, but it impacts 2 to the n coefficients. That's the point. That's followed by quantum interference that changes the coefficients again. And then throughout the algorithm, by the end, the idea is that almost all of the probability amplitude is coalesced around one particular state. Here we say beta prime equals 1 or approximately 1. And that's important because we know that when we make a measurement, the probability of getting any one of these outputs is going as the magnitude squared of that probability amplitude. And so if the probability amplitude for one of the states out of the exponentially large number of states, if that is 1 or near 1, then with high probability, we'll get the right answer. Okay, next slide, please. So then you could ask, well, why don't we have quantum computers today? And then the issue is basically 2 timescales. And one is the coherence time, the lifetime over which the qubits remain quantum coherent. And even if we can create the computer in a perfect quantum state, we'll call it psi, almost immediately it starts interacting with its environment in ways that we don't have full control over, and we don't know. They're random interactions. We may know something about them, their statistics, but we don't know the specific interactions. And what that means is that over time, the qubits will evolve in a different way than we had intended. And so effectively the state blurs and eventually it's gone. So the qubits are still there, but the state in which it's in is now in a different state than we had intended from our algorithm. And the time frame over which this happens is called the coherence time. And it can be due to the qubit's lifetime, coherence time, or even control errors. Now, the second time scale we care about is the gate time. And this is the time required for a single gate operation. Pick the one that takes the longest. That's a conservative estimate. And the figure of merit is the number of gates per coherence time. So how many operations can I do before the state blurs away? And this is a proxy for what we call gate fidelity. Next slide, please. So with this, we can compare many different qubit technologies against one another. What I'm showing here on the left is the number of operations before an error. That's basically the metric we just talked about, number of gates within the coherence time. And that's basically 1-to-1 in the gate fidelity. So if you have one error in 100, we would say that's 99% fidelity. One error in 1,000, 99.9%, etc. And on the horizontal axis is the gate speed. So how rapidly can I implement these gates? Basically 1 over the gate time. And what you see is you want to be in the upper right corner for the best performance. And today, no technology is quite there. And that's why there's no clear winner yet. And likely there won't be a winner. It'll just evolve over time. But some of the major candidates include trapped ions, superconducting qubits. You can see them there. I should say that the blue square is the 1 qubit gate fidelity, and the red triangles are 2 qubit gate fidelities. Next slide. And there are also neutral atoms, NV centers, and others. For implementing quantum error correction, it's also important that we know the measurement times. And right now, for all of these technologies, the measurement time is the slowest. So the cycle time for error correction, say for a superconducting circuit, is about maybe a megahertz, whereas for trapped ions and for neutral atoms, it's about a kilohertz. And that factor of 1,000 matters because the computer runs a lot slower, obviously, if we can't apply the gates as fast. Next slide. So with that, let me turn to superconducting qubits. We often call them artificial atoms, and I think it's because of this analogy that's shown here. On the left, we have our periodic table of elements, and those elements have different behaviors depending on the numbers of protons, neutrons, and electrons. And on the right, a very loose analogy here, but on the right, we have circuits which have inductors, capacitors, and Josephson junctions, and we can put those circuit elements together in different ways with different numbers. And depending on how we do that, we can come up with a circuit with different types of behaviors, and we call them artificial atoms. The one feature that they all have is that they, when cooled down to low temperatures, they have discrete quantum mechanical states as illustrated here. Next slide. So, yeah, apologies, this doesn't unfold, but the way that you can think of this is think of it as a parallel LC circuit with an inductor and a capacitor. This is a harmonic oscillator, has a harmonic potential, and so the energy levels are equally spaced by h bar omega r. Omega r is the resonance frequency of this oscillator. And the problem is that we can't uniquely drive the 0-1 transition without driving all the other transitions. So we need something to be nonlinear here. And the element we choose is the Josephson junction, which is a tunnel junction, superconductor, insulator, superconductor. And the tunnel junction has the current and voltage relation that was given to us by Brian Josephson. But for our purposes here, if we combine them in the usual way, we can get an inductance that is nonlinear in the current. That's the point. And with that nonlinearity, we can create what you might think of as our version of the hydrogen atom. It's the simplest electronic circuit that we've got for qubits. It's a Josephson junction on the left and parallel with a capacitor on the right. And when we do that, the energy is no longer parabolic, but takes on a cosine potential. And as a result, the 0-1 transition has a unique frequency from all the other transitions. And so we can consider this now a qubit. Okay, next slide, please. So we need to operate it at a very low temperature, and that's driven primarily by the fact that we chose the resonance frequency of this nonlinear resonator. And typically it's around 5 gigahertz. And if you equate that Planck's constant times frequency to Boltzmann constant times temperature and solve for temperature, that's about 250 millikelvin. And that means that even at 250 millikelvin, thermal blackbody radiation will drive the 0-1 transition. So we don't want that to happen. So we operate at a much colder temperature, say 20 millikelvin, where those processes are almost negligible. And, 30, 40 years ago, this was a research project, but today, these are commercially available. And you can see a picture here that shows the cold stage, where this whole region here is about 0.5 meter by 0.5 meter by 0.5 meter. So it's quite a large volume. And you can see the attenuators, microwave switches, the qubits are in packages like this, or on the right like this, filters, etc. And all of these can be operated at cryogenic temperatures, it turns out. Okay, next slide. Of course, we fabricate these, and this is a feature. We fabricate primarily on silicon, at least here at MIT, and these are silicon wafers up to 200 millimeters are wafers that we fabricate on. And if you zoom in on the wafer to a particular device, here's one device, a linear chain of 5 qubits, and you can see readout resonators in the upper right part, and you can see some control lines in the lower left for each of these qubits. If we zoom in on one of them, this plus sign that you see is actually a capacitor. It's a capacitor to ground. And then the control lines are in the lower left. And then zooming in more, you can actually see the inductor. Here the inductor is quite small compared to the size of the capacitor. But if you zoom in, you can see it. And now you see that it's a loop, and it's interrupted by two Josephson junctions. And this is called a squid. And the reason we use it is because if we put a magnetic field through this loop here, we can control the qubit frequency in situ. And then finally, we zoom down to the lowest level, or the smallest size, 100 nanometer scale, which is the Josephson junction itself. So this leverages CMOS fabrication techniques. It is a silicon technology. Next slide, please. This is a video that unfortunately won't run, but the idea here is that we control rotations around the Bloch sphere by using standard IQ mixing, which is shown on the right. And with a local oscillator, which is close to resonance with our qubit, we put that into a mixer and we multiply that by an intermediate frequency arbitrary waveform. And the output of our mixer then is a pulse that is resonant with the qubit, but it has a phase, 0 or 90 degrees, shifted, depending on whether we use the I or the Q port of our mixer. And that determines whether we'll rotate around the x-axis or the y-axis of the Bloch sphere. Okay, next slide, please. Yeah, and so the coherence times of our qubits have improved dramatically over the last 20, 25 years, from around a nanosecond for the first qubit in 1999, almost approaching a millisecond now for the qubits today. And you can read more about this in some of our review papers that are shown at the bottom right. But to give an idea, here are some of the coherence times that we have for different types of artificial atoms or superconducting qubits. And right now, the fluxonium is our highest T2 time, around 350 microseconds. And our longest T1s are over a millisecond now. Okay, next slide. So part of improving coherence has been a story of improving materials, fabrication, and qubit design. So what I'm illustrating here are basically all of these problems. So in the early days, we made qubits LC resonators with a parallel plate capacitor that's shown here. And if you zoom in on that or the junction, which also has a capacitance, because of the parallel plate nature, most of the electric field is in this dielectric between the two plates, which means that that dielectric is participating almost 100%. And these dielectrics are quite lossy. And as a result, our T1 times or energy decay times were maybe microsecond at best. And so the idea from Sholkoff group at Yale was to open up the capacitor and make it a lateral capacitor side by side. So now the blue plates are side by side. And so the electric field goes from one plate to the other, but most of this electric field is actually going through the silicon substrate, which is a very high Q dielectric, or in fact through vacuum in some cases. And so as a result, the T1 time became much longer, 10 microseconds at the time, but now hundreds of microseconds. This, of course, is not scalable, and it's the way it's shown here, but you can relax a little bit, go back to a planar substrate, but keep the lateral capacitor geometry, and then you get many of these benefits. And those are the types of qubits that we're using today. So to improve coherence, you can change the design, for example, change the capacitor geometry, or you can do materials and fabrication engineering to improve the dielectrics and the way we fab it. Next slide, please. What's challenging, though, is that if we want to do this type of iterative improvements, it takes a lot of technology. It takes materials growth, maybe materials analysis. You have to design a device. You then have to fabricate it. You then have to test it at cryogenic temperatures, do some data analysis, figure out what happened, and then evaluate and update. And of course, then you spiral in and eventually, after many iterations, make an improvement. And that's part of the reason that it's taken, 20 years to get to the point where we are today. Next slide, please. And if you want to build a scalable technology, we can go back to David DiVincenzo's criteria from the late 90s. There are basically 5 of them, and they all make a lot of sense. In fact, almost all of these are identical for classical technologies as well. You need to have a robust, reproducible technology. We're not going to scale to millions of qubits if we don't have a reproducible technology. Same thing for our transistors. You need to be able to put the qubits and a quantum computer in its initial state. We need to be able to measure it. We need a universal set of gates. And of course, we need sufficient coherence and fidelity to do that job. And today we're at about, 3 nines or 4 nines fidelity. And I'll show a comparison later if we have time, how that stacks up against classical computers. But it's, classical computers, the error rate is 1 part in 10 to the 20th power. They almost never fail, whereas our qubits fail with 1 part in 1,000. Okay, next slide, please. So this is what quantum computers look like today. Here's IBM's Osprey. This has 430 something qubits, and they just announced 1,000 qubits yesterday. This is Google's Sycamore processor. Here's a processor from Rigetti. These are all gate model superconducting. Here's IonQ. That's a trapped ion computer. Here's one of D-Wave's quantum computers, a quantum annealer, which we just heard about. And then, of course, in the middle here, this is not a quantum computer. You'll recognize this, I hope, as the Wright Flyer, the first airplane to be self-propelled, piloted by a person. And I put this here because I think this is basically the stage that we're at with quantum computers. When we saw the Wright Flyer, 1903, we knew that commercial aviation would come. This was quite an achievement. At the same time, this was not a commercial airplane, right? It's going to take time and for quantum computing to mature to the point that we can say they're solving real world problems that are commercially viable. On the other hand, everything that these companies are doing right now is critical to go on the road or the path to get to that quantum computer of the future. And so even though the quantum computers we have today aren't very powerful, they can't do very much. This is all part of the technology development, just as this initial Wright Flyer airplane was important at the dawn of commercial aviation. Next slide. So with that, let me just say a few things about engineering quantum systems. And by the way, Vijay, kick me off when you need me to stop. So
yeah, sure. I think we have time. You can go ahead for some time. Yeah.
Oh, okay, thank you. So the grand challenge for realizing scalable quantum computers is going to be implementing active error correction. And the reason for that is the physical qubits that we have today, their error rates are 1 in 100 to 1 in 10,000. Okay, so the probability of an error is 10 to minus 2 or 10 to minus 4. But where we need to be for practical applications is something around 1 part in a billion or 1 part in a trillion. So orders and orders of magnitude away. Again, for comparison, our CMOS transistors are down here at 10 to the minus 20. Thankfully, we don't need to be at that level. We'd take it if we had it, but the blue region here is sufficient for practical applications. So how do we make up this gigantic chasm that we have? Well, we can do material science and we can do fabrication engineering and design improvements, and those are important for moving this yellow region down a little bit. But I don't think it's going to make up, 6, 7 orders of magnitude. To do that, what we need is active error correction. And the idea is to take a single physical qubit, like we've seen, and aggregate several of them together. So there you can see now there are 9 qubits here. And the idea is that those 9 qubits acting together can perform better than any single individual. And the concept is that you might be thinking, well, okay, if I put a whole bunch of qubits together that are bad, the situation is only going to get worse. And that's true if the individual qubits are too faulty. But if they're above something called the threshold, if they are at least good enough, then aggregating more together increases the resilience through redundancy. And at some point, you can improve the physical qubit error rate enough that adding more makes the situation better. And that's the concept of error correction. So of course, this doesn't come for free. There's an overhead associated with adding more qubits. So initially you take a hit in performance, but with error correction, that can be made up for by the quality of the qubits and the distance, the size of the error correcting code that you have. Adding more qubits then, or larger codes, will improve the overall performance exponentially. And you can see that here on the right. So we have the physical error rate of our, say, a 2-qubit gate, and you can see that here it's maybe, around 0.1%. So that's 3 nines, 99.9% fidelity, so 0.1% infidelity. And yet, if we look at the logical error rate on the left, as we increase the number of qubits, say from 17 in blue, which we call a distance 3 code, you can count them 1, 2, 3 qubits on a side. If you increase that to 5, and then 7, and then 17, and then 25 on a side, you can see that this error rate is dropping exponentially, right? And that's what we need to do to get into this region of gate errors where we can do practical applications. Now, the number of groups around the world have demonstrated preliminary examples of error correction. Andreas Wallraff's group, for example, here at ETH in Zurich, where I am now, has demonstrated a distance 3 code and was one of the first to show the cycle. But in those cases, the error rate didn't improve by doing the error correction. But he showed that, going through the cycle, which is quite an achievement. Recently, though, Google has shown that by going from a distance 3 to a distance 5 code, by adding more qubits, the error rate actually went down. Only a little bit, but it went down. And that's a very important demonstration because it shows that error correction can work. Now, of course, we need to make it better, but it showed that it can work. Okay, next slide, please. But if we want to make a large-scale quantum computer, we need an architecture. It's more than just qubits, right? There's an application layer, which means software and programming and a human-computer interface. Of course, at the bottom, we have our physical qubits. But in between, we have several layers that have to do with, for example, a logical controller. We're familiar with that from classical computing that interprets the application and the software we wrote, compiles it in such a way that we know what gates to apply to our physical qubits. But of course, in parallel with that, we have additional 2 layers, layers 2 and 3, whose only job it is to identify errors and correct them or mitigate them if possible. And mitigating errors is called passive error suppression, and actively correcting them is called active error correction. Next slide. And this has to happen every clock cycle. Next slide, please. I usually think of this in the context of a sport that we play in the US called lacrosse. And without the videos, it's probably not going to make much sense. But yeah, so let me not do that. You can advance to the next slide, the next few slides, and get through this section. Yeah, without the video, it doesn't make much sense. Okay. Now, even with active error correction, there's still research and improvements that we need to make. And in particular, one of them is quasi-particles. So when radiation or photons hit superconductors, they can break up Cooper pairs and create excitations. And this is a problem because those excitations aren't local necessarily to 1 qubit. You can see that they in a local region will excite many qubits. And that's a problem because we would call that a correlated error. And a correlated error is something that conventional error correcting codes don't necessarily correct for today. And so we need to do research to either eliminate or mitigate quasi-particles in our devices. And that's just one of many noise sources that we have in superconducting qubits, and we should do our best to mitigate them as best as possible. Next slide, please. Yeah, and the way that, yeah, thank you. So with that, I know that I'm at the top of the hour. Vijay, should we stop it here, or what do you think?
I think we can take
continue for
5 to
another
7 minutes more.
I'm sorry, what was that?
We can go for another 5 to 7 minutes, and then we'll have a short
Okay,
question.
yeah, I don't have too much. So let me do that, and then feel free to kick me off. So where we are today with superconducting qubits is we have small scale processors. What I'm showing here on the left is a two-dimensional array of superconducting qubits. And you can see it's getting pretty crowded. If you want to try to access the qubits from the edges of the chip, sometimes called the beachfront, you have to bring in wires, and it's getting crowded. And of course, if we went to a 5x5 or a 6x6 array, this just wouldn't work anymore. And so the way that we handle this is through 3D integration. So next slide, please. So the 3D integration that we're doing here at MIT is illustrated here. Basically, there are three chips. One is the qubit chip, and that, of course, is the wafer or the chip that has the qubits on it. And you can see that here's a capacitor and a qubit, and it's face down, and it's bump bonded to something that we call an interposer. Now, the interposer is made of the same type of high resistivity silicon that the qubit chip is made of. So even though the electric fields are now penetrating both qubit chip and interposer substrates, we're not degrading the qubits very much. But in order to access the qubits, then we need to have through silicon vias, which are shown here, and these are superconducting. And then to get the signals to the through silicon via, we need a readout and interconnect layer, which is the third layer. And it's a multi-layer process. You can think of it like a multi-layer printed circuit board where signals can go over and under each other. But once they arrive at the right place, they basically go up and address it. So that's the 3D integration that we're building. And let me show you a few pictures now of that. Next slide. So of course, the qubit chip on top, we already saw this picture. So next slide, please. That's the top chip. This is a side cut. Oh, sorry, back one. Yep, this is a side cut of the interposer and through silicon vias. It's about 100 microns deep into the silicon, and it's about 10 or 20 microns in diameter at the top. So aspect ratio of 10 or 20 to 1. We make it with titanium nitride. And so you can see that the titanium nitride is superconducting by 2 or 3 Kelvin. So these are superconducting through silicon vias. Okay, next slide, please. So already, even with just 2 of these chips, we can do some interesting things. So one thing we can do is recognize that the resonators that we use to read out the chips, I didn't mention that, but we read out using resonators, are distributed, and they can be quite large. This one here shown is more than 1 millimeter in length. And of course, the qubit itself is quite large. It's almost 0.5 millimeter. But with a TSV, what we can do is we can take the resonator portion and make it vertical. And so that's what's shown here, is that we have a TSV, and we have a little coiled inductor here, and there's some parasitic capacitance between the inductor and the TSV, and this resonates. And if we design it correctly, we can make a resonator, but now it's vertical and it takes up much less space. You can see the size of it correspondingly here. Okay, next slide, please. We've done tests of this, and so what we're showing here is a T1 of a qubit that's read out in this way in a flip chip geometry with a vertical resonator. And the T1s are not bad, 20, 30, 40 microseconds, something like that. So this works reasonably well. Okay, next, recently published, if you're interested. Now, the other thing that we can do, next slide, please, thank you. The other thing that we can do is, in fact, recognize that we can actually make a capacitor out of these TSVs as well. That's on the right here. And so if we make a vertical capacitor with two TSVs and then create a junction along the top right here, we now basically have made a qubit. And so the size of that qubit shown here on the left is much, much smaller than the huge lateral capacitor. And so you can have both a qubit and its readout resonator both being vertical. And when we did this, the T1 times similarly were 20, 30, 40 microseconds range. So we're still working on this, but that's pretty, that's not bad. And again, if you're interested in learning more, there's a paper by Tom Hazard from our group as the lead author that just came out this year. Okay, next slide. The other thing that I'll mention is that 3D integration also improves calibration. And what I mean by that is it reduces crosstalk and allows us design features that reduce calibration. Just to illustrate this visually, on the left, we have a 9-qubit chip, just planar chip. And if we look at the crosstalk between different qubits, that's shown here with this confusion matrix where the diagonal is the qubit talks to itself, which of course is normalized to 1. And then you look at the mutual inductance to all the other qubits, and you can see that they're all greenish color, which is roughly 10% crosstalk. It's huge, right? But if we go to a flip chip geometry, even though we have more qubits here, if you look at the diagonal, it's yellow, but the off diagonal, the talking to other qubits is darker blue. And so we're now at the 1% or less level. And this was enabled by the flip chip, which allows for better screening of the crosstalk, but it also allows better ways to bias the qubit, which have less crosstalk intrinsically. So that's a paper that just came out from Cora Barrett in our group. If you're interested in learning more, she's at the bottom there if you're learning more about that. And so with that, I think that's the end of the talk. Next slide. No, there's one more. Sorry. So I forgot to say, we also have that readout and interconnect layer. If you go back just one slide quickly, that this bottom chip here, you can see is basically an 8-layer superconducting chip. So each of these gray regions is superconducting. And we've put this all together and it still gives us coherence times around 20, 30, 40 microseconds, but I won't really have time to talk about that. And so with that, let me thank you for your attention. And if we can go to the next slide, let me also thank my many colleagues at the MIT campus and MIT's Lincoln Lab, where this research was performed at both places. And I very much apologize for all the technical difficulties, but thank you for giving me some extra time, and thanks for your attention.
Thank you, Will, for that comprehensive overview of superconducting qubit engineering challenges and where the future is. We have some time. We're running late, but we can have a few questions.
Yeah, one or two.
Yeah.
Hello.
Yeah, that's. It looks like that the flip chip is the answer for future, right?
I think so. Yes. The companies that are making these multi-qubit chips with hundreds of qubits on them, of course, are doing 3D integrated versions. And so I don't see any alternative to doing what we call heterogeneous integration of qubits, interposers, and readout and interconnect layers. Yeah.
The vertical holes that you mentioned about 20 micrometer diameter, those you fill completely with titanium nitride?
Oh, we only line it. We only line it with the titanium nitride, about 100 nanometers thick. Okay. And we also don't fill the vias. We leave them empty, which has some implication for subsequent processing steps. But most of the commercial fills that go in to fill the gap that's there are quite lossy. So we want to avoid them.
Okay. And the third thing is,
of course, putting 20 microns, 10 or 20 microns of titanium nitride and filling it up with just the metal is also quite time consuming.
Mm-hmm. I understand. So the correlated error that you mentioned is due to quasi-particles, and This also happens that if you send a quantum computer to space and the high energy
Absolutely.
particles, if they hit. Right?
Yeah, so what we need to do as a community, I glossed over this in the interest of time, but some people are proposing maybe we'll build our quantum computers deep underground where they're shielded from, in particular, cosmic rays and the muon secondary particles that come from cosmic rays. But of course, this is a huge overhead to operation. So rather than doing that, what we need to do as a community is find ways to mitigate the quasi-particles. And we do that with conventional CMOS. It's called radiation hardening.
Yeah.
And we actually have ways to do that with superconducting qubits, and we're just preparing a paper now that shows that quite nicely.
Oh, you can do the radiation hardening for superconducting qubits?
Yeah, that's right. So of course, the degree to which it's hardened is something that's still, to be investigated carefully, but we've shown that through gap engineering of the Josephson junctions themselves that we can prevent quasi-particle tunneling. And we're not the only ones who've shown that, but we're preparing a paper that also shows it. And by doing that, the main issue with quasi-particles is that they tunnel across the junction and create a relaxation of the qubit. And so if we can stop that tunneling through some band gap engineering, we can prevent the T1 mechanism, and now the qubits are radiation hardened.
Okay. All right,
Okay.
Vijay.
There was somebody else who wanted to ask a question.
Yes, sir.
Yeah, please go ahead.
Yeah. Thank you, sir, for this interesting talk. Sir, I have a confusion regarding that graph where you show the differences between physical qubit error and the logical qubit error. I mean, what's the basic differences? What's the basic reasons why we see these differences in errors for a physical qubit and a logical qubit?
Oh, yeah. So the physical qubit error is the typical error that we have due to relaxation events or dephasing events. We sometimes call them bit flips and phase flips. And that happens at about a 1% or 0.1% or even 0.100% level now in the physical qubits. But that's just too lossy for the too many errors to do a real calculation, which requires billions and trillions of operations. So error correcting codes is one way to get beyond that, but there's no free lunch. We have to take many physical qubits and band them together to achieve a more resilient logical qubit. And fortunately, this theory is very well developed that we know that there's an exponential win if we can do this, meaning we can suppress the error rates at a logical level exponentially as we increase the size of our code, which means increase the number of physical qubits. So there's no free lunch. We have to add a lot more qubits, but we gain much, much more than that. And so by increasing to 100 or 1,000 physical qubits, that's to make one logical qubit, by the way, we can go from error rates that are, say, 1 part in 1,000 to error rates that are closer to 1 part in, say, a billion. And that's what's going to do it for us. Now, we're only suppressing the error. We don't eliminate it, right? And that's important to remember because sometimes people think of error correction as I've corrected all the errors, there's no more errors. No, there's still an error rate, but the rate at which the errors are happening is low enough that we can hope to complete a calculation without any errors. So if our error rate is 1 part in a trillion, we can pretty reliably do a computation that requires a billion steps. Right? So that's the idea, is to suppress the error rate to a point where I can run the commercial algorithm I'm interested in with a very low probability of having an error.
Okay, that means we'll use effectively that logical qubits, which is made of some collection of physical qubits. Is that so?
That's correct. So when we talk about an algorithm needing, say, 1,000 qubits, that means that algorithm would need 1,000 logical qubits. And then if you count 1,000 physical qubits per logical qubit, now we're talking about 1,000,000 qubits, physical qubits, right? So indeed, the number of qubits increases pretty quickly here. But that's what we have to do if we want to realize, commercial scale problems.
Thank you, sir.
Yeah, thank you for the question.
Okay, maybe one last question.
Hi, Professor Will. Hello.
Questions on YouTube.
Hello.
Oh, sorry. There are some questions on YouTube.
Yes, so I'll speak out one.
Okay, maybe just pick one. Yeah.
Okay. So one question is, how can we mathematically model the error to the topology, quantum volume, and number of gates in general sense, or any mathematical model to optimize the overall error?
Sorry.
I'm sorry, that was a bit quiet on my side. Could you repeat it, PJ, please?
Yeah. No, I couldn't hear it either. Please come closer to the mic and say it loudly.
Yeah. So can you hear it clearly now?
Okay, it's a little better, but
okay. So how can we mathematically model the error to the topology, quantum volume, and number of gates in general sense, or any mathematical model to optimize the overall error?
That's a very good question. The mathematical modeling of errors in a quantum computer is still something that's being developed today. And the challenge is that the fact that quantum computers are powerful is based on the fact that we can't simulate them with classical computers once they get beyond certain size, roughly 50 qubits. And we will be well beyond 50 qubits. So there's no chance with a classical computer that we'll be able to perfectly simulate a quantum computer. So we have to come up with ways that we can abstract and make reduced complexity models that tell us information that we need to design these chips or to characterize and qualify them, even though we can't perfectly know what's happening. And this is not so different than a conventional chip. With a chip with 1 billion or 100 billion transistors on it, there's no way to test every single possible transistor in there on every single chip that they sell. So they have protocols that they run that gives them confidence the chip is working. But some of the older folks here may remember, I think around 2006, Intel had a chip that actually had a logical error. It wasn't a very important one, but in fact, they had sold many chips where there was a flaw that had escaped their testing procedure. The last point is that quantum volume is a metric that IBM had proposed, but it requires being able to fully simulate a quantum computer to know how close to the actual outcome the computer got. And so if the number of qubits was 40 or 50, that's possible. But if it gets into the hundreds, it's just not viable anymore, because doing a full state tomography or process tomography of a large chip like that is just not possible, and simulating it just is not possible. So even IBM acknowledges that quantum volume was useful when they were at quantum volumes of 2, 3, 4, 5, 6, or 7, but getting to much larger quantum volumes, they have new metrics that they're coming up with now.
okay. I think that was an interesting set of questions and discussion. Thank you, Will, again. And I think with that, let's thank all the speakers in this session, and we'll close for lunch now. Thank you, everyone.
Okay.
Thanks.
Yeah. Thank you very much. And again, my apologies for all the difficulties.
Yeah.
Thank you, Will.
Yeah, Bhupen, Snehal, you can take over.
Yes.
Okay.
So let's come back at 1:30 for the next session.
Thank you, Bhupen. Sorry for this issue.
Well, that happens sometimes.
I feel like I use Zoom every day, and I'm not sure what the problem is. Anyways, good to see you. Good to see you, VJ. Take care, and thanks again for the invitation.
Likewise.
All right. Bye, Will.
Bye.
Hi, Miko.
Hi, how are you?
I'm fine. So you have joined. Everything fine?
Yep.
Good. So sometime back, your postdoc, Sumon, visited us for a brief time, very short time.
Yeah, I think he was on vacation in India and
Yeah.
doing some traveling.
Yeah, he just contacted and he just dropped by just for a couple of hours. That's all. So he's of course, I mean, I met him in the conference.
Right.
He's presenting a poster there on your Unimon. Right. So he couldn't spend much time, so it was very short.
Okay. Well, there is maybe some overlap what he talked about, but I have also a lot of other stuff here in my talk. So
No, that's fine. No, he didn't give a talk here because we are just for a couple of hours.
okay.
In our set, our dilution refrigerator, you have just put in the cryoelectronics.
Okay.
And the Israeli team from Quantum Machines will come to install the control electronics later on. They asked us not to open the boxes.
Okay.
So hopefully we'll be ready to make measurements on a single qubit to start that in a couple of months.
Okay, there you go.
So then you have to think about more meaningful things to do.
Yeah, yeah.
So in that case, I don't know. I mean, if there is any possibility for any collaboration from you or support that.
Yeah, sure. I mean, if there is something you're interested, you will see in my talk quite a lot what we're working on, and I think it could be possible for us to, I mean, help you guys building up something or send you some devices to measure. Let's see.
Good, because we'll probably need much more time to set up our fabrication facilities also. We won't be able to do immediately anything.
Okay. Yeah. I mean, we are fabricating these chips all the time. So if there is something that you're interested and we have chips, it's possible to send. Of course, what we like to do is that we like to, when we send them out, we like it to be packaged and that there is some, let's say, relatively high certainty that it works. Because if we send you 10 chips and you bomb them and they don't work, then you wasted your time.
That's right.
So it's a bit of a work for us, and then we need to find just the person who is motivated to do that work. But typically it works out.
Right. So initially, I think that initial characterizations of single qubit and learning things will get some time. They have a postdoc and two PhD students right now. They're taking care of the lab. Well, let's go through the initial phase and then we'll try to explore the possibilities. The first qubit, of course, we'll get from Vijay. They have used a lot of them and they are at their disposal. We have 5 more minutes to start. Let's see. In this session, we have 3 speakers. You, Paul Ford Diaz from Kilimanjaro, and Arthur Garcia is also from Kilimanjaro.
Yeah, unfortunately, I have to take off after my talk. We have our Center of Excellence group team leaders meeting there. Before Christmas, we go to a nice restaurant typically. Here we do that, so
that's very important.
Yeah, so I need to go there, and also I have prepared some talk there as well last night. So,
so it's, I think in Europe, I think it's having a kind of vacation with a program, which is scientific program. That's quite usual. So I spent quite a lot of time in Germany. Initially, I was postdoc in Germany in Hamburg Synchrotron Radiation Lab. And then I had two sabbatical years there. One in Hamburg, Daisy, and another in Dresden. So there, for 1 or 2 days, we used to go out, the whole institute practically, the whole department, somewhere away. And then we had a 2 days scientific program. That's the in-house scientific program, basically. So similar things are the.
We also have such events for the center, but yeah, then it's like we invite all the researchers in the center to.
Yeah, maybe that's a
annual seminar.
So is that a common tradition in Europe?
Well, if you have a research center like this is an externally funded center, then you typically have at least an annual event, and you can also have these review meetings combined.
Mm-hmm. Right. All right. So you have other Indian postdocs also there in your group?
Yes, I have Suman and Priyank. I think they are from India. Then I have a PhD student from Nepal, and I'm trying to hire. I am trying to hire one student from India at the moment also.
Trying to hire or fire?
Hire. I think he's thinking at the moment whether he wants to jump to the north from India.
So does he have any background in this area?
Yes. He has some. He has a very nice CV, I would say, for a.
It's from where? Which institute?
I'm not sure if I can disclose. I mean, more information in this forum.
All right. I don't insist on that. I just casually ask.
Keep the information confidential. Yeah. But in general, I can just say that.
Yeah. I just casually asked, so you don't have to answer. That's fine. Let me see. How many people have come back? Let me check out. We still have a couple of minutes. জয়েন করেছে কত? Okay, I welcome everybody back to the program. And I am Bhupen Dev from the Center for Quantum Engineering Research and Education. That is the organizing institute for this symposium. So I'm going to be chairing this session. And this session has 3 speakers. Let me introduce the first one, Professor Mikko Mutonen, and he leads the Quantum Computing and Devices group at the QTF Center of Excellence, Aalto University, Finland. He's an associate professor of quantum technology, shared between Aalto University and VTT Technical Research Center of Finland, and a co-founder of the quantum computer company, IQM. Mikko's research interests cover a wide variety of topics in quantum physics and technology. The title of his talk is Superconducting Qubits with Millikelvin Electronics. Mikko.
All right. Thanks a lot. It's very nice to give this presentation to you, and I hope you enjoy, and actually feel free to ask questions anytime. And also at the end, I hope we have some time then to.
Yeah, the talk is for 45 minutes, and the discussion after that. Would you like me to give a tinkle after 40 minutes?
Yeah, sure. I can also try to keep track of the time, but also, if you like, you can. I think you can also ask questions during the talk, because then we just need to leave 5 minutes for the transition, right? So, but it's up to you. I can do whatever, but I'm going to talk about a little bit about a few different things, so to say. So when I transition to a new theme or new topic, that could be a time also to ask questions from the previous one, but also you can of course ask questions from anything after the talk. So
okay.
All right.
Yeah.
So
I see that this write-up that I see here, it shows writes associate professor Purview. I know that I see that you are a full professor already.
Oh yes, okay, that's true. I actually got just like a month ago. I got promoted to full.
Okay,
professor.
congratulations.
So I think when I gave you my information, it was still associate professor.
Congratulations.
Okay. Thank you. So let me just give a glimpse of our lab. This is a picture from about more than 4 years ago. You can see that our then new fridge Blueforce XLD was not fully yet wired up of the room temperature electronics, and now we are actually expecting the fourth fridge right here to the bottom right corner. So this will be quite well packed with Blueforce fridges. It's amazing to see how close, how small floor space you need to make these experiments that I'm going to talk about. And thanks to, of course, my research group, Quantum Computing and Devices, it's been great to work with these talented people. Of course, I like to thank also the collaborators, and as you might know, we started more seriously working on superconducting qubits when we got this quantum computer project funded something like six years ago. And that gave also a rise to spin out IQM from the research. And IQM is now its full own entity. And here I'm not talking on behalf of IQM, but I'm talking more from I'm representing Aalto University and VTT here. But anyways, it's been very nice to see IQM to grow here, and also we have been able to collaborate with them scientifically in some cases. And also you heard about the Quantum Technology Finland Center of Excellence. Here are all the group leaders here, and Jukka Pekola is leading the center. And that's been a very nice also forum to find collaborations, especially VTT and VISA. VISA, we collaborate a lot on the experimental side. VTT is doing amazing fabrication, toolpaths, and things like this for helping us in our experiments. And in Finland, we also have so-called Institute Q. It's a national quantum institute. It's like a network of more than 50 research groups working on quantum science. Okay, what I think is important now for quantum computers is fidelity. Of course, preparation, measurement fidelity, but especially gate fidelity, because typically your gate depth is more than 1. So that's very important in this NISQ era where we have error-making quantum computers. We published earlier this year work mostly done at IQM about long-distance transmon coupler with the gate fidelity of almost 3 nines. And this is actually a 2-qubit gate, so for a single qubit, the fidelity is 3 nines in this case. And that's great. I think this is kind of the numbers you like to see on your quantum processors, but I think the aim has to be in general to get 4 nines of fidelity in all operations, and then I have a feeling that there could be a good chance of getting some early quantum advantage. Of course, that requires a breakthrough in the algorithmic sense as well. Well, another point is scaling. People say if it doesn't scale, don't do it. Well, in the early NISQ quantum advantage, I think it's more the fidelity than scaling, because if you have thousands of qubits and only 3 nines of fidelity, you can't do a single depth of circuits before getting errors, right? So you for the NISQ, you don't need the systems to scale beyond what has been demonstrated now. You just want the fidelity up. But in the long run, when you have quantum error correction and you want to grasp all the juice from your quantum algorithms, you need the system really to scale. So if you have the fidelity locked at 4 or 5 nines and you can scale up, then you're basically home free. So that's really the key in the quantum error correction case. And now I'd like to talk to you with this motivation about a few things. We access the gate fidelity and the scaling aspect. And for the fidelity, we have been developing this qubit concept we call the Unimon. That has higher anharmonicity than the transmon, but otherwise works in a quite similar ways. It's protected against the charge noise and stuff. So that is something that I will talk about later on more. But we have also been developing control electronics that operate at millikelvin temperatures. For example, we have developed a millikelvin microwave source to control the qubits in a very low noise fashion. For readout, we have been developing the most sensitive bolometers in the world, and another technique that could boost also the readout. And for reset, we've been developing so-called quantum circuit refrigerators, which are kind of on-demand tunable dissipators for your qubits, so that you can dissipate the energy or information out from your qubit, basically for the reset purposes. And later on, we'd like to combine these with the Unimon to make a demonstrator of high fidelity qubit system in all respects. Okay, but let me first talk about the Unimon qubit, where Eric Hypä, who is a quantum engineer at IQM and working on his PhD for Aalto, has had a very, very big contribution. And the Unimon you can see the circuit diagram basically here on the right. It's a CPW resonator half wavelength that is grounded at both ends. Typically, your CPWs are open at both ends, but this is grounded from both ends. And there's a junction in the middle, which makes actually this a gradiometric squid type of thing, that where you have a junction that is inductively shunted to ground. And this lumped element circuit diagram looks pretty much like a fluxonium, but the idea here is that you operate this in a regime where your Josephson energy and the inductive energy, they are almost equal. So that's the Unimon regime. And if you look at the potential landscape on the left, you can see that at half flux quantum point, then the quadratic potential is cancelled by the quadratic part of the cosine potential, and you're left with something that is very unharmonic. And that's where you get the boost in your unharmonicity. And of course, this is not the only qubit out there. We have also put a big sort of a phase diagram of qubits on this plot. And especially the quantum qubit has similar features as the Unimon, but the Unimon has a difference that it is a geometric inductance that we have here. We don't have a junction chain that is making this inductance that you cancel. And because it's inductively shunted, it's of course fully immune to low frequency or let's say quasi-static charge noise. And because of the gradiometricity, it's insensitive to uniform flux changes. And the nice thing about this is that because you use exactly same components as you use for transmon qubits, you can use the same fab recipes and materials. So it's really just a change in the design. All right, the Unimon chip that we measured is here. There's actually 3 Unimons coupled to a common readout line, and they have also their readout resonators capacitively coupled to them. And when we tune the flux difference, you can see that at 0 flux, the frequency is close to 9 gigahertz, and the unharmonicity is very small, just tens of megahertz. But when we tune the flux to half flux quantum, these potentials, they start to cancel each other. And well, naturally the frequency goes down, but at the same time, the unharmonicity goes up. So then it becomes hundreds of megahertz. Mm-hmm. And this matches quite nicely our models. When we make each A larger, we cancel more and more of the quadratic potential, and the unharmonicity shoots up. And you can see that we can go close to a gigahertz, or well, we could go even to a gigahertz and beyond if we wanted, but we stopped basically here, relatively close to a gigahertz. Then the gate fidelity, we basically were measuring the gate fidelity with randomized benchmarking, and we were reducing the gate duration. And as we do that, we see the fidelity getting better and better, and it's actually coherence limited. So we're not yet exciting the qubit to higher excited state with these gate pulses. And if we would just keep on reducing the gate duration, we would get higher fidelities. But unfortunately, our electronics did not manage below 13 nanoseconds. The good thing about this was that on a good day, when we calibrated everything...
Limited by the electronics that you have now?
Excuse me?
Is this gate fidelity limited by the electronics you have now?
Oh, but it's limited by the coherence, but because of the electronics and the setup, we could not make faster pulses than 1-3 nanoseconds. Mm-hmm. So in some sense, you could say that the electronics was limiting us here on achieving higher fidelities, although it's coherence limited for a given gate duration.
Okay.
And the average gate fidelity we could keep constant for 8 hours, and that was good news that it can be very stable. All right. So let me now, by the way, if you guys have some questions about the Unimon, I think now it's time to ask, because I'm moving now to the balametric readout of qubits.
Unimon, that potential that you have shown, you don't work at the minimum of that the value that was there?
Oh, we do work at half flux quantum. Oh, so these fidelities are measured at half flux quantum. That's the operation point of the Unimon. Okay. It's a flux sweet spot as well.
All right. Okay, you can go ahead.
All right. So for the balameters for readout, if some of you know that the typical dispersive readout of qubits, it's based on a linear readout resonator, and you typically drive. So the frequency of this resonator depends on the qubit state, and you typically drive in the middle of those two frequencies. So then your information is encoded in the phase of the microwaves that travels through this transmission line, and you amplify that, for example, with a quantum limit amplifier such as TUPA. And in the end, basically what you measure is the voltage or the expectation value of the annihilation operator. And what we are proposing to do here is to change this quite large amplification chain. Okay, sorry. This is a typical trajectories in the IQ plane when you do this dispersive readout, and you can get single shot. These dots are single shot readout results. But what we are planning to do, or we have basically done, is to replace this amplification chain, which has these bulky isolators, which are really big components, and they are preventing the system to scale up. We want to replace that by a simple 50 ohm resistor. And this 50 ohm resistor, you might think, well, how can you do that? Well, it's actually an input of the bolometer. And when the system is getting now signal to it and different differences in the power, you basically can measure the temperature of the resistor with the bolometric technique. And now you are sensitive to photon number and not sensitive to voltage. And that's great, because let's say that if you have a vacuum state in your cable, you will not have fluctuations, photon number fluctuations there, but you would have fluctuations in your voltage. So there is quantum noise that is actually amplified in the traditional case by the tuba, but there is no vacuum quantum noise giving you photon detection signals in your bolometer, for example. And we can use this multi-channel driving technique then to be sensitive with the qubit state, to basically transform the qubit state not to the phase signal of the microwaves, but to the amplitude or power signal of the microwaves. And you can see that here is an experiment where the qubit ground state stays close to the vacuum state, and the excited state goes further out to about 50 photons in the cavity. And that's actually quite large power for a bolometer, and the bolometer should kind of be quite should be convenient to measure these kind of power levels with our bolometers.
So is that zero state means you have single photon in the photonic state?
No, here you can see that the amplitude goes to about 7, and 7 squared is about 50. So of course, depending on how you design your readout, your critical photon number, or the photon number you can put to the cavity, can be only 2, or it can be much more. It depends on your design. Okay, so a little bit more about these advantages is that actually the pump power of the bolometer is about, let's say, minus 30, sometimes even minus 40 dBm. So it's many, many orders of magnitude lower than the tuba pump power. So if you want to scale these things up, you can think that you can probably afford to have a bolometer per qubit, because well, even 100,000 times minus 140 dB is only a picowatt of power. So you can think that you can afford to put a lot of bolometers there and operate them, whereas in the tuba you might run into some problems with the power dissipated when you pump them with high power tones. The bolometer is basically qubit sized, so it doesn't add much of the footprint, even if you would do it on a chip very close to the qubits. The tubas are much larger. Well, now don't get me wrong. I really will use tubas and we like them. I just want to say that with this different readout technique, there may be some advantages of the bolometer. And there is in the bolometer natural frequency conversion. So you pump the bolometer at the frequency that is very different. It's like half of gigahertz frequency, whereas the qubits work at several gigahertz. So you don't have this crosstalk and frequency crowding for that reason that easily. And you want to keep the bolometer input cold. It's a cold resistor, and that's exactly what you want your qubit to see. You don't want the qubit to see some sort of hot environment or some environment that is non-equilibrium. And as I said, there is no quantum noise amplified in the bolometer. So with these sort of advantages, we started to use our metallic bolometers first because they are more robust. And here you can see a typical sort of readout chain of the bolometer. So we reflect a 0.5 gigahertz power from it, and then we see a dip in the transmission, and that dip in this reflection coefficient that depends on the heater tone that we put into the bolometer. Because the tank circuit of this bolometer is basically an LC resonator where the inductance is arising from these Josephson junctions, SNS Josephson junctions that are sensitive to temperature changes of this gold palladium nanowire. The input is here, it's basically a 50 ohm resistor that absorbs the radiation.
How many Josephson junctions you need for a single bolometer?
Well, in this case, you can see that we have, wait a minute, is it 7 or I think it's, oh no, it's 8. Well, 8 junctions where one of the junctions is much shorter. I'm not sure, we don't necessarily need so many, but we did put them in this generation in series. It basically, you can tune your characteristic impedance of the LC resonator circuit by adding more junctions. You can get it up, and also there will be less Josephson nonlinearity with the given inductance when you have more junctions in series. Basically, we think this is quite sort of that the Josephson nonlinearity is very weak typically in these bolometer experiments. All right, and then we use the dispersive readout scheme, but we drive at the resonance of the ground state. And so basically, if the qubit is in a ground state, we start to populate the resonator. If it's in the excited state, we don't populate it. And we use it in this transmission mode. So when we are actually in resonance, we have less signal going to the bolometer than when we are out of resonance. Okay. And this is the chip. We have basically 6 qubits on the chip, but we only measure one of them now. And here you can see Rabi oscillations measured with the bolometer. So basically, I can explain what we do. So we, from time to time, or let's say that we first prepare the qubit in its ground state by waiting, for example. Then we put in a separate qubit drive line. We put a resonance drive with the qubit with the variable duration that is on the x-axis. So basically, you start to Rabi oscillate the qubit, and then when we stop the drive, we read out the bolometer with this 10 microsecond readout pulse. And we can change the frequency of the qubit drive, and we can see the typical Chevron pattern. And you don't see much of decay in this time scale of a microsecond because the qubit T1 was quite long compared to the 1 microsecond. All right. And this has only about 500 averages of the bolometric readout. And that we think was quite remarkable. We were thinking that the bolometer is much worse in the first experiments that we do, but this was really the first time we could see this, and it seemed to work out nicely. And then we went for the single shot experiments, and we did an experiment where we changed the averaging time, basically the time we average at the end of the readout pulse and the pulse length. And you can see that the fidelity depends to some extent on these parameters, and then we can choose like a point where the fidelity is at maximized. And I have shown here the single shot probability distributions with the qubit prepared in the ground state and excited state at that operation point, where we get the fidelity of 0.62. And with this definition, this fidelity 0 is really random guessing. So we are well above 0. So we clearly have single shot readout. And in this very first experiments that we did with the bolometer. So we were quite excited about this. And this is a nice starting point to optimize. Why do we have or what is the bottleneck for the fidelity in this experiment? It's actually the T1 of the qubit or the speed of the bolometer itself. But if we take the T1 errors out, then the fidelity would be already more than 90%. So what we are going to do in the future, we are going to replace, when we have those working, this metallic one with the graphene bolometer, which is about 2 orders of magnitude faster than this metallic bolometer. And then we can most likely improve the fidelity a lot. And there are some other improvements we can also make already now with the metallic bolometers as we speak. Okay, if there are some questions about this bolometric readout, I'm happy to answer them now or also later before I move on.
You can go ahead. I think you can go ahead.
Okay, I'll just move on. All right, now about the millikelvin microwave source. Why we think it's important for scaling up quantum computers is this, that typically what you have is you have your, let's say, n-qubit quantum processor at 10 or 20 or 30 millikelvin. And how you control it is that you have your microwave source and a waveform generator at room temperature and a mixer. That's the way that is mostly used in the community. Now, of course, you could also have DDS, direct digital synthesis, but this is kind of the most traditional way of doing. And then you have this number of coaxes going down, and you attenuate at every stage your signal, and then you deliver to each qubit its own driving signal. You can frequency multiplex this to some extent, but still the number of cables will scale with the number of qubits. So if you think about scaling to millions or billions of qubits, this is probably not going to be the way to do it, because you would need a fridge that starts to be the size of a soccer field or even larger than at some point. So, and for us, our 5-qubit control electronics looks like this. So even going to 500 also is going to make your rack big and expensive, right? Also, the cables are expensive, the attenuators are expensive. So it's going to be thousands of euros per qubit. So millions of qubits would be billions of euros with this, just scaling up with this technology, which is probably not going to be the case at that point of time, of course. So one solution could be that you put the microwave sources to millikelvin and the waveform generators to higher temperature. You would save a little bit of, let's say, money this way, because you would not need as high bandwidth in your cables, and they could be then, the demands are more relaxed. However, in the end, of course, the solution will be that your control electronics will be fully at millikelvin, and you would only have a sort of a data IO line basically going down.
In this case, your mixer is at 10 millikelvin?
Excuse me, can you
Your
repeat
mixer,
the question?
which in the conventional setup, it's outside at room temperature.
Yeah, right. So the one on the left is the conventional setup. I'm saying that what we are now showing some results of the microwave source that would be used in this kind of setup in the center.
So
but in the long run,
microwave and this arbitrary wave generator, they are mixed at 10 millikelvin.
They could be mixed. We are not in the experiments we did so far. We did not mix them. We only have characterized the source itself. But I'm saying that I'm motivating our research by this kind of sort of scenario that could be then used as a next step.
Okay.
All right. So our source looks like this. It was actually designed and fabricated by VTT. And if we look at the circuit diagram, simplified circuit diagram here on the left, you can see that it's basically a capacitively shunted Josephson junction where we also have a resistive shunt, and we current bias that 1 ohm resistor, and that basically makes a voltage bias on the Josephson junction. And there is also an inductance here in the circuit, which will make the system to resonate when the voltage across the junction corresponds to that resonance frequency. And here we can see that the inductor is this kind of double spiral inductor, and the capacitive shunt is this big cayenne colored thing here. And the junction is actually in the crossing point here denoted, and the resistive shunt resistor is this blue, dark blue colored thing here. So that's how it works, or that's how the design looks like. And when we feed in the bias current through this line here, that goes through the resistor and biases the junction. I'm just going to show our results and compare them to the previous results. So if you compare the previous millikelvin sources that are these two ones here, we had more than 100 times more power coming out. And if you want to make gates for qubits with, let's say, 3 nines of fidelity or higher, you really need this power. It's quite a nice calculation that you can do that independent of your characteristic impedance of your line. You need this amount of power because you can't make with resonant driving, you can't make your drive signal to couple to the qubit too strongly, because otherwise the qubit would also decay through that line. So there is this kind of a trade-off. So then to do higher fidelity gates, you need more power. And the line width of our source was also narrower. And when we measure the phase noise, it's also better. So we really were able to go into this regime where this could be useful for qubit driving, whereas the previous works showed that yes, this in principle works, but the specs were not as great for driving as we have. All right. So first, what we did is that we started to ramp up the bias current, and we measured just the total power coming out of the device. And with a quite simple theory, we could predict basically the power, and the measurement is spot on at this range of bias currents. So this is a sort of a sign that the system works as expected. And we can also measure the frequency of the, so this is measured with the spectrum analyzer. And you can see that the frequency also is changing when we ramp up the bias current. And also from the quite simple theory, these are some Bessel functions here. And you can see that everything here is well defined. So from this very simple theory, we can also get a prediction that matches nicely with the measurement. So we have a good understanding how the system works, and these simple theoretical results can then be used for further optimization of the devices. The line width in the so-called free running mode, where we don't phase lock the source to anything, is about 4 kilohertz. It's a Lorentzian line shape, but my postdoc was using a resolution bandwidth of 1 kilohertz in the spectrum analyzer, so that's why it looks Gaussian. And when you measure in the IQ plane and average for a long time, you will get this kind of a ring. And the reason why you get a ring instead of a blob is that, well, your source is not phase locked, so the phase will drift and you will get all different phase values. But the important point is that there is nothing in the center. So it's not a thermal source, it's a coherent source. And well, then we can go to injection locking, so where we basically, on top of the bias current, we add a weak coherent tone to lock the phase of the oscillator. And then you can see that the line width really narrows down. And it actually narrows down to so narrow line that it starts to be difficult to measure with the spectrum analyzer we had, because the minimum resolution bandwidth was, I think, like 1 hertz. Sorry. Well, here it says 100 hertz, but I think it was about 1 hertz, the minimum one. But it's a Gaussian filter, so we can start to look, where does the Gaussian start to have tails, and then we can basically say that, okay, what if our source had a 10 millihertz Lorentzian line shape? Well, the tails should be here where the yellow line is, but the tails are lower. So we could say from this data that, okay, the line width has to be less than 10 millihertz from the actual source, maybe somewhere around the millihertz or lower. Okay, this was when we were measuring the
line width 1 millihertz in gigahertz. Frequency is 5 gigahertz.
1 millihertz is 10 to minus 12.
Line width for 5.3 gigahertz pulse.
Excuse me?
1 millihertz line width.
Yes, and the frequency, as you can see, it's somewhere at 5 gigahertz.
Yeah.
Yes, so it's 5 times 10 to 12 times narrower than the central frequency. So then we went and measured the spectrum at different frequency offsets, and I just want to say that this measurement here does not have that issue of the resolution bandwidth. So we do measure at very small offsets as well, and you can see that when the source is on and off, it's the blue and red curves. There is some difference here, and so there is some amount of phase noise is coming from the source. But when we calculate what would be the gate infidelity arising from this phase noise that we measure, you can see that it's less than 10 to minus 4 for quite many gates, like the NOT gate, for example, up to more than a millisecond, or more than maybe even up to, well, yeah, for gate durations more than a millisecond, and your T1 time or T2 time is typically less than a millisecond. So this source would be ready to go for such high fidelity cryogenic pulsing. We did not have the pulsing yet implemented in the source itself, so you would need then the mixer as well at millikelvin. All right, but then let me move to the last part of my talk. And so now we have gone through the qubit, the readout component, which is the balameter, the microwave source, which is for the gates, and then still for the reset, we have been building quite for a long time this quantum circuit refrigerator. I'm going to show our latest chip or design here, and that our latest QCR is basically a quarter wave resonator which is grounded at this end, and we have a single NIS tunnel junction here. So the NIS is normal metal insulator superconductor tunnel junction, so it has no supercurrent through it. But when the quasi-particles tunnel, they can at the same time grab photons from the resonator or from something that is coupled to the resonator, which is a qubit here, and cool that down. And we can drive this junction. It turns out it's quite versatile. We can drive it we can put DC voltage, we can put AC voltage, we can put even RF voltage, microwaves. And all of these scenarios gives us cooling. And we read the qubit with a separate readout resonator. So that is then a little bit isolated from the cooling effect. And first, we did some experiments where we actually could use the qubit and the dispersive shift of the qubit arising from these photons in this reset resonator to measure the Fox state populations of the reset resonator state. So for the first time with QCR, we have now been able to see that how many photons there really is in the resonator. So here we sweep the qubit driving frequency on the y-axis, and you can see that this state here corresponds to let me see. I think this should be the ground state. Yes, this line here, this top line is the ground state, and when we drive the qubit stronger with the coherent tone, you can see that we are changing our state, starts to look more and more like a coherent state. And here you can compare the measured populations and those of the coherent state, and they match quite well. So coherent state, if you have a large amplitude, you start to have no population in the zero Fox state, and you can see that, yes, that's what happens here. Okay, then we drive the system to a coherent state of about 1 photon on average, and then we can increase the QCR DC voltage. And you can see that you start to lose photons from the two photon Fox states, 1 photon Fox state, and going towards the ground state. And that's what we plot here on the blue. So the photon number is going down. And in the dots, we only use the DC voltage. In the crosses, we also added on top a microwave drive. And you can see that you can actually you can make this decay to be faster with lower DC voltages with the microwave drive. And then what we went ahead is we also heated up the system. Okay, actually, this is when we are then driving with the microwave drive. We are driving the QCR instead of a DC voltage. So we don't put at all DC voltage. We can put microwave drive, or we can put an AC drive, and with the same power, and we can see that they work quite in a similar way. All right. Let me go forwards and show you then the qubit. So we also were able to observe that if we don't pulse the QCR, the qubit has a T1 of, let's say, 8.5 microseconds. And then when we turn on the QCR for a variable amount of time, which is on the x-axis, we see the qubit population that to decay much faster. So we can see that we can speed up the qubit decay with the QCR, and we are, since then we have taken more data and analyzed this a little bit more carefully, especially using single shot measurements on the qubit to really see, is the qubit in a thermal state or is it in some other state? And if, let's say that if we prepare the qubit in the 2-photon state or F state that you typically call it, can we also reset the qubit then? And yes, we can. Here on the right, you see that independent of the state we measure, we prepared the qubit to, we get after a long QCR pulse, we get the same thermal population. And actually, we are now writing a manuscript about these experiments that we have done much more since, and we hope that to be in archive pretty soon. Maybe I think in January it should be there. All right. Any questions about the QCR? Or actually, now you can ask questions from anything, because I'm just going to leave this summary slide here, and you can ask questions.
So I have a question.
Yes.
Hello. Yes. So this is regarding the millikelvin microwave source. So up to how much frequency can you tune this microwave source?
Aha. So now the frequency of the source is basically determined by the frequency of your tank circuit. So we had this inductor and the shunt capacitor. So that, but okay, with the bias current, you would tune it a little bit, but that was very little. So what I think is that if you want to tune the frequency, you would probably want to introduce a squid or a JOFET somewhere, not probably to some place which is extremely strongly coupled to your current through the inductor, because then you can get excess noise from your tuning element. But still, you could probably tune it relatively okay amount to, for example, to kind of fine tune your frequency somewhere where you want it to be. With the mixer, of course, then I mean, typically you have an LO and then you have a mixer. So if you have a mixer set up, then you could drive your qubits even with the microwave source not tuned at the resonance with your qubits, because you could then promote or depromote or increase or decrease the LO the signal frequency from the LO by the frequency of your INQ quadrature signals you put to the mixer, for example, if you use an IQ mixer.
Your state-dependent bolometer measurements, so that can you put that slide on? I mean, you probably have some.
Sure. Here.
Yeah, and then it was this one. So detector signal in millivolt. Ground state.
Yes. So the x-axis is to some extent arbitrary, because it depends on how much amplification we have even at room temperature before we record the bolometer signal. So I wouldn't look at how many, is it a millivolt or is it hundreds of millivolts, but it's kind of a signal axis. So then, but the important point here is that how well separated, relatively speaking, these two distributions are. So relative to their width.
Mm-hmm.
And the y-axis is logarithmic, please. Please note that. So on linear scale, it would look, of course, that the distributions are much sort of more distinct.
Mm-hmm. Yeah, I see that. So the detector bias signal, that is sort of arbitrary. It's not absolute.
So the detector signal is, so we put in this pulse, pulse to the readout. We pulse the readout line, and then that pulse is going to the bolometer, and then at the end of that readout pulse, for the last 10 microseconds in this case, we average the detector signal, which is in volts, and then we get one shot, and then we repeat that experiment, and we basically I think we have binned this detector signal axis here, and then we calculate like what's the relative amount of shots per bin, and that's how we get the point on the to the y-axis, or the y value for the point probability.
Okay.
I have one question.
Yes, please go ahead.
Yeah, for the arbitrary wave generation, what do you practically use? Is it direct digital synthesizers, or you use analog oscillator and analog microwave division chain to synthesize your frequency?
Well, we used to use mixers exclusively, but now we have also turned into DDS. I think it's coming. So we still mostly use mixers, I think, but we do have some equipment that can do DDS as well.
Okay, thank you.
All right, so we still have some time, so if someone else has more questions. Eventually, you want to put this microwave sources very close to the qubit at that 10 millikelvin stage, right?
Yes, and that microwave source that we operated, we did operate actually this at the qubit temperature. We didn't just yet have a qubit chip that would be coupled to the source.
So in the same design, you'll just integrate qubit and the microwave source.
Well, the microwave source is made with the niobium process, the tri-layer niobium process. So I wouldn't put this. I mean, you can make relatively okay qubits with that process as well, actually, but I just for practical reasons, I wouldn't probably do it with this on the same chip. But you could have basically the idea that I show you here is that you have a quantum processor that is bonded or somehow bonded to a superconducting CPU. And and there could be, of course, even an interposer layer here that would have the microwave sources. But basically, the microwave sources, I see that they would not be on the qubit chip itself, but they would be on a control electronics chip that would be bonded in a scalable way to the qubit chips.
Okay, so if that can be also integrated with mixture, which is also at millikelvin, then that's the picture is shown in the middle. That would be advantageous.
Right. In this case, I mean, you could even have different chips for the source qubit and the mixer if you wanted. The mixer could, of course, also be done with the same process as the microwave source. For the first experiments, typically, to make things work and the designs work, it's good to have them on different chips because it's easier to fix only one part of your system, keep the rest unchanged for that time. But then, of course, in the long run, you could when you know that it's working, then you can scale it up.
Anybody else has any more question? We still have a few minutes. If not, then let's thank Mikko for this excellent talk. And thank you, Mikko, for...
Thanks.
All right, we wait for a few minutes and I don't know, Paul is already here. So Shall you start already? We have 5 minutes. We still have time, but we can start and finish it later. Paul, you are there, right? Hello? Paul, are you there? Probably not yet. So in that case, we wait for 5 minutes. Wait for him to arrive. Hi, Manu.
Sorry, Bhupen, did you say something? Or?
Yeah, I said that. Are you still from home?
Yes, yes.
Yeah. From home? Okay.
Yeah, yeah.
All right. So you have fully recovered from your cold?
Hello. Almost, yeah, yeah. Okay. So I think Paul is here, so we can start.
Yeah, sorry, I was in another call, and
yeah.
you were calling me now.
Okay, welcome you, Paul, to this session. And so let me introduce speaker, Dr. Paul Diaz. He's the leader of the Quantum Computing Technology Group at the High Energy Physics Institute in Barcelona. He works on quantum computing with superconducting qubits. And he's also the co-founder of Kilimanjaro Quantum Tech. The title of his talk is Superconducting Coherent Quantum Annealers. And they are the one who got the European largest project to build a quantum annealing computer. Paul.
Okay, yes, let me grab my slides. Okay, can you see my slides and my mouse?
Yeah, we see it.
Excellent. Okay, well, good afternoon, I guess, everybody. Good morning, Europeans. Good evening, Americans. Thank you very much for the kind invitation to represent the efforts we are doing in Barcelona, and particularly on coherent quantum annealers. And so this talk is going to be quite introductory because basically we are still at the introductory stage of developing this technology, but there's some things we've done, and I would like to share with you the different areas where we have been advancing. As Professor Duff was introduced me, I'm a researcher, full-time researcher at the IFAE Institute for High Energy Physics, where I lead quantum computing lab, and I'm also co-founder and currently CTO of Kilimanjaro. And so part of the work that I will describe involves both teams. So this is a bit what I'm going to tell you today. I'm going to introduce the concept of coherent quantum annealers and the project Abacus, which is the European project that was awarded to the consortium I'm coordinating. And then I will introduce a bit the flux qubits we're developing for this project. And then later on in the presentation, I will tell you a little bit the latest developments we've done in the QCT group in IFAE on developing new materials or studying materials for quantum processors, particularly the nitridized aluminum thin films, and also we've studied penetration depths in aluminum. And finally, I will very briefly mention the explorations we're doing in project where we explore the interaction between ionizing radiation and qubits. So this is the IFAE group, the Quantum Computing Technology Group. Currently, we have 5 PhD students. One of them is basically finishing, and we have a new Indian PhD student starting early next year. The lab has been built since 3 years, and we have our own fabrication facility that is basically set up in the last few months. So this is basically the academic lab that I'm coordinating, but then Kilimanjaro has a much bigger team, and they are partly working also in this lab together. So we have some ongoing collaboration between the two teams. So let's start with the coherent quantum annealing description, in particular the project Abacus, annealing-based variational quantum processors. That's the project that was awarded to us. Before introducing the project, I want to motivate why the need for this project. So as you may know, there's existing quantum annealers by the Canadian company D-Wave. They've been around for more than 20 years now, so they have a lot of experience and they've made a lot of developments. But there's some facts about their technology that we would like to put our focus on. First one is the coherence of their qubits is poor, in the sense that they've measured and they've published values on the range of a few nanoseconds compared to the microseconds timescale that their computations usually take. Therefore, their system is incoherent most of the time. The interactions between qubits that they've designed, they are the type of Ising models, and these are amenable for classical algorithms such as quantum Monte Carlo. Therefore, they are easier to simulate by classical methods. The connectivity, as is well known, is a bit sparse, and that reduces the computational power of the machine, because to embed like fully connected graphs, the effective qubit number drops by orders of magnitude. And finally, they focus only on two-body interactions. So as a result of this, there hasn't been any quantum speed up. And the question is there a way to improve on this technology without simply increasing the number of qubits that's the avenue they are pursuing? And our proposed solution, or our proposed alternative, is what we call coherent quantum annealing, which basically the key ingredient is to use qubits with long coherence, and long coherence with respect to the relevant timescales, which are the ones of the duration of your problems. Then we also are interested to go beyond these Ising type interactions. So this is in the language of spins. Ising type is the ZZ interactions of the spin magnetic moment, and so going beyond this is adding an XX or a YY interaction to this model, and that already makes the classical problems, the classical algorithms, give them a very hard time to solve the same problem. We want to improve and increase the density of connectivity between qubits, and ideally we would like to go beyond these two-body interactions. So this last one is something more like a wish than what we can actually do with the span of the project. So all these points actually, they go along the same lines as what is needed for these equivalents between the adiabatic quantum computing and the standard digital quantum computing that has been demonstrated. This equivalence has been demonstrated in a few papers. I'm citing the first one, but there is at least two more that I'm aware of that came later. So all these ingredients are necessary in order to bring at the same level adiabatic quantum computing and digital gate-based quantum computing. So the question is whether these circuits or these elements can be all brought in together. I would like to also emphasize at this point from the memorable paper by John Preskill, where he coined the term NISQ, the near scale intermediate noisy quantum computers, regarding quantum annealers, that it's a debate still open whether the quantum annealers will provide advantages, and the key ingredient is that more experiments are needed. So this technology has to be developed further. I mean, there's been a ton of development on digital gate-based quantum computing, particularly in superconducting qubits, but not as much in quantum annealing. And therefore, one needs to take advantage of all the developments in digital gate-based quantum computers for building coherent quantum annealers. And so this is part of our motivation to take this avenue. So here comes the Abacus project. So this is the one that is going to lead these efforts to build these coherent quantum annealers. And I'm the coordinator from IFAI, and then there's some faces you may know. Juanjo García Ripoll from Madrid, from CSIC, is a theory collaborator. Martin Baides from Glasgow, Johan Pop, Karlsruhe, Nicola Rock from Grenoble in the Institute, NRS. Kilimanjaro is actually involved through Artur Garcia, in this case to do quantum algorithms, and HQS quantum simulations, also to provide quantum algorithms and quantum simulations, and Delft Circuits is a startup from Delft to develop cabling, cryogenic cabling. All right, so this is again a bit of a motivation that this project is relevant for us. Because since at least especially on the annealing side, but partly also on the gate base, that Europe is at a disadvantage with respect to North America and Asia in quantum computing, and in fact, quantum annealing could provide opportunities to be more competitive. And throughout the world, quantum annealing is not as widely pursued as the gate-based quantum computing. As I said, there needs to be more efforts being done, especially experimental. And then reiterate that this quantum annealing has a long-term direction to become a universal quantum computing, analog quantum computing approach. And then there's been no scale-up quantum speed-up yet demonstrated, and there's no besides Abacus, there's no other European project funded for quantum annealing. So what we are developing, because this project has been running now for 3 years, although we started right in the middle of the pandemic, so that caused some delays. But the idea is to build a few qubit prototype with coherent qubits, coherent flux qubits, and we study interactions that go beyond this Ising model. We increase the connectivity of this small qubit device, and then we implement algorithms that go beyond the standard quantum annealing, like diabatic quantum annealing, quantum simulations, and variational algorithms on this few qubit chip. We also are studying the effects of the coherence in quantum annealing, and where is the limit? So how many qubits do you need to achieve quantum advantage? These are all questions that are open, and we are studying them. And then we want to focus also on going beyond quantum annealing. This is also the part of the name of this project, which is basically on the quantum simulation and the variational quantum computing. And finally, we are developing a roadmap for scaling this technology, because in this project, it's a small project. Actually, it has another year to go, and we cannot build big systems. We are a bunch of academic groups, so we can propose methods and ingredients to go beyond this project and to build bigger systems, particularly for industrial partners, like for instance Kilimanjaro, which is basically what the company is doing, in fact. And this is a sketch of the project where the low-level part, the quantum processing units, are developed by IFAI, Karlsruhe, and Glasgow, and then the cabling by Delft, and the amplification by Grenoble, and then all the programmability is on the CSIC, Kilimanjaro, and HQS. So now let's start to focus on the technology, on the qubit technology we're developing, which is the key ingredient, is the first ingredient you need to start building these processors. And for that, we're gonna down select from the qubit types that we call the high impedance qubits and the low impedance flux qubits. So the low impedance flux qubits are the standard flux qubits that maybe some of you are familiar with, which is the so-called persistent current qubit, or the few junction flux qubits that were originally developed between Delft and MIT. And MIT actually pushed the technology further 6 or 7 years ago, when they came up with the capacitively shunted version, and they obtained coherence times which were on par with the Transmon planar geometries. But then there is the high impedance flux qubits, and these are also known as fluxonium qubits. Fluxonium qubits, they have basically a junction in a superconducting loop, and in the superconducting loop, the inductance, and therefore the impedance is very, very high. So the idea is to adapt the design of these fluxonium qubits and make flux qubits, because they are in fact, topologically, they are the same. They're a junction shunted by an inductance, but they're in a different parameter regime. And so the low impedance flux qubits, this is what we are working on in the PHI group. And the high impedance qubits is the developments of Johan Popp in Karlsruhe. And we are basically side by side working on these technologies in parallel to end up with a winning candidate, let's say. So I wanted to add a couple of slides on introducing flux qubits because it's quite relevant to understand why we're doing this. And I think by now it's maybe not so many people are familiar with flux qubits anymore. So it's good to remind people what they are. So the one I call the hydrogen atom flux qubit, that would be the radio frequency SQUID, which is essentially a loop, superconducting loop with a single junction, and then there's a magnetic flux threading this loop. And in a classical world, this loop behaves in the following way: by increasing the external flux, there's a current that is generated in the loop to screen the flux and keep the total number of flux quanta in the loop constant. That's because this is a superconducting system, and therefore the fluxoid number has to be an integer of 2 pi. And then depending on where you are in this flux parameter, the current might be parallel and add to the flux, or it might be anti-parallel and subtract to the flux to keep the total flux constant. But there is a maximum current that this loop can sustain, which is the critical current of the junction. So when you approach this critical current, then a new fluxoid number, let's say there's like a phase slip, and a new fluxoid enters the loop, and then the current becomes reversed, and then it starts again and over and over. So this is a classical picture. Of course, in reality, at this point, when there is this jump, the two classical states, they are degenerate. They have the same energy, and therefore quantum mechanical, they're actually coupled states, and they become superposition states, superposition of current states. In a circuit diagram, this is the kind of circuit we are dealing with, a junction shunted by an inductor. And there is this parameter, beta, that is historically used to characterize the circuit, even before the qubit era, which is the ratio of the geometric inductance, the shunts the junction, and the effective geometric Josephson inductance of the junction. And when this parameter is larger than 1, that's in the bistable regime, that's when the potential energy, and I'm drawing it here, has 2 minima. And particularly in the half flux quantum in the loop, the 2 minima are degenerate. And therefore, we are in this condition that I was describing here classically, where the 2 energies of the opposing currents coincide. So if you actually write down the potential energy of the circuit, you have the Josephson term, and then the parabolic term of the coming from the inductor. And I already included the fluxoid quantization in this term. And so you have 2 energy scales, the inductive energy and the Josephson energy, which appear also in this beta parameter. So if you have this Josephson energy dominate over the inductive energy, then you can get this double well potential. And the horizontal axis, I'm sorry, I forgot the label. The horizontal axis is the phase, is this variable phase, which is basically the phase across the junction. So if you have a phase, finite phase across a junction, that means there's a current through the first Josephson relation. And notice that these 2 minima, they are symmetric around 0. So that these 2 currents, they have the same magnitude and opposite direction. But there's this barrier in between. This is not infinitely high barrier. And these states, they are quantum states, and therefore the wave function, it can tunnel. And in fact, the two wells, they see each other. And so the actual eigenstates are superpositions of current states. And these are basically the persistent current states of the flux qubit. But to achieve this condition that the inductance in the loop is larger than the Josephson inductance, you need actually quite large loops, because this inductance needs to be on the range of nanohenries or tens of nanohenries. So if you take the standard materials we used for building superconducting qubits like aluminum, you need very large loops. So in the past, people basically, that's what they did. For instance, D-Wave, this is the qubits they have, and you know their qubits are like hundreds of microns large in size. So that's a problem, because that couples the loop size couples with local microscopic flux noise, and therefore this impacts coherence. So in the late 90s, this proposal came from between MIT and Delft to replace this inductor by two junctions, and that implied that you could shrink the size of the loop very significantly to just a few microns across. And then you obtain this kind of qubits. These are the persistent current qubits that basically they operate in a very similar way as the RF squid. The Hamiltonian is a bit more complex because now you have more than one degree of freedom, since you have more than one island. But you can anyway diagonalize this Hamiltonian, and this is what I did here. Very similar potential also at a half a flux quantum. And then the wave functions, they have this similar aspect than the ones I showed before. They are even and odd superpositions of the persistent current states. This design of flux qubits, this was, let's say, for some years, in the early 2000s, for some years, it was the most coherent qubit until people came up with the 3D transmons, and then the 2D transmons were improved, and so forth. But now there is news. I mean, the field has advanced, and this, let's say, small junction array can actually be replaced with actual inductors using superinductor materials. So now we can go back to the original RF squid, which only has one junction and an inductor. And that makes life a little easier because it has less, let's say, it's less complicated to fabricate. But of course, it has its own challenges because working with superinductors, which are disordered superconductors, is not straightforward. But it's definitely a way to go back to smaller loops. And that's basically what is being exploited in the KIT efforts in the high impedance qubits that I will not present here, but it's part of the development within this project. So just to conclude this introductory part of flux qubits, this is the actual energy spectrum. No, sorry, this is not the spectrum. These are the energy levels as a function of flux. And for standard parameters, you see that the lowest two states, they approach each other at half a flux quantum, and they're very far from the next level. And what matters here for quantum annealing, because that's what really we are interested in, is, I mean, flux qubits are good for digital gate-based quantum computing, but we are actually not interested in that. We want to use them for building quantum annealers. And in quantum annealers, you basically need a simulator of spin 1/2 particles. And a spin 1/2 particle, as you know, it has the degree of freedom of spin, the magnetic moment of spin, that couples to external magnetic fields. And in fact, it wants to align with the external magnetic field. So for a given direction of the magnetic field, the parallel configuration of the spin is the lowest energy state, while the antiparallel is the excited state of the spin. So if we reverse the direction of the magnetic field, the lowest energy configuration will also be reversed. Now, so you have two possibilities that your spin can point to in its lowest energy state, and this is for an isolated spin. Now, when you couple spins, the actual orientation of the spins, they depend on the coupling to the neighbors, if it is ferromagnetic or antiferromagnetic, so if they will be parallel or antiparallel, or if they will be frustrated, and then it is not easy to guess what is the direction of each one of the spins. And this is actually the core of quantum annealing. You want to measure where each spin is pointing. So you need a qubit that can emulate this kind of physics. And so the flux qubit, you can see it in this picture, the ground state energy changes the slope as you cross this symmetry point. And this horizontal axis is flux, this magnetic flux is the magnetic field. Therefore, by adjusting this magnetic field, we change the direction of the current, because the slope of this energy band is the persistent current in the qubit loop. So we can map the persistent current with the direction of the spin 1/2, and therefore we have a good emulator of a spin 1/2 particle. This is what you get in flux qubits. You don't get this with other types of superconducting qubit like transmons. So therefore, flux qubits are a key and necessary ingredient for building a quantum annealer. Now, this is what we have been doing so far. We have developed the first prototypes of these flux qubits. This device was designed by our group in IFAE, and the fabrication was carried out in the group of Martin Baides in the University of Glasgow. They have a subtractive process with 2 e-beam steps, and this is a zoom in of the device. This is a loop, and then we have a small junction here and 3 larger junctions. Then when you zoom out, you see that there is this pad. This is the capacitor pad that shunts the small junction to the ground. And then from the top, we have a readout resonator. This is the standard dispersive readout technique used in circuit QED, superconducting qubits. So we actually have a multi-qubit chip, but the qubits are isolated. Each qubit is coupled to its own readout resonator through a common fit line. And then we can actually make a spectroscopy of the entire chip. And this is what you see here, where we, on the horizontal axis, we change the current in our coil, and that basically changes the flux in the qubits. And then we scan in frequency through this central line. We measure transmission. And you see that there is some horizontal fringes that appear at specific frequencies, and that some signal is reproduced in flux. So each one of these lines corresponds to a resonator on the chip, and then these brighter spots, this is where the qubits cross the resonator resonantly. So we have six qubits and we have 6 resonances. So the whole chip works. But so we are going to focus only on one of these qubits. As we use zoom in, you get something like this. This is a body level crossing between the flux qubit and the resonator, and it is symmetric because the qubit spectrum is actually hyperbolic. And the splitting here is a few megahertz, is a bit lower than we designed, so we have to improve on that, but it's sufficient. And then once we have this picture, then we move to the 2-tone spectroscopy, and that's what you see on the right side, so that we obtain the qubit spectrum. For this device, the minimum energy splitting turned out quite low, much lower than we expected. So this is actually one of the first working prototypes. We've had several iterations to converge. So we still are improving on this. So this is not our final candidate, but nevertheless, they're working. And the qubits, actually, the latest design, they look like this rhombus. So this is a Manhattan style. Each corner has one of the junctions. So it's these 4 junctions. And then we've characterized the coherence of these qubits. The T1 is quite long, as expected for low gap flux qubits. And we measured with the stars point where we have been measuring. As we approach the 0.5 frustration, that's the symmetry point, we see that the average T1 is 30, 40 microseconds, is actually lower as we approach the symmetry point. This is expected, first of all, because that's where the qubit magnetic dipole moment increases. So it is expected that the T1 will drop. The double well in this potential, they become closer and closer to each other. So that means the tunneling or the scattering is stronger. But because of this small gap, we believe we also have thermal effects. So the T1 is also impaired by that. And then as you increase the as you move away from half a flux quantum, which corresponds to going up in the spectrum, at some point you're close to the resonator, which is about 7 gigahertz, and so the T1 starts to drop. And the values here we have done, we have calculated that they correspond to the expected Parcel limitation at this level of 25 microseconds. So the T1 values are very nice, but T2 is not as nice as expected because we have measured, you see the time scale here is only tens of nanoseconds. But this measurement has been done at high frequencies where the qubit is very sensitive to flux noise. We're now working hard to make these measurements at the symmetry point. It's not so easy because of the low frequencies, but we're working on that. But T2 is expected to monotonically increase as you approach the symmetry point if you are limited by flux noise. But of course, there's other sources of noise that could be a problem here. So we're still investigating that. So this is work in progress. Apart from these single qubit experiments, we've also been now already for some time developing couple qubit chips, and this is one of them, one of the devices we've been measuring. So following from the individual flux qubit designs, we moved to coupled qubits. As you see in this picture, we have a flux qubit shunted by a capacitor and another flux qubit shunted by its own capacitor. And then in between, we have an RF squid, which is basically a big loop with a small junction. And the squid is galvanically attached to the qubits. And this is to enhance the coupling between the two without going to very large loops. So this works for qubit numbers which are not too high, but it's not really the most scalable approach because of the crosstalk. But for this, we can definitely work with. And then each qubit has its own readout resonator. Both resonators are attached to the same feed line. And each loop has its own independent control of flux. And so this is a screenshot of the spectroscopy measurement, and where we can basically compensate the crosstalk between the lines and arbitrarily position the two qubits anywhere we want in flux and in frequency space. So this is the lower line is resonator 1, where the qubit 1 is coupled to. The upper line is resonator 2, where the qubit 2 is coupled to. And you see that because the avoided crossing is larger here. And then we can actually separate the two qubits, but we can also bring them into resonance. And that's how we are operating this chip. So we are currently characterizing the tunable coupling using the coupler loop. But again, this is also work in progress. And this, I should stress, is actually done through the Kilimanjaro team that we're working together to develop these quantum annealers. So this is as far as I'm going to tell you about quantum annealers. We are now in the process of coming down to a more optimal device between low impedance and high impedance qubits. And I didn't mention it, but we also are working on developing a readout that distinguishes the two current states, because the standard dispersive readout, it only tells you populations, but we need to distinguish current states in the ground state. And for that, we need a flux-sensitive readout that we're developing. We are making bigger chips with 4 qubits that I didn't mention. And then in the following year, we are going to start focusing also on capacitive couplings, tunable capacitive couplings between qubits to implement this beyond the Ising model. And then simultaneously, we are working on this flexible cabling by these Delft circuits. And at the same time, in parallel, developing these applications to be run on these chips. So let me completely jump and now talk about something else that we're working on, and I would like to use the opportunity to present to you, and hope you'll find this interesting, because this is done to improve our chips, but we believe it may be usable for the community. And so the first what I'm going to tell you about is on nitridized aluminum thin films. Is a paper that it's about to be accepted for a publication, and you can read it on the archive. It's been there since some months. So what we've done here is to actually spatter aluminum thin films, and then in the spattering process we've added nitrogen. So this is basically the same process that you do when you spatter niobium niobium titanium or titanium, and then you want to make nitrides out of them. So we're basically making aluminum nitride, but non-crystal aluminum nitride, because aluminum nitride is the electric is an actual piezoelectric. But we are interested, I mean, inspired by the success of niobium titanium nitride and titanium nitride. We wanted to study also superconducting aluminum nitride, and for that we needed to tune the nitrogen concentration in this sputtering process. So what we've done is to sweep the concentration, the relative concentration of nitrogen with respect to argon in the sputtering chamber, and we've characterized thin films. What I'm showing here first is the resistivity at room temperature of these films, and in the left, this is the reference of aluminum. So as soon as you start adding nitrogen, the resistivity goes up, because essentially you're introducing disorder. You're making your superconductor disordered, and for a range of percentages, you more or less get a plateau. But then at some point, the resistivity starts to increase. Notice this is a logarithmic scale, and then it exponentially diverges for large enough concentrations, and the material becomes insulating. In fact, when it becomes insulating, you can see it with your naked eye that it changes color. So you don't even have to measure it. You know that the 15% one is insulating, whereas the 11.7 is close, but is not yet insulating. And so then we characterized all these chips at low temperatures. And this is what we obtain. So for, I'm sorting them here by resistivity, but also by concentration. And I'm just going to comment the concentration one because it's easier to follow. As soon as you add nitrogen, the TC of the film increases very fast. And we measured peaks of about 3.5 kelvins for the 5% sample. I mean, I should state that this horizontal scale, this is basically calibrated for our setup. A different setup, these numbers will change slightly. I change by a few percent up and down. What really matters is the resistivity. So this is more or less a universal language. But for reference, I'm just quoting the percentage of nitrogen. So we get this peak of TC, and then as we increase the percentage of nitrogen, this peak drops, but kind of stays constant around 3 Kelvin, 3 or 2.5. And then it starts to drop very fast, even below the TC of aluminum. And the next sample, this is the 13%, the L is the 13%, and the next one is the 15%, which is already insulating, and it does not transition into the superconducting state. In fact, so I'm showing here, we've measured 2 different runs of fabrication of this 13% sample. In one of them, it became superconducting below 1 Kelvin. In the other run, it didn't become superconducting. So this transition to the insulating state is pretty close to this value of nitrogen. And here I'm showing the resistance versus temperature of different samples. So all these results are actually similar to what people have observed with granular aluminum, which is essentially oxidized aluminum. That there is this kind of like dome shape pattern of TC versus essentially resistivity. And what's different though with this material, with nitridized aluminum that we call nitrile, is the microscopic structure, because granular aluminum, is made of grains, and nitrile might not be made of grains. We actually are starting to image the films at the different regimes, and we don't see a very clear indication that this is granular. So this is work in progress, and now the next work we are going to produce will be related to the microscopic structure of the material. But as it is a disordered superconductor, we also wanted to demonstrate that it can survive under strong magnetic fields. And this is what we did. Actually, we used a setup by Professor Wolfgang Bernstorfer in Karlsruhe. We sent some samples and they characterize them in their setup, where they have basically two coils in the in-plane and out-of-plane components of your chip. And so they could characterize up to a Tesla that the sample, for instance, the 10% sample does not transition. And even the 6% at 1 Tesla, the 1.5 Tesla does not transition into the normal state. only when we increase the temperature close to the TC. For the in-plane component, it's a bit similar, although in that case, the setup is only limited to 0.1 Tesla. So we only see, we see aluminum as expected at 10 millitesla transitioning, but all the nitrile samples, only when we increase the temperature, we see them transitioning. So this is consistent with what people observe in disordered superconductors. And then finally, the property that I wanted to highlight is the inductance, so the kinetic inductance of these films, because again, as it is a disordered material, the kinetic inductance is also high, much higher than aluminum. And here, this is calculated, this is not measured, is a calculated value. Perhaps the right plot is more easy to follow because the kinetic inductance is expected to follow the resistivity. And indeed, we see in this log-log scale, we see a linear slope, and we reach values of hundreds of picohenries per square, which for the most, let's say, the samples closest to the insulating state. So this is basically what people call in the literature a superinductor. And with superinductors, you can make interesting circuits. You can build interesting circuits like fluxonium qubits, or you can also build parametric amplifiers. So it would be interesting to study such devices we're using this material, because in the end, the intrinsic losses have to do with microscopic properties of the material, and this one is a new material. So we're definitely going to explore that. In fact, in that direction, we have started making some superconducting resonators, lumped element and distributed resonators. And this is very preliminary data, but I just wanted to show you that we're working on it already. So this is our reference sample of aluminum for a lumped element device that we obtained internal quality factors of tens of thousands. This number has to be improved already for aluminum, but it's our first reference. And for nitrile is slightly higher, but it's basically similar to aluminum. So at least we see that we can make up to this value good resonators, but of course this is not a great value if you compare it to the high purity aluminum resonators. So we're working on it. This is just the first batch of samples that we fabricated. And finally, I wanted to talk about another material property that we've been studying, and it's very recently put on the archive, is about the magnetic penetration depth of aluminum, because this is a property that people, it comes from old days of superconductivity, and normally for qubit people, this is kind of like assumed, and not a lot of work is done in this direction anymore. But I would like to stress some properties that might be interesting. First of all, is about distinguishing between the two superconductivity types. So type 1 superconductors, that would be the first image. The coherence length is much larger than the penetration depth. In this case, the material becomes superconducting, and when you apply an external magnetic field, it stays fully superconducting until the highest field possible is attained, and the screening currents are too large and the system becomes normal. But in type 2 superconductors, where you have the penetration depth much bigger than the coherence length, there is an option, there's the possibility to allow magnetic flux through the sample in tubes of flux. And these are also known as vortices. And each vortex contains a quantum of flux. And this makes these materials attain much larger critical fields. And these are typically used in making magnets. In superconducting qubits, we are using thin films. And aluminum is actually type 1 superconductor when it is thick, when it's in the bulk. But when it is thin, it's actually type 2, because coherence length drops. It drops because of the, let's say, the mean free path of the electrons, which is related to coherence length, decreases, but also because the penetration depth increases a lot. And so at some point you cross this boundary between the two types of superconductivity, and you're led to aluminum type 2 with vortices. Okay, so we wanted to study where this transition happens, and then to study the penetration depth itself, because this penetration depth is necessary when you want to design circuits with high kinetic inductance, for instance. So what we've done is we followed two parallel methods. In one of them, we made lambda element resonators in which we could tune the inductance, particularly the kinetic inductance, by changing the thickness of the film, and then measuring resonance frequency and fitting this resonance frequency to simulations using Sonnet, and then extracting the value of this penetration depth. Then in parallel, we've used meanders, and we just measured resistance of these meanders at low temperatures. And there is a relationship for the dirty superconductors that we have here between the penetration depth and the resistivity close to the critical temperature. So with these two methods, we've actually compiled a bunch of data of different samples, and this is the result as a function of the thickness. So you see that for very low thicknesses, this penetration depth increases very rapidly. The thinnest samples we've made were of 25 nanometers, but you could certainly go lower. So the blue dots, these are resonators. The triangles, red triangles, these are thin films. They more or less agree. They scatter a bit. It's a bit difficult to make everything very systematic, but they follow the right trend. In these smaller plots, I wanted to highlight two things. The first is the kinetic inductance that we observe for these 25 nanometer samples. This is above 1 picohenry per square. So if we make these films thinner, you can actually get pure aluminum to be not a superinductor, but to have a significant inductance in its loop. And so this could be interesting for making high impedance devices. On the other hand, we have this discussion about where is this transition between type 1 and type 2 superconductivity in aluminum. So you see for the thickest samples, the values we measured, they're in the 50 nanometer, 55 nanometer range. They're approaching the bulk. The bulk aluminum is 50. So they're not there, but they're very, very close. And so what we did was to estimate, because we have not measured it yet, we are planning to do that, but we have estimated the value of the coherence length using different approaches that they are typically followed by the literature. And so with two different methods, we obtain a range of values of coherence length. Actually, this is we've refined this. This is not the most updated version, but we've refined this, and the values are closer to the upper range, so more like around 130, 140 nanometers. So that's where it could be that the aluminum changes superconductivity type. And then it means that for the thicker films, there's no vortices. I mean, in the surface of the film, of course, if you make a hole in your pattern, you will trap a vortex there. That will happen in any superconductivity type. But the vortices that are happening in the bulk of the material, the core is normal. So if this vortex moves, it can actually cause dissipation. And that's bad for flux qubits particularly. So that's why we are actually worrying about this. And we're trying to explore methods to decrease the number of vortices in our films. So in the last minute, I'm just going to very briefly flash the other project we're working on, which is together with the Canfranc Underground Lab in Spain. This is an underground laboratory which is in the Pyrenees, between the mountain range between Spain and France. This is a cross-section of the mountain, actually. And here, this vertical line marks where the border is. And so the lab is actually, they have different rooms. And in these rooms, they have basically labs. They've been running, this lab has existed for 40 years at least. But only in the last 2 decades, it has become let's say a serious lab where international experiments are being carried out. And we're interested in bringing qubits into this space to study the effect or the effect of the absence of cosmic radiation in the chips, because as it is known, it has been proven in the community that high energy radiation, ionizing radiation, can create quasiparticles and decohere the qubits. So we are collaborating with the CROSS project. This is led by Professor Andrea Giuliani from the Orsay University in Paris. And they have actually a dilution fridge that looks like this inside of this lab. And you see the mixing chamber. Below the mixing chamber, they have a ton of lead. This lead is used to screen radiation from the upper stages of the fridge, particularly the mixing chamber, where there is a lot of silver, and silver has very radioactive isotopes. And then the samples will go down here. So we have not started yet, but this project has been awarded by the Spanish ministry, and we are in the process of developing it. And what we've done in this direction, though, is to count muons, count cosmic muons. And this is a last interesting bit of information I'm going to share with you. It is we've basically mapped the angular distribution of muon flux. This is nothing new. It has already been, let's say, measured many, many times, but in the qubit community might not be known. And this is one direct consequence. So because of the thickness of the atmosphere, the muons, when they go through it, they decay. So if you look at the horizon, you see less muons. We've made this detector, which has two plastic scintillators. It's actually in the suitcase, it's very portable. And this allows us to measure in different directions. And so if you measure the flux directly above your head, you get the standard one, which is about 40 counts per minute in this detector that corresponds to 1 count per million per centimeter square. This is what we get at sea level. But then when you turn 90 degrees, this count rate drops by a factor of 4.5. So this means there is far less muons coming from both directions, in fact. But this means that you should position your chips vertical, so looking through the horizon. So this is universal for all flux qubit, for all superconducting qubit experiments. And we've actually made measurements even at shallow depths using our portable detector. We've gone to a subway station in Barcelona and in a road tunnel that are in a depth of about 100 meters, and we measure a drop of this count rate by a factor of 30 with respect to the surface. So this is the actual summary of the plots. So this is to say that in order to screen from cosmic radiation, maybe you don't need to go to underground labs, which are very there's very few in the world. They're very remote. But in the cities, we have a lot of structures that are already built, and you don't even need to go to the subway. You may even go to a sub-basement of a building to get already a shielding factor. For instance, in this, we went to the synchrotron that we have in Barcelona, which they have a order 10 meters of rock, and the muon flux dropped by a factor of 2. So if you want more details, you can also read this preprint we put out this year. And at the end of my talk, thank you very much for your attention, and I want to thank all my team in IFI, also the team at Kilimanjaro and the funding agencies. So thanks.
Thank you all. This is now open for questions. Any question from the audience?
Yes, I have a question. So, how did you measure the penetration depth of your sample?
Mm-hmm. How do we? So I couldn't get it.
Yeah. How did you measure the penetration depth of magnetic field in your sample?
How do we measure it?
Yes, how did you measure it?
Well, so the penetration depth, I went very fast because I didn't have too much time to stop on it. But the penetration depth is directly related to the kinetic inductance. It's basically the responsible of the kinetic inductance. So by measuring the kinetic inductance, you measure the penetration depth. So this is a general form, this first equation. But for thin films, this other equation is necessary because d is the thickness. So as d becomes smaller, you have this hyperbolic cotangent. So, but you can basically measure the kinetic inductance by measuring the resonance frequency of superconducting resonators, and then by using finite element simulators, we can get a good estimate of capacitance and geometric inductance, and so the remaining variable is the kinetic inductance. So this is one method, and the other method is directly measuring the resistance of these meander wires before they turn superconducting. And this resistivity is directly related to penetration depth through this equation. And this is the question is valid for disordered superconductors like thin film aluminum. So it's an estimate, but it's actually not a bad one. Yeah.
Okay, thank you.
So I should state that this is in this configuration, this penetration depth is the orthogonal penetration depth, because that's the one that you obtain in superconducting qubits, because the magnetic fields, I mean, they are basically entering your chip vertically. We're not considering in plane fields here. Yeah.
Okay, thank you.
Okay, so is there any other question? If not, let me ask some question.
Mm-hmm.
So since it is inhomogeneous superconductors,
yes,
internal Josephson junctions. So does it bother you for the future application of qubits or whatever you want to do?
Well, so the case of granular aluminum is basically, the model is exactly what you described, because they have aluminum grains that are surrounded by aluminum oxide, and each grain couples to each other by Josephson tunneling. So that the granular aluminum is well. Excuse me.
Hello.
So granular aluminum is well known to be modeled by a chain of junctions, but with nitridized aluminum, we still don't know if this model is also valid. I mean, there will certainly be some kind of tunneling, and that may lead to some kind of effective Josephson inductance of microscopic Josephson inductance in the material. But well, we have to study whether these
actually
losses.
the resistance variation as a function of temperature, you see a peak near the transition temperature.
Yes,
that is probably an indication of this presence of Josephson junctions also. There's a variation of TC, I think, that in general produces a peak there.
Yeah, so actually we see this peak only in a certain configuration of our 4 probes. So if we change the order of the probes, this peak disappears. So this basically tells us that we have disorder. We conclude
if you make the linear 4 probe, then you probably don't see it. But if you make van der Pol,
yeah, we make van der Pol.
Then you will see that.
But not with all the configuration of the 4 probes. Yeah. So this actually we comment this on the manuscript, that we actually found that by changing these in the van der Pol configuration, by changing the ordering of the probes, the peak disappears. So, but I would be happy if you
actually, we have done some measurements of superconductivity on cobalt disilicide.
Mm-hmm.
There we also have the grains inside, and we observed this sort of peak, and which you can actually model by considering a distribution of TCs also.
Yes.
Which may happen in the grainy systems.
Only in grainy systems?
In the grainy system, it is very likely to happen.
Uh-huh.
Because their different grains may have different transition temperatures.
Right.
In a particular combination of like, you can model it as a different parallel resistances.
Yes. So the information we have so far is that in nitridized aluminum, there's some kind of domains. It's not.
Right.
I don't know if we can call them grains, but I'm not the expert here. The fabrication is done by my collaborators in the Microelectronics Institute of Barcelona, and they're the ones that are doing all the imaging. And we're still discussing what the material is actually microscopically, and it definitely changes actually a lot from the low percentage of nitrogen to the high percentage of nitrogen. But it's interesting what you point out. Yeah.
So what
We
are also planning to make resonators with this cobalt disilicide. We haven't done that yet, but we are planning to do that.
What I am wondering is that if you have this grainy aluminum or whatever this nitridized aluminum, which has this kinetic inductance. So that kinetic inductance also contains the information of the Josephson coupling between the grains.
Yeah,
That might also have some, like we have LJ in case of this Josephson junction that we could make.
yes, I mean, if you model it in as a grainy structure, definitely, yes, I agree with you that there is this relationship. I didn't mention it, I went too fast, but all the samples are 100 nanometers thick. So we are now actually measuring thinner ones that where the kinetic inductance is much, much higher, actually, because here we only see high kinetic inductance in the samples that are very close to the insulating regime. But for thinner films, of course, you get more kinetic inductance, and we are now probing 25 nanometer samples, and they are more
High
inductive.
kinetic energy, kinetic inductance means your resonance frequency will decrease a little bit.
Can you repeat that? The kinetic inductance will decrease.
High kinetic energy inductance implies a lower resonance frequency, right?
Oh yeah. If you keep the same dimensions, correct. Yeah. Yes. So we have to take that into account. So what we are really interested is in the microscopic losses of the material when we have this high kinetic inductance, because that will tell you if this is going to be a good resonator or not. So this is what we are working on in parallel. Yeah. Because it's not
the coherence length of the aluminum nitride films, or?
Oh well, yeah, it's hundreds of nanometers. I mean,
how do you determine the coherence length?
Oh no. So coherent length. Sorry. No, coherent length. We have not measured it. No. We don't have values yet. We plan to
coherence length.
We plan to measure it with these high magnetic field setups, but we have not measured coherence length. Yeah, we have only estimated penetration depths, but not the coherence length. Yeah.
But in the plot, you have shown some coherence length also.
I know, but that was for aluminum. That was for pure aluminum. So here, yeah, for nitridized aluminum, I only showed this kinetic inductance, but these are calculated from the resistivity. But the coherence length I mentioned, this is here. This is for pure aluminum. There is no nitrogen here. This is for just pure aluminum.
Okay, because for grainy system, it's very difficult to determine the coherence length. For aluminum, you can directly determine from HC, critical field at 0 temperature. But that Landau-Ginzburg theory you can apply.
Yes.
But for a grainy system, you have to use a modified Landau-Ginzburg theory. So it's not straightforward to determine the coherence length.
Yeah, we're currently investigating that, how to get this value. That's why we have not done it, and also because it requires high magnetic fields that we don't have available in our lab. So we're collaborating with another lab where they can do these measurements. But we need to measure C2. Yeah.
I have one more question. Why do you use 4 Josephson junctions in the qubit? Any particular reason?
Well, so originally the first proposal was with 2 junctions, because this gives you this kind of potential that you have
three junctions. That is right.
Yeah, that would be the 3-junction qubit. The 4-junction qubit is a variation of the 3-junction qubit, and this is inherited by when we were doing these qubits with the Dolan bridge technique, because there you always have an even number of junctions. With the Dolan bridge, the shadow evaporation using the Dolan bridge, you always have an even number of junctions. There is always, even if you don't design it, there's always a parasitic one. So we basically design the circuits with 4 junctions. But with this subtractive process, actually you can go back to 3. In fact, 3 give you a little bit more flexibility, because the values of this smaller junction that lead to this double wall potential, it's a bigger range. If you put 3 big junctions, like I'm showing here in the picture, the range of values of this alpha where you get the double wall potential is reduced. So it's you have to fine tune it a little more. Yeah. But we do have samples that I'm not showing here where the small junction is actually a squid loop, and then you can tune it in situ. And this is a way to adjust and bring the qubit to the double while regime. This is something that is still too premature for me to show you here, but we're working on it.
Okay, we have also come to the end of this time. So thank you, Paul, once again.
Thank you for the invitation again.
So the next speaker of this session is Dr. Arthur Garcia Saez, and he's a leading researcher at the Barcelona Supercomputing Center, Barcelona. He works on optimization problems and machine learning applications. He's also co-founder and chief software architect of Kilimanjaro Quantum Tech. The title of his talk is Large-Scale Simulation of Quantum Systems.
Hi, everyone. I'm Artur. Thanks for the invitation and the presentation. Can you hear me well?
Yeah, you can start.
Okay, I'll start sharing the screen. And now I hope it's in full screen mode.
Yes.
Okay, good. Excellent. So I'm Artur Garcia. I'm like a group manager of the quantum computing effort at the BSc, at the Barcelona Supercomputing Center, which is the national supercomputing lab in Spain. And I'm also a co-founder of Kilimanjaro Quantum Tech, where we make use of some of the technologies that we develop at BSc and other institutions into the construction of a quantum annealer. But what I want to explain today is it's a very different topic, rather different from the previous speakers as well. But I think it's also very important to have the perspective of current state of the art of the simulation and capabilities of large supercomputers in order to simulate quantum circuits. I will be a little bit technical in order to explain how do we do these simulations, but then at the end I will introduce some applications and results that we already have with these methods. So, okay, so let me just introduce my research group. We are a team of physicists and computer scientists devoted to the development of quantum algorithms for scientific applications. So we've been working in different problems related to optimization of quantum systems, such as quantum chemistry or nuclear physics. And we believe that the short-term applications of quantum computation will be really hard scientific problems based on a quantum formulation. In order to advance our research, we develop simulation tools, and these are tuned in order to work in a supercomputer. And by that, I mean like pre-exascale systems, such as the top 10 supercomputers in the world. This is very, very useful at this moment when we have real quantum computers that have some noise issues and scalability limitations. And having a fully fledged quantum simulator allows us to test these quantum algorithms in ideal conditions. As a quantum group, we also provide like a consulting information to the capabilities of current quantum technologies, and this is very important for a supercomputing center like this BSc and other supercomputing centers that quite recently joined the effort of the quantum computing community. So for these institutions, they are typically used to develop and install different technologies, typically classical technologies, but with the appearance of quantum systems and quantum computers, we need to be very aware of which are the capabilities and future trends of this field in order to decide which systems will be installed in the center in the future. So the main task that we do is to develop simulator tools and then run these on our own supercomputers at the Barcelona Supercomputing Center. And the main tool that we use for these simulations is a mathematical structure called tensor networks. I'll be discussing how we manage tensor networks in a supercomputer in the following slides, but let me just mention here that tensor networks, once you codify your quantum problem into a tensor network, it may be seen as an efficient representation. So storing all this information is not it's not a storage problem, but it's like a computational problem, classical computational problem that consumes a lot of supercomputing resources. HPC stands for high performance computing. So that means like large amount of nodes working together to solve a particular mathematical problem. But once we manage to manipulate these structures, then we have a totally equivalent result to those of the real quantum devices. So these are, let's say, state-of-the-art techniques for quantum simulation. And at the end of the day, as a research group, this means that we have fully working noiseless quantum computers. The good thing about tensor networks is that they also are able to manage noise situations with only a quadratic overhead. So it's not like a very different scenario for simulating the noiseless and noisy quantum computers. So we, as a research group, we collaborate with a large number of external collaborators, and our strategy is to have real experts on domain problems that we want to test the quantum capabilities that we develop. And for that, we have a large number of collaborations with other institutions and companies that are experts on different domains. And for that, we work together, we set up the quantum simulation, and they provide information about the particular scientific problem. And for that, we have joined efforts with some companies in order to state chemical reactions, or to, I will be talking in the final section of my talk about the nuclear structure. And also we have developed methods in order to identify strange situations in experiments on high energy physics that may lead to the discovery of new physics. And also, and these are mostly quantum problems. And I would say we expect to have quantum advantage on these quantum problems first, but also we keep an eye on classical applications of these methods. And that means, for instance, image processing, as the picture that I'm showing here. And we have an ongoing project where we are actually processing medical images with quantum circuits and quantum and tensor network techniques. So let me discuss a little bit about these tensor networks. And these are the central tools that we use in order to make our simulations in the supercomputer. So the first thing we have to notice is, of course, that these simulations are hard. Simulating a quantum system is exponentially hard with the size of this system. And the reason is that the Hilbert space grows exponentially with the number of qubits. Okay, so once you have around 50-something qubits, the memory requirements to store the full state vector goes to the petabytes. So that's on the limit of what a modern supercomputer can handle. So we clearly need a different approach to the simulation problem. Otherwise, we are always bounded and limited by this memory explosion. Okay. But actually, we are very interested in solving this problem computationally on a classical supercomputer, because having a quality quantum simulator allows you to test most of the ideas that we develop when we design quantum algorithms. And this is an important thing, because many of the ideas currently developed are based on heuristics that should be tested. And without testing them and putting them into practice and improving them, it's very difficult to advance approximations and new heuristics for these novel quantum algorithms. Besides that, it's interesting to understand that simulating a quantum system allows you to also simulate more like larger systems where this quantum system is just a part of. For instance, you can imagine a classical quantum approach, a hybrid approach, where you have two devices working together, and then you need to simulate the quantum side, while you already have the classical part working. So what we are going to do is to start from a quantum circuit. Let's say that you have a quantum device, and then you have a schematic of this quantum circuit. And then from there, it's trivial to obtain this mathematical structure such as a tensor network that will describe exactly, without any approximation, the structure of the quantum circuit. So this step, moving from the quantum circuit to the tensor network, is trivial, and it's very efficient, let's say. So at the end of this process, you start with the quantum circuit, you end up with the tensor network that codifies this quantum circuit. So now all the operations are going to happen over this structure, over this tensor network. And given some process of manipulating this tensor network, at the end of this process, what we find is that the probabilities that we obtain for some measurements at the end of this quantum circuit are exactly equivalent to the ones that we can obtain from running the quantum hardware. And actually, tensor networks are very efficient in order to compute expectation values of local operators. So having this representation and looking for a particular measurement result, it's very, very convenient using the tensor network approach. The interesting thing from my point of view, which is from a supercomputing center, is that manipulating these structures, these mathematical structures on a supercomputer is very handy because some of the operations can be easily parallelized and done in different nodes at the same time. So this means like a huge speed up of the computation. And by this, we mean that we are going to manipulate very large tensor network structures that will fit into these exascale systems, which are the currently top supercomputers in the world at this moment. So as I was mentioning, we start from the circuit. I'm using here as a reference the circuit that was used by Google on the 2019 experiment. And then from here, you obtain a completely equivalent tensor network structure that you can see on the right. So once we want to obtain the outcoming probabilities of this quantum circuit, we have to perform what is called the contraction of this tensor network. And this is a totally equivalent operation as to run the experiment, the quantum experiment, many, many times. The problem is, of course, that this is not like an easy problem, and this computationally may be very, very hard, even having this efficient representation in the form of tensor network. So either you have a very powerful computer that will handle exactly these computations, or you will require to perform some approximations. And this I may discuss afterwards, but actually tensor networks are very also convenient to perform these approximations. So the process that we follow is the following. You start with the circuit, you create this tensor network, and then you need to decide which is the path or the order of operations that you are going to perform in order to contract this tensor network. And by that, I mean you take two neighboring tensors, which is like two of these small balls that are joined by this link, and decide that, and this operation is totally equivalent to a matrix multiplication. So at the end of the day, performing a contraction of a tensor network is totally equivalent as to perform a lot of matrix multiplications. And the problem is that depending on the order that you choose in order to perform all these matrix multiplications, the problem may be easier or harder. So computing the correct or the optimal order is very important for being able to perform this simulation. The problem is also that finding the optimal order is also a hard problem. So we have two hard problems here. The first one is to find the optimal order, and then to perform the operations in this optimal order is also a hard problem. However, if we are able to find good solutions with heuristics or with other methods, this operation can be done in a supercomputer. And this is what we are actually doing. So what you first do is to compute this optimal order, meaning provide a list of all the tensors that will be operated on and on which order. Of course, many of these operations at the beginning can be done in parallel. And then as a result of these operations, you will be creating intermediate tensors that can be very, very large. And this is, let's say, the bottleneck of this contraction operation. Sorry. So once you have computed the order, then you execute the contraction. And then this can be done, as I was mentioning, in a supercomputer. And then depending on the outcome that you are trying to simulate, you can perform some sampling over this final structure, or you can directly compute expectation values of these local operators. So, as I was mentioning, finding this optimal order is a hard problem. It's actually an NP hard problem. And then what we are mostly doing is use suboptimal contraction strategies. And the reason is the following. We can find very good contraction strategies without providing the optimal one, but being very close to the optimal one, but using a much less computational effort, using good heuristics. So we typically rely on these heuristics in order to provide a so good approximation that we don't care if we are not sitting on the optimal structure. And then we are going to perform this exact contraction of the tensor network. And then if we are not able to perform the contraction, because even with a supercomputer, some of these tensors may be too large, what we can do is to reduce the size of these tensors with some approximations that are based on properties of the tensors. So this is, we understand very well how to do it. And it's possible that even with a very high degree of approximation, you can still get very, very good results. And then from the computational side, the advantage is that most of these operations are linear algebra operations, matrix, and matrix vector operations, meaning that actually they can be boosted by using GPUs. And so once you are sitting on a single node operation, you can decide who is going to do this operation. And of course, using GPUs helps a lot here in this scenario. So what we are going to do is to create a library, or we have actually created a number of libraries in order to perform these operations, because each of these contractions of two tensors is going to be transformed into a task. And this, we are going to rely on a task scheduling library to organize all the execution of the full contraction of the tensor network. And then this task scheduler, and there are different frameworks that can be used for the user, will allow you also to decide at the level of a single node who inside this node is going to perform this operation. So once we have computed the optimal path, what we find is a strategy like this. Each of these nodes, this is like a graph dependency tree. And then what we have here is a number of tasks that will be performing operations over different nodes. And as you can see, there are no data dependency over the first row of tasks that can be executed completely in parallel. But once we start having dependencies, some of the operations will have to wait until the previous ones are finished. And so you end up with a tree structure where at some moment, some of these tasks will involve a very reduced amount of tensors, but of a very large size. And once you have computed these contractions, then at the end, this final operation will execute and deliver the result. So this is a very good analysis of the parallelization capabilities of these tensor network operations before we actually perform the execution. And this is the outcome of the optimization of the optimal path for the contraction. So the tensors themselves are multidimensional structures. So they are very similar to matrices, but they can be very, very large. So inside of this mathematical structure, we have a large collection of numbers indexed by a collection of indices. Okay, so the idea is that we are going to use these tensors that can be very, very large. And once they are so large that they don't fit the memory of a single node in a supercomputer, they are going to be separated in different blocks. Once we have these different blocks, we have to design all the operations that will be performed over one of these single tensors to be a combination of operations that will be operating on different blocks of this tensor. And each of these blocks should fit the memory of a single node because the operations will happen on the single node domain. So the approach that we are going to be using in order to describe the typical operation of a contraction of two tensors is to take this with some arbitrary indices. And in these pictures, these are three-dimensional tensors. So you may imagine this as a sort of matrix multiplication. And of course, the outcome of this is also a matrix. Okay, but this will depend on the number of nodes. And depending on the circuit that you want to simulate, the tensors that will appear along the contraction may have different number of dimensions. So your approach should be like flexible enough in order to handle any kind of tensors. So once you have these, you can identify that there are some indices that will disappear because of the contraction. And at the end, the outcome will have only the open indices, these J and M. Okay? So at the end, we're going to perform a lot of contractions over this dimension, I and K, that are the ones we have used in order to separate in blocks these two structures. So what we are going to first identify is that actually by operating this region here of this first tensor and this region here of the second tensor will only provide results that belong to this region here. Okay, so this is the locality we are looking for once we want to truncate the problem into smaller subproblems in order to perform these very large contractions. You have to imagine that the memory requirements for some of these tensors may be of the order of hundreds or tens of hundreds of petabytes. So these are very, very large tensors, and the number of blocks will be also very, very large. But the good thing is that only by using some sections of these, some blocks of these tensors, we compute local regions of the final result. Actually, this process can be nested into smaller and smaller blocks in order to provide the final solution as a combination of operations that will happen only on the corresponding color blocks that I'm showing here. So all these color blocks will interact with the corresponding colors on the other tensor, and then will deliver the final result in this final region here. So let's take the sub blocks here. You can see, for instance, these magenta ones, and operate at this level only. And you will see that actually this nesting of operations is actually like a fractal structure. And so operating on these small blocks will deliver a small component of the final result. And the good thing is that this can be done very, very fast, even at the GPU level, if you manage to have these blocks small enough that they will fit into the GPU memory. So this is a matrix multiplication. So once we have an n-dimensional tensor, we can always reshape this tensor into a matrix form. And this allows us to use like already dedicated operations for matrix multiplication. And this is also like a very, very important advantage, because there are very powerful libraries that will handle this matrix multiplication for the user. So you don't have to go and codify at this level, which is the best approach numerically. But once you are able to determine that these structures have like the memory capabilities for fitting into a GPU, you will take the full advantage of using these accelerations in your construction method. So as I was saying, we can operate over a particular region by selecting a combination of blocks that will be operated pairwise, and then combine together into a final operation that will take all these results, partial results, into a single one. So this is a gathering operation that will take all these results that have been obtained potentially in parallel in different nodes of the supercomputer, and then brought together into this single region by just summing all these terms into a collective sum. So this will provide, you repeat this for each of the blocks of the resulting tensor, and then you obtain in a parallel way the contraction of these two large tensors. And this is the cornerstone of the method, the tensor network methods approach in supercomputers, just truncating and separating in blocks all these tensors and computing them in parallel. So once you have to perform this final construction, just let me mention that there are many different strategies, and actually each library should determine which is the more convenient approach for different systems, because you can have like sequential combination of these different blocks. Let me go back. You can combine these sequentially over the same region of memory and be adding over here, or you can perform a commutative operation and bring together all these different partial results into a single result by a combination of commutative tasks that can be performed in any order. So the two approaches are not equivalent. And actually, this is important that you go and measure in your supercomputer which one is the most favorable one. And also depending on the block size. And this is also something that is worth mentioning. All these truncations depend a lot on the memory and also the connectivity of your network. And this will have to be determined for each of the systems in order to assess which is the optimal block size for each tensor network contraction. This is something that we really like a lot. This is how we see that actually our parallelization efforts are working very well. So this graph was actually giving the information of, on each of these lines, these pixel lines, what you see is that if there is a color, that means that the worker, because each of these lines means a different worker that is performing contractions. So whenever we see colors, that means that the worker is busy doing operations. And whenever we see black regions, that means that the worker is idle, waiting for some results from other nodes in order to proceed with the following operations. And when we see a lot of color here, broadly speaking, that means that actually every worker is busy doing operations all the time, meaning that we actually obtain a huge gain in the parallelization effort in order to boost all these tensor network contractions. And we can measure these also with the total CPU consumption that we see in this curve here along the time of the contraction. There are some kinks here when the scheduler gets, let's say, too busy to deliver the tasks to different computing nodes, but at some moments we reach 100% efficiency of the contraction operation. So all these efforts have led to the production of a library that we deliver open source in our GitHub repository of the group at the BSc. This library is called Tenet, and has a number of auxiliary libraries that will allow you to take your quantum circuit, convert it into a tensor network, and then perform all these operations into your local system, or even worse, even better, I would say, on a supercomputer. The library is written in Julia. It's still under development, but it's been optimized for different architectures, such like the Intel architecture or the ARM. And it's capable of handle a large number of nodes and perform these contractions for large quantum circuits. So I invite you to just download it and test it. It's, as I mentioned, it's still under development, but you can also reach us and we can help with the issues that you may have. So in this final section of my talk, I want to discuss applications of all these simulation capabilities that we have at the Supercomputing Center. And the main reason is that having this simulator, we then are able to perform development of quantum algorithms and then put them into test with these simulations. So I want to mention a project that we've been working in collaboration with researchers at Universitat of Barcelona, also in Spain, and focusing on a particular scientific problem called the nuclear shell model. So once you want to describe the internal structure of the nucleus, there is an approach called the shell model, for which you identify some degrees of freedom, some fermionic degrees of freedom, that will describe the interaction between nucleons inside this nuclei, namely the protons and neutrons. But this doesn't include all the protons and nucleons for a particular isotope, but this will include the interacting protons and neutrons above a closed shell, for which all these protons and neutrons don't have any effective contribution to the different levels of energy of the system. This means, in other words, that we have a number of fermionic degrees of freedom that can be occupied by two different species, protons and neutrons, according to a Hamiltonian, which is an effective Hamiltonian that has this structure, which is a very well-known structure of a fermionic Hamiltonian. And these coefficients will be determined by the interactions that you have among different shells of this energetic structure. So basically, this means that you have some shells, some different energy levels on which you can put all these different particles according to this Hamiltonian and the fermionic rules of commutation. So it's important to notice that there is interaction between neutrons and protons, but the interaction will depend strongly on the particles and the positions in this model. So it's quite different from a lattice model or some model similar like the Fermi-Hubbard, because all these coefficients will have a close connection to the physical structure of this nuclei and will be different for every different system. So what we have here is this is the structure and the number of nucleus that we are going to study with the tensor network methods. And here you can identify for a given proton number the different isotopes that you can have for different neutron numbers. The shell structure that we are going to use, identifying also different levels like this P, SD, or the PF layers. And from here, what we can start to observe is actually what we already know, is that the Hilbert space grows a lot by adding levels into this shell structure. So of course, we are facing a problem which is hard and has been like developed in nuclear physics for some years. Our approach is based on quantum computers, and we assume that actually quantum computers are going to be very good at solving these kind of Hamiltonians. We know that because we don't have to put some effort into the codification of the problem. We already have good tools in order to describe the system, but we have to assess or identify what the amount of resources that we're going to require in order to provide good solutions to this Hamiltonian problem. So let me stop for a second and mention the numerical method that we are going to use. And this is a variation of a family of quantum algorithms called variational quantum eigensolvers. And in particular, this one is called ADAPT, BQE. So this is for an adaptive method of these variational quantum eigensolvers that is especially devoted to solve fermionic systems with some properties. So as you may know, variational methods have been extensively proposed in the last years as a good tool for small-scale quantum computers that are classically optimized in order to deliver solutions to energy problems, minimization problems of the energy. So you have a quantum system that will evaluate the energy after the generation of these of a number of states with a quantum circuit. And this quantum circuit is optimized by classical means in order to deliver a subfamily of states that will minimize a target energy. So this is a very nice approach, but it raises some difficulties. For instance, how you design this variational quantum circuit such that the outcomes of this circuit are good candidates to be the ground state energies of the Hamiltonian problem. So the ADAPT-PQE proposes a consistent approach to this by having some insight into the states that you want to create with this variational method. And the idea is that for fermionic problems, and in particular in quantum chemistry, where this method was originally proposed, you typically have a structure of the wave function that can be described as an initial wave function, which is very well known. This is the Hartree-Fock wave function, modified by the action of some collection of operators. And these operators can be selected among a very large family, but there are physical reasons to believe that actually this is a very, very good approach. We choose these T1 and T2 operators to be excitation operators of a 2 and 1 and 2 body terms. So this unitary coupled cluster with single and double excitations should be created like this. We start with the Hartree-Fock quantum state that we know how to create this on a quantum computer. And then on top of that, you apply a collection, a very large collection of operators of this form in order to create a very good representation of the full configuration interaction, which is the true ground state of this chemical system or the nuclear system. So this is a very elegant and interesting approach based on physical properties. The problem is that this collection of operators is very, very large. And this means that actually to efficiently create this final state is going to be very hard. And this is where the ADAPT-PQE method appears, because we first of all can notice or identify that actually all these contributions to the from these operators to the final structure of this full configuration interaction state are not totally equivalent. All these contributions are not equally relevant. So what ADAPT-PQE is going to do is to choose a particular number of all these large collection of operators, just a subsection or subselection of these operators, in order to choose to create a very good approximation of these without having to pay the price of applying this very large collection of operators. So in other words, at each step of the algorithm, what we are going to do is to identify among all these operators in a collection or a pool of operators, which are the ones that have a largest contribution at each moment to the final energy ground state. Considering that we are performing operations over the initial Hartree-Fock state. So basically, in an adaptive way, we are creating a quantum circuit, and each layer of the quantum circuit will be one of these operators that will be contributing the most to the final creation of this full configuration interaction. At some moment of this iterative process, we can stop and with a polynomial number of terms, create a very good representation of this state without the large collection of operators. So let's take this method and apply it to the Hamiltonian that I showed for the nuclear shell model. And what we can see here is that by adding more and more operators on this adaptive process, what we can create is a very good approximation of the ground state. So what you see here is that the error that we have when we compare our results of the energy with the true energy of the system that we are optimizing to, meaning that actually the error can be very, very small for different isotopes and different species of atomic nuclei. So this is very good news, meaning that actually with a reduced number of layers, we can already provide very good approximations to the ground state of these systems, meaning the equilibrium structures of these nuclei. And also we can count the number of gates that we require in order to obtain this state, because each of these operators, let me go back, has to be decomposed into a collection of single and 2-qubit operations on your quantum circuit in order to be able to create this final state as a quantum circuit. So once we have that, we can see that actually some of the nuclei are harder than others in order to be prepared. Of course, the number of particles is an important issue here, but the scaling of this number of CNOT operations, which are, let's say, the hard ones for a quantum computer, or at least in a simulation, a quantum simulation, this number doesn't increases dramatically, and actually for a bounded or a linear progress, you can already find very, very good approximations of the energy of this ground state. So we can also perform additional analysis on what are the structures, the physical structure of the solution that we obtain. And for that, we use entanglement. We can use entanglement theory in order to see, for a particular degree of freedom of the system, how the system is coupled with the rest of the system. And what we can see is actually that our method clearly at the very first stages already identifies that some of the orbitals, meaning these different labels, already get saturated for a fixed number of correlations with the rest of the system, while the energy or the error is still improving along the evolution. So at the end of this process, what we obtain is the adaptive VQE will deliver a recipe for creating a quantum circuit where each of these huge blocks is one of those excitation operators that we add into the Hartree-Fock state that is prepared here initially. And these are swap operations in order to bring together the degrees of freedom that have to be operated in these huge blocks. So each of these blocks will have some dependency on parameters that will have to be tuned by this variational process. So these are classically tuned. But at the end of the day, you get the recipe for this particular quantum circuit in order to create the ground state of this nuclear shell model describing a particular nuclei. And in this case, this is oxygen. But for each of the problems, you will find a similar structure, a different one, because the optimization may have different results. But this will allow you to create in a quantum computer the states that you are targeting to. Once you have this state, then you can perform additional measurements over these states in order to understand the physical properties of these systems. And this is what we believe is one of the strengths of the quantum computer, to have an efficient representation of a particular quantum system that you can create in the lab and then use it to study and develop new physics. For instance, once you have created this state, then you can apply a real-time evolution of this system in order to understand, for instance, dynamics and dynamical properties of this system on the quantum system. So just to start finishing, let me also give an additional step into applying quantum information tools to understand nuclei properties. And the idea is that we can use entanglement theory in order to understand how these different degrees of freedom are related after the interaction of these neutrons and protons through the shell model Hamiltonian. The interesting thing is that this analysis can be done once we have obtained the ground state by the means of the adaptive VQE method that I just explained. So this is one of the outcomes of having a good representation in terms of efficient quantum circuit to create these states. So what we show here is the correlations as measured by the von Neumann entropy between different degrees of freedom of this shell model system. And what I'm showing here is that, so you can, for instance, identify these are 3 blocks referring to different isotopes of beryllium. And each of these blocks is divided in subblocks. And for instance, what I'm showing here is that these are the correlation properties among all the protons among themselves. So these are the degrees of freedom that I label in the shell model as occupied by protons. This other block is the similar thing for only neutron interaction, neutron-neutron interaction. And then these other blocks refer to the cross interactions between protons and neutrons. So, and then we perform this study for the outcome of the optimization for different Hamiltonians, referring to these different isotopes of beryllium. And we can start doing some physics here and observe that actually the entanglement properties of these different isotopes are very different depending on the number of neutrons that are present in this shell model. So what you can see here is that by staying on the beryllium, by increasing the number of neutrons, so meaning like heavier isotopes, the correlations between protons and neutrons among themselves become stronger. And in particular, the proton-proton interaction become very, very strong, while the interactions between neutrons and protons become negligible. So this is a quite surprising result from the point of view of nuclear physics, because you wouldn't expect this directly from the structure of the nuclear shell model Hamiltonian. Quite the opposite, actually. So and this analysis can be done for other species. For instance, this is neon for different numbers of for different quantities of neutrons as well, and you can see a similar behavior here. So by adding neutrons into different nuclei of neon, you can see that actually the strength of the correlations among protons and neutrons among themselves gets larger and larger, while some features of this interaction disappear, as you can imagine, because of monogamy of the quantum correlations between different components in a closed system. So for us, this is an interesting feature to start the development of novel algorithms that may take advantage of these entanglement properties, because there is a strong correlation between the entanglement properties of a system and also the simulation capabilities that we may have with tensor network methods or similar methods that can be run classically. So I'll be finishing with just some observations. First of all, I'm a strong supporter of the use of supercomputers as a tool for quantum computation, at least at this moment. Let's say that in some years, quantum computers may be less noisy, more precise, much larger, and then supercomputers may not be able to provide any contribution for very large simulations. But at this moment, I would say that these are a very, very useful tool in order to assess the capabilities also of quantum computers, but also to obtain results from novel quantum algorithms. In order to do so, we've been manipulating these tensor network structures that we and actually the community believes is the right approach in order to perform these simulations. And the best results for quantum simulations are obtained currently with these tensor network methods, which allows to run large simulations of quantum circuits, either exact or in an approximate way. So that means that we can relax some of these operations that I've been mentioning in order to obtain an approximation contraction of the tensor network that will allow you to reach larger systems. So that means that you can reach hundreds of qubit simulations with some error. And this error will be larger or smaller depending on the system capabilities or properties. So from here, we have shown that using these quantum algorithms for analyzing fermionic systems, we can obtain information about fermionic problems in nuclear physics using this nuclear shell model description of the nuclear structure. And from these optimizations of these fermionic problems, we can observe that actually the entanglement properties have interesting features depending on the number of neutrons. And there is a potential structure that we may exploit in order to find better algorithms for simulating these nuclear systems. And with this, I just finished my talk here. I hope you have many questions. Thanks a lot.
All right, thank you. The talk is now open for questions or comments. Anybody would like to ask questions?
Yes.
Bhanu, go ahead.
Yes, this is Bhanu Das. Yeah, I have a lot of questions, but I'll just ask a few, and maybe we can continue this sometime later. Could you please show the slide optimization of the nuclear shell model? That slide, I think we had the couple plus. No, maybe okay. Yeah, the next one. Yeah, right.
This one?
Okay. Yeah. Yes, I can see that you've used adapt VQE, but you probably have used tensor networks here, but that's not too evident to me. Has it been used, tensor networks?
Yes. So let me explain.
Yeah. Sorry, please.
At this moment, this is just a description of the algorithm.
Right.
And let's say that from this description, what I obtain is a collection of operators and quantum states that I need to combine. Then let me just go to here. This will help a lot to explain this. So let's say that you have this quantum circuit. And then the adapt VQE will tell you how to decide which blocks you apply here. And then which are the parameters that you have to put into these blocks. So your final goal is to design this quantum circuit. But the requirement in order to perform the optimization is that you have to evaluate the energy, the Hamiltonian, of this quantum circuit every time in order to decide which is the next step of the optimization. And this is a complex task. And this is where we use tensor networks. Because evaluating these quantum circuits, when they are small, can be done with the state vector approach. But when they are large, you require other numerical methods. Because all the results that I'm showing are performed by simulations. There are no real quantum hardware involved here. And so let's say that the tensor network is a tool in order to obtain the energy that you can compute from this quantum circuit and the collection of expectation values that you need from the Hamiltonian in order to evaluate the energy. And this is a problem for which tensor networks are very good.
Okay. So after you've got the circuit, you do the you run this on a hardware then.
Exactly.
Okay. I see. Okay. Now the entanglement part, have you been able to, maybe you said this, but I didn't fully understand. Have you been able to identify which entanglements are important?
You mean, for instance, like multipartite entanglement or like structures like this?
Yes.
So what we measure here is just two orbital coupling, and this already gives a lot of considerable amount of correlations inside the system. So we actually believe that most of the correlations present here, not all of them, but most of the correlations, depending on the isotope, correspond to proton-proton or neutron-neutron interactions.
Yeah, see, the correlations are sort of related to entanglement. The more the correlation, more the entanglement, isn't it? So from that point of view, you'd expect that quantum computers would be better suited for,
exactly.
Yes, for computations that are entangled.
Exactly. The interesting observation is that quantum computers may be very useful to solve this part of the problem. Because there are regions where you don't have correlations.
Yes.
And then you could assume that then these regions are not that hard for the computational method.
Yeah. Right. You did mention about dynamics, that is the time evolution of systems. Of course, you did mention it. That so suppose if you take particles in a lattice and you look for time evolution, how efficient would it be on present day digital quantum computers? If you want to take something like 100 lattice sites.
It's a good question, because for the classical methods, this is the hard problem. So let's say that I may use tensor networks for solving this energy problem, and for that I may have some numerical difficulties. But let's say that the structure, the physical structure that I'm describing with the tensor network is very well matched, let's say. And so finding ground states with tensor network methods is a very, for this problem, is a very good tool. However, real-time evolution of quantum systems is very difficult for a tensor network. So let's say that from this circuit, let me just move a little bit. Let's say that from this we obtain like static properties of a quantum system. So we obtain the final ground state and so on. You could plug here a collection of gates that will mimic the real-time evolution, a collection of unitary operations that will mean how this Hamiltonian makes the system evolve. And if I perform the same simulation with the tensor network of these new gates that I'm putting here for the time evolution, what I will observe is that the error that I commit is much larger. And there is an active research now for finding better algorithms in order to simulate with tensor network or related mathematical structures this real-time evolution. But for sure, I do believe that actually real-time evolution is a very good candidate to be like a good problem for quantum computers. And we know for by now that it's actually very difficult to perform this simulation on a tensor network.
Yeah, okay. All right. Okay, so I mean, I have more questions, but maybe others should ask. Okay, I mean, okay, I just remembered one other thing. I mean, is there any particular platform like superconducting or trapped ion which is better suited for these kinds of things, or that?
Yeah, for instance, for the nuclear shell model, what we have in this Hamiltonian is a all-to-all interaction.
Yeah.
So clearly, this may have a problem, and for instance, in superconducting circuits, this will create some overhead of gates, where you have to bring together the terms that interact according to the topology that you have on your device. While other structures or other architectures may be like may have it easier. But I would say it's still a complex problem for today's quantum computers.
Okay, all right. Thank you.
Any other question? If there is no other questions, Bhanu can continue if you have more questions.
Yeah, I have a question.
Prasenjit, okay, Prasenjit is the question.
Yeah, can you kindly open that entanglement part?
Yes.
Yeah, so you have told that, I mean, this entanglement entropy is being evaluated between these proton versus neutron partitions, right?
Yes.
Okay. So as you increase the number of neutrons, you are saying that these the entanglement between the proton and neutrons gradually decreases, and mainly the entanglement is in between the proton and neutrons, right?
This is what I said, at least for beryllium. But if you observe here on the neon case, you'll find a moment when these neutron-proton interactions start to raise some entanglement between different species. So it's not like a clear-cut criteria that you can say that by adding neutrons, the proton-neutron interaction will not raise entanglement between these degrees of freedom. But let's say that at least the proton-proton and neutron-neutron correlations will increase.
Okay, so I just want to understand, I mean, how do you measure this? Say you have, some neutrons and some protons, and you do the bipartitions, and then you find the entanglement entropy of any of the partition, say neutron versus proton.
No, this is not what I'm showing here. So this is a different calculation. What I'm doing here is the following. If I go back to the if I go back to the shell model, so each of these is a different degrees of freedom. Okay.
Right.
So what I'm doing here is to compute the reduced state of this degree of freedom with whoever else. Okay. So by pairs. So I choose, for instance, 0 against the 6 in this differential. So this would correspond to this point here. Okay, and then I compute the entanglement entropy of this reduced state of two orbitals only, and then I compute the same for any pair, and of course I order them according to the neutron or proton label, and this gives rise to this structure. This is the proton-proton, but there is a finer structure here for the different layers. So you can see there's the p3/2 against the p1/2 here. But if you go to larger systems, you will see that there is a like this PF layer also, or SD layer, sorry, appearing in the contribution.
Oh, okay. So that means you are telling that, I mean, due to some sort of monogamy, the entanglement is being some sort of, I mean, transferred between these initially, which was between this proton and neutron.
Exactly. This is some kind of emergent property of this nuclei, and this couldn't be tell by the observation of the Hamiltonian from from the beginning. So this was kind of a surprising fact, because if you observe the coefficient terms of these Hamiltonians, this doesn't indicate that this is kind of entanglement structure should appear.
Okay. Yeah, that's very actually interesting, because that's some sort of dynamics where this due to this monogamy, this entanglement is being I mean, some sort of concentrated only between the neutrons or protons.
Exactly.
Okay, thank you.
All right. Is there any other question? You have a couple of minutes more. If not from anyone else, if anyone would like to ask more question.
Okay, I'll do that later. I mean, so
Okay.
we are in touch, I think.
Yes, let me put here, this is my email. So just feel free to write me, and we can then just set up a conversation.
Sure, right. Yes.
All right, let's thank the speaker once again.
Okay.
And thanks everybody.
With this, I would like to thank all the 3 speakers of this session, and I close the session. So please join tomorrow at 8 o'clock.
Yeah.
All right.
Okay.
Thanks to our team who have worked very efficiently.
So we now end this meeting.
Pardon?
I'll now end this meeting.
Yeah.
Okay. Yeah, fine. Thanks. Thank you.
Thank you all.